Hello. Now, this video is already long enough. I mean, 10 hours if you watch part 1 and then plus another 4 hours for part 2. YouTube's max upload is 12 hours at the time of recording. So I won't keep you too long, but there are some things you know before you dive into it. How I recommend going through this is when we write the code, well, actually, first of all, if you're here to learn TensorFlow and Deep Learning, you've come to the right place. By the end of this 2-part video series, you'll have written hundreds of lines of TensorFlow code if you follow along with the coding videos, and you'll have a code-first introduction to some of the main concepts in deep learning. Now, again, how I would recommend going through these videos is to kind of have the YouTube window on one side. Once we get to the code part, you'll see it when it comes up. If you want to skip this intro, go to the timestamp below. And then have on the other side of your screen is Google Colab or a Jupyter notebook. That's where we're going to code. If you want all of the course materials, they're available on GitHub. There'll be links below for everything, by the way. And if you need to ask a question, go to the discussions tab on GitHub or leave a comment below. If you do have a question about anything to do with the video, whether it's on the GitHub discussions or YouTube comment, please leave a timestamp so that way I can check where you're referring to and then go to that point in the video and help you out from there. But without any further ado, get ready to write lots of TensorFlow code. Oh, and yeah, PS, I forgot this. This is part of a full course on TensorFlow and Deep Learning that I teach on zerotomastery.io. So if you like what you're going through in this video or in part 2, and you want to sign up to the full version, which covers a lot more materials in the order of 20 plus more hours of TensorFlow code and other specific parts of deep learning, there'll be a link to sign up in the description below. This is for real this time. Enjoy.
All right. Are you ready? I hope you are, because we're about to learn deep learning with, wait for it, TensorFlow. Now we could go back. I want to watch that again. Deep learning with TensorFlow. Now, if you like that little animation, that's just a taste of what to come, because we're going to have lots of fun learning deep learning with TensorFlow. Now, if you're here for that, you might be asking yourself the question, what is deep learning? Well, for these type of questions, and you'll probably notice this trend throughout the course. Oh, we've come to our friend Google here. What is deep learning? Oh, there we go. A type of machine learning based on artificial neural networks in which multiple layers of processing are used to extract progressively higher level features from data. Whoa, there's a lot going on there. You might be thinking, Daniel, why did we go straight to Google at the beginning of this course? Well, for questions like this one, where there's some sort of definition, this is what I want you to do. If you're not sure what it is, I want you to search for it and do some research, because what we're going to be focused on in this course is getting hands-on as quick as possible. So we're going to be writing lots of code. So let's come into my definition of machine learning for this course. Machine learning is turning things, data, into numbers and finding patterns in those numbers. And you might be thinking again, now Daniel, I've signed up to this deep learning with TensorFlow course. Why have you got machine learning there? Well, we'll answer that question in a second. But in terms of finding patterns, how does this happen? Well, the computer does this part. How? Code and math. Now, we're going to be writing lots and lots of code to do this. More specifically, code or deep learning code with TensorFlow. So let's have a look at machine learning versus deep learning. We have this fun little diagram that you might also find on Google. There we go. Artificial intelligence. Artificial intelligence, machine learning, deep learning. There we go. Very similar one here. So if we have the broad field, that is artificial intelligence. So trying to get a computer to think for itself. And now if we have machine learning, which comes under artificial intelligence, remember the definition for machine learning from before was writing code for a computer to figure out patterns in data. Well, deep learning is usually considered a subfield of machine learning. And so this is about all you need to know for the time being. I mean, if you want to do your own research, what deep learning is, go ahead and do that. But again, with this course, we're going to be focused on getting hands-on writing deep learning code. So if we come here, what's the difference between traditional programming versus machine learning or deep learning programming. So with traditional programming, you might start with some inputs. You might code up a bunch of rules. In our case, we've got our favorite Sicilian grandmother's chicken dish here. And she's got this recipe and she knows it off by heart and she's passed it on to you because you want to host a dinner party at your place and invite everyone over. So you might start with the inputs, which are the ingredients. We've got some vegetables here. We've got the chicken, of course, and we've got the rules. This is what we have to do. Cut the vegetables, season the chicken, preheat the oven, cook the chicken for 30 minutes, add vegetables. And then if you've done all this correctly, you'll get this beautiful output. But where machine learning algorithms usually differ is that you'll start with the inputs and the ideal output. So this is the major difference here. We're going to be very familiar with this concept of inputs and outputs by the end of the course. And so what happens with a machine learning algorithm is you'll show it examples of what the inputs look like and what the ideal outputs look like. So this is a beautifully cooked chicken here from this input. So you'll start with this, and then the algorithm will figure out, hopefully, the ideal rules to get from this input to this output. All right, so that's the machine learning in a nutshell. The next video, we're going to cover why use machine learning or deep learning. So now we've got a little conceptual overview of deep learning, very brief. The next question to answer is, why would we want to use machine learning or deep learning? So the good reason is, why not? I mean, you might have seen what machine learning is capable of. You might have heard of the power of deep learning, the power of artificial intelligence, and just all the problems we've got in the world. Why not we just use it? Maybe. But a better reason is, for a complex problem, such as maybe we're trying to teach a self-driving car to drive, can you think of all the rules you'd have to code if we remember back to our Sicilian grandmother's famous chicken recipe? Maybe you can code up the rules for that, such as preheat the oven, cut up the vegetables, cook the chicken for 30 minutes. But in terms of self-driving car, when you go for a drive, do you think about the rules in your head or do you just drive? You'd need stop signs, you'd need traffic lights, you'd need what to do for another car. You can imagine how that problem gets quite out of hand pretty quickly. So for a complex problem, can you think of all the rules? Probably not. And so I found this great comment on one of my YouTube videos here, the 2020 Machine Learning Roadmap. So be sure to check that out if you haven't checked it out. This is from Yashawi. I think you can use ML, so machine learning. If you see ML throughout this course, it's machine learning, for literally anything as long as you can convert it into numbers and program it to find patterns. Literally. It could be anything, any input or output. Oh, we've seen that again, input or output from the universe. Wow. Important piece to note here is as long as you can convert it into numbers. Now again, if you're reading this and you're like, Daniel, this doesn't make sense. I've never experienced deep learning before. Don't worry. We're going to have plenty of practice throughout the course. But here's the exciting part. I think you can use ML for literally anything as long as you can convert it into numbers. I want you to keep that sentence in your head. However, when should you not use machine learning? If you can build a simple, rule-based system, or actually maybe not very simple if you're building a complex software product, that doesn't require machine learning, do that. Where's this come from? Well, this is from a very wise software engineer. It's actually Rule 1 of Google's Machine Learning Handbook. So this is our first external resource for the course. There's going to be a bunch of these, so don't worry. I'll link them to wherever you need them. So this is the rules of machine learning. Best practices for ML engineering. We're not going to go through this, but I'm going to link to this. If you want to read through this in your own time, feel free to do so. This is a very exhaustive resource to get you up to scratch on how Google thinks about using machine learning. So we'll come back. So yeah, if you think about using machine learning, but you think you can code up a simple rule-based system, you should probably do the rule-based system rather than machine learning. So what is deep learning good for? Problems with long lists of rules. So when the traditional approach fails, machine learning / deep learning, again, Whenever you see throughout this course machine learning / deep learning, you can kind of think of them as the same thing. May help. Continually changing environments. So if the problem you're trying to solve is constantly changing, I mean, the information you're dealing with is continually changing. The good thing about deep learning is that it can adapt to new scenarios. So if the problem you're working on changes, you can train another deep learning model on those changes. Discovering insights within large collections of data. So imagine the problem of trying to take photos of food and identify what's in that photo. Can you imagine trying to handcraft the rules for 101? So you just wanted to start with, you were building an app called 101 dishes. So you've got maybe spaghetti, ramen, steak, eggs, kale, coffee. Can you imagine trying to handcraft the rules for what 101 different kinds of food look like? I can't. Now, what is deep learning not good for? Typically, again, take this with a grain of salt because as you'll see, as you get deeper into your, pardon the pun, deeper into your deep learning journey, you'll see there are lots of ways, if you're stuck on a certain problem about what we're about to see on this slide, you can kind of formulate ways to circumvent that problem. When you need explainability. So the patterns learned by a deep learning model, again, we haven't seen these, but we will get familiar with them, are typically uninterpretable by a human. So if a deep learning model is finding lots of patterns in numbers, which we'll see throughout this course, typically those patterns are quite hard to interpret once you look at them. When the traditional approach is a better option, remember, if you can accomplish what you need with a simple rule-based system, you should probably do that. When errors are unacceptable. So since the outputs of a deep learning model aren't always predictable, meaning they may contain errors, maybe deep learning isn't your best option. If you need a software system to do the same thing every single time, potentially a non-deep learning based system is what you're after. And when you don't have much data, so deep learning models usually require a fairly large amount of data to produce great results. However, we'll see how to get great results without huge amounts of data. So as I said, typically not good for. There are ways to kind of try and circumvent these points here. So let's have a look again. Machine learning versus deep learning. So in terms of when to use machine learning versus deep learning, traditional machine learning algorithms have typically performed best on structured data. So what I mean by structured data is data or information you can find in an Excel spreadsheet or a Google Sheets. So you've got rows and you've got columns. So this is clearly row 2, for example. We've got car sales, we've got a make, we've got a color, we've got odometer, doors, and we've got a price. So maybe we want to build a deep learning model or a machine learning model to take these parameters here, which are often referred to as features. So columns, features, make, color, odometer, doors, and predict the price. Whereas deep learning typically performs better on unstructured data, such as natural language text, or in the case of we wanted to build our Food 101 application to take photos of food and identify what's in that food, or if we have a Wikipedia article talking about deep learning. So this is an example of data that you could argue that there is structure to this picture. Like, I mean, you got a shape here, you got shapes there, and here you've got a sentence there, but it's certainly nowhere near as structured as what you find in an Excel spreadsheet. And then again, you could have something like voice, so sound waves. If we go here, we'll dig a little deeper into the structured versus unstructured data. Let's have a look at some of the most common algorithms you're going to come across in the machine learning and deep learning world. Of course, this slide only goes through just the names of the algorithms, but we're going to be getting hands-on with building some of the most common deep learning algorithms you see coming up in a minute. So on the machine learning side of things, you might have the random forest, the naive Bayes, nearest neighbor, support vector machine, and many more. And since the advent of deep learning, these algorithms here are often referred to as shallow algorithms. Now, what that means for now is not too important. I just want you to start getting familiar with some of the terms you're going to hear in the machine learning and deep learning world. So when they come up, you're not going, wow, what does this mean? Now, On the deep learning side of things, we have neural networks, fully connected neural networks, convolutional neural networks, recurrent neural networks, and the transformer architecture is a fairly new one that's only come out in the last couple of years. And for this course, we're going to be focused on building these 4 type of neural networks here with TensorFlow. These are kind of like the bedrock type neural networks, the ones that a deep learning field over the past decade or so has been built on top of. And again, if we're looking at through the structured data versus unstructured data paradigm, these algorithms here, the machine learning algorithms, are typically better performing on structured data, whereas neural network type architectures are typically better performing on unstructured data. However, depending on how you represent your problem, many algorithms can be used for both structured data or unstructured data. Now, we've covered the names of a few types of different neural network architectures. So you're probably wondering, or the question in your head is probably, what exactly are neural networks? So let's tackle that in the next video. All right. So in the last video, we heard that neural networks are a common deep learning algorithm. So what exactly are neural networks? So remember, for these type of what questions or definition questions, I want you to get really familiar with going in, what are neural networks? Explained, neural networks. Neural network, okay, Wikipedia. These are generally quite wordy definitions. A neural network is a network of circuit or neurons, or in a modern sense, an artificial neural network composed of artificial neurons or nodes. So you might get diagrams like this. And so that's just a one-sentence definition, but let's have a look of an overview of what neural networks are. So we might start with some data here, whether it be images of food or some natural language text or some sound waves like what's going into the microphone here. And then if we want to use that data with a neural network, we're going to have to somehow turn this into numbers. So this is called a numerical encoding. There are many different names for it, but we're going to treat this as a numerical encoding. And you might be wondering, what are these square brackets? Well, that's to represent that we've got this data here and we've turned it into a numerical encoding, which is often referred to as a tensor, but we'll see that. We're getting ahead of ourselves here. And so before data gets used with a neural network, it needs to be turned into numbers. Okay, remember our one-sentence definition of machine learning. Machine learning algorithms are about turning data into numbers and finding patterns in those numbers. So this is our numbers here. Now we might feed these numbers here that represent our data into a neural network. If we come here, this is a simple neural network. This is a very similar diagram here, but probably a little bit more colorful. And what is this neural network going to do? Well, it's going to learn a representation, all the patterns, features, weights. These are other terms you might hear of what kind of representation it learns. And again, depending on what problem we're working on, whether it's recognizing images or discovering meaning from text or trying to turn a sound wave into text, you're going to have to choose the appropriate neural network for your problem. We'll see how to do that in upcoming lessons. So this is, okay, we've got 3 steps so far. We've got data as inputs. We've turned that data into numbers. We're going to feed that to our neural network, and this is going to learn a representation or find patterns in these numbers. What does it do then? Okay, then it's going to create some representation outputs. You might notice that these numbers have been transformed. And so this might not mean anything to us now. We're going to inspect this in a moment with TensorFlow code. But what these representation outputs are basically the neural network going, you know what, I've taken in these numbers here. I've found the patterns. These are the patterns that I've found in a numerical representation form. Okay, all right, and then what do we do next? Well, it's up to us to take these representation outputs that our neural network has learned about our data and convert them into human understandable outputs. So say, for example, in classifying images of food, we might have a photo of ramen here, Might have to turn that into numbers in some way. Might have to feed it through our neural network and get our neural network to discover patterns in that, so it outputs into a representation output. And then it's our job to write some code to convert these representation outputs to hopefully, if it's learned it right, it's going to output the label ramen. And the same goes for this photo of spaghetti. We could pass that through and it goes to there. And maybe for this tweet, we want to say we were building a system that was to read a tweet and say we wanted to know where natural disasters are going on in the world. Can we convert this tweet into numbers, feed it through a specific type of neural network, convert it into some sort of representation output, and then label it as, say, a disaster-based tweet or not a disaster? And then finally, say we were building a smart speaker or something to recognize sound waves. How would we turn those sound waves into numbers? Pass it through our neural network, get our neural network to discover patterns in those numbers, create a representation output, and then translate or transcribe, I think transcribe's a better word there, transcribe that to, hey Siri, what's the weather today? Whoa, there's a lot going on here. But again, this is the whole premise of neural networks here. We have some inputs, we turn those inputs into a numerical encoding. Our neural network that we've chosen for our specific problem will learn a representation referred to as patterns, features, or weights. We'll create some kind of representation output based on the patterns it's figured out, and then it's up to us to define what we want our outputs to look like based on this. So let's look at the anatomy of a neural network. So if we have it here, the first layer of a neural network is referred to as the input layer. So when you see diagrams like this is actually a very common diagram of what a neural network is. If we go here, neural network, back, what are neural networks? There we go. So we have inputs, something in the middle, outputs. Remember in our previous slide, our input, the data goes in here. In this case, this would be labeled with, these are two hidden neurons. Again, we're going to get very familiar with these terms as we keep going. And in the middle here, there's hidden layers. You'll notice this is a plural. So usually there's one input layer, or depending on what data you work with, you might have multiple input layers. Hidden layers, this can be an arbitrary amount of layers. So you could have one hidden layer, or you could have 152 hidden layers. So these hidden layers learn the patterns in the data. And then it has a output layer. So this outputs the learned representation or prediction probabilities. Again, we're going to get very hands-on with all of these terms. I don't want you to get too flustered with the terms that I'm putting out here because we're going to see all of these in action. And in this case, with the input layer, there's two neurons, and there's three hidden neurons here, and there's one neuron in the output layer. And I want to put a little tidbit here, is that when I say learns patterns in data, it's kind of an arbitrary term because you're going to hear lots and lots of jargon and different terms for different things in machine learning. And I'll try use as many different terms as possible, but also tie them back to kind of a single term. So when you hear me saying patterns, you'll often hear different things like embedding or weights or feature representation or feature vectors. And these are often all referring to very similar things. Now, when it comes to neural networks, we've seen the anatomy, but there's also a few different types of learning. The first one is supervised learning, semi-supervised learning, and then unsupervised learning, and transfer learning. Whoa. And so supervised learning often involves having data and labels. So in the case of identifying different images of food, we may have the data would be the images of the food, and the labels would be the labels of food. So ramen, spaghetti, coffee, steak, pizza, associated with each one of those images. Semi-supervised learning has some data, or actually could be as much data as supervised learning, but it only has some labels. So, for example, maybe we had 10,000 images of food, and we only had labels for 1,000 of those images. And we wanted to train a neural network on the images which have labels And then we use that neural network to try and label the other images of food, the ones we don't have labels for. And then unsupervised learning is you basically only have data and no labels. You kind of pass your data to a machine learning model or a neural network or a deep learning model. Again, very similar terms for very similar concepts. And you kind of go, hey, I'm not sure what patterns are going to be within this data, but see what you can find anyway. And then transfer learning, which is actually a very, very important concept. We're definitely going to get hands-on with this one. The beautiful thing about deep learning models is when they learn patterns in some sort of data set, those patterns can be used for another problem type. So transfer learning would be taking what one deep learning model has learned on some set of data and then using it in another problem on another set of data. So in our food image discovery or image classification problem, we may take what a machine learning model has learned on just pictures of the world, so general pictures, and apply that to our specific images of food. Now, in terms of this course, we're going to be writing lots of code to do supervised learning and transfer learning. But again, the premise of what we're doing, starting with inputs, turning that into numbers, and then having some sort of algorithm go through those numbers, find patterns, create outputs, can also be used for these other two types of learning here. All right, so now we've heard a little bit about deep learning, we've heard about neural networks. What is deep learning actually used for? Now, what is deep learning actually used for? Well, we'll return back to this comment we saw before, because this is actually a beautiful comment. Thank you very much, Yashui. Hopefully I'm saying that right. I think you can use ML for literally anything as long as you can convert it into numbers and program it to find patterns. Literally, it could be anything, any input or output. Again, lots of emphasis on input or output from the universe. And so I want you to keep this sentence in your mind, because by the time you finish this course, you're going to look at the world through a different lens. I mean, you're going to walk down the street and you're going to wonder, how could I represent this experience that I'm having in numbers and then program a machine learning algorithm or a deep learning algorithm to find patterns in those numbers? Seriously, once you learn the concept of machine learning and deep learning, you start to look at almost everything through the lens of turning something into numbers and finding patterns in those numbers. Now, let's have a look at some common deep learning use cases that you've probably experienced in your day-to-day life. So the first one is recommendation, translation, speech recognition, computer vision, natural language processing. Again, emphasis on some here because there's many more, but these are some of the main ones. So the recommendation here is my YouTube home screen. We've got some programming videos. We've got a video of my friend's YouTube channel, an interview from Peter Norvig, one of the heroes of artificial intelligence, some RuneScape videos, because that was a game I love to play, jiu-jitsu, some bodybuilding, oh my goodness, more hacking videos. So I can safely say YouTube has learned me pretty well. And now this is based off, again, my history of the things I've watched on YouTube. And so if YouTube has all of that information, it can go, you know what, Daniel, I've seen 100 different people, or maybe in the case of YouTube, there's actually close to, I think, over 1 billion users on YouTube. Maybe there's 100,000 people out there like me. And they're like, you know what, you've watched programming videos, so we're going to show you this one. And you're interested in the movie Her, great movie, by the way. We're going to show you this soundtrack based on the patterns that we found in everyone else's YouTube browsing history. And then in the case of translation, we might have some language here. This is English, the language that I speak. And if I wanted to speak Spanish, I'm not even going to pretend that I can pronounce that. I can type in my sentence here. Deep learning is epic. And then Google will run a deep learning algorithm to figure out the patterns in this English sentence and translate that into Spanish. So if you're a Spanish speaker out there, you can tell me or send me a message of how accurate this translation actually is. In the case of speech recognition, we may have some sound waves, again, like what I'm saying here. And when I find out from Siri, it's like, hey, who's the biggest big dog of them all? And so deep learning probably go through that sound wave and transcribe it into this sentence here. Computer vision, actually, this image is a bit painful for me. because this is actually from some security footage from one of my neighbors. You see this car here? If I had a computer vision algorithm that was running on this security camera, maybe I could pick up this car or found the license plate, because this car, actually, the trailer, it had a trailer on the back. The trailer came off as it was driving past my car on the street, and the trailer hit my car and basically totaled the whole car. So now I need to find a new car, and this was the car that did it. So if their security footage had a computer vision algorithm, maybe we could have found it. So I'm still on the investigation for that, but that's one use case computer vision can be used for. So again, a deep learning algorithm may take the pixels of this image, find the patterns and go, you know what? I've seen a car that looks like this before. Maybe it's a Toyota Hilux that you're looking for. Anyway, we'll leave that problem there before I get too upset. I really loved my car. And the other one is natural language processing. So maybe taking in an email, you got your text here. So unstructured text here. Hey, Daniel, this deep learning course is incredible. Oh, thank you so much. I can't wait to use what I've learned. I hope you send me a lot of these type of emails here. That is my actual email address, so feel free to send me whatever you want. And this is not spam, so this is something I want to see in my inbox. But if you're sending me messages like, hey, Daniel, congratulations, you win, that is a big number. I'm not going to pretend that I can read that out loud without slowly deducing how many zeros there are. That's spam, so I don't want this in my inbox. I want a natural language processing algorithm, a deep learning algorithm, to put that in my spam box. And so if we dive a bit deeper, you might see these referred to as sequence to sequence, or sec to sec for short, deep learning problems. Now, the premise here is if sequence to sequence doesn't make much sense, just think about it like this. You have a sequence of words and you want to translate or transform that into another sequence. That's what you're trying to doing with seek to seek problems. Same with here. You might have a sequence of sound waves and you're trying to convert them into another sequence of words. And for this problem here, it's called classification or regression. Now, classification, is this email not spam or spam? Is it one thing or another? There's also multi-class classification, but we'll get onto that in a second. And then regression, you might be wondering, hey, Daniel, I've heard regression is more so for predicting a number. Yes, well, in this case, in our computer vision problem, our numbers might be the pixel coordinates of where the corner of this box should be. So maybe we start with an image that doesn't have a box on here, and then our computer vision algorithm looks over it, or our object detection algorithm looks over it, and goes, you know what? I think the car is most likely in the box here. So maybe that's 50 pixels in from the x-axis and 60 pixels down from the y-axis there. And so that's that corner, and then it does the same for each other corner. Now, I want to show you another phenomenal use case for deep learning that only just recently happened. So if we go here, now you could also just go deep learning use cases, and you're going to get a whole bunch of different ones. There we go, automatic speech recognition, image recognition, natural language processing. But there's one I'm specifically looking for. Now this is DeepMind. Deep stands for deep learning. Now this is a deep learning research company. Boom, AlphaFold, a solution to a 50-year-old grand challenge in biology. I'm not going to go too much into this, but this is possibly one of the biggest breakthroughs in AI, powered by deep learning, as well as, do I want cookies? Fine, I'll have the cookies, as long as they're delicious. Now, do we have deep learning here? Here we go. Now, new deep learning architectures we've developed have driven changes in our methods for CASP14, enabling us to achieve unparalleled levels of accuracy. Again, I'm not going to go too deep into this, but this is the type of, I believe they've used a deep learning algorithm. This is actually brand new, to figure out how a protein should fold. Now again, I haven't read up on the research here, but this is just the type of things that deep learning can be used for. If you remember the comment we looked at before, the YouTube comment, I think you can use ML for literally anything as long as you can convert it into numbers and program it to find patterns. So that's what DeepMind have done. They've taken proteins, turned them into some sort of numerical representation, crafted a deep learning architecture to find patterns in those proteins. So this just blows my mind. As I said, by the time you finish this course, you're going to have a new lens on the world. So we've seen what deep learning can be used for. How can we write these deep learning algorithms? So this is where TensorFlow, that's worthy of seeing again, TensorFlow comes in. So in the next video, let's figure out what TensorFlow is. We've seen that deep learning can be used for a range of different problems, including how deep learning architectures are now figuring out the protein folding problem. In other words, finding patterns in proteins. I mean, proteins as in the building blocks of you and I. So if proteins are the building blocks of you and I and deep learning is finding out patterns in that, how might we create such deep learning architectures? And if you see deep learning architecture, deep learning model is kind of another word that you can substitute in here for architecture. So when you see deep learning architecture, you can think deep learning model. And when you think deep learning model, you can think deep learning architecture. So how might we build such a thing? Now, this is kind of a segue to TensorFlow. The TensorFlow is going to help us build deep learning architectures or deep learning models. And now, of course, naturally, you're probably asking, well, what is TensorFlow? Let's figure this out. TensorFlow is an end-to-end machine learning platform. You can write fast deep learning code in Python, which is the language we're going to be using, / other accessible language such as JavaScript. And when you write that fast deep learning code using TensorFlow, that code is able to run on a GPU, which is a graphics processing unit, / TPU, which is a tensor processing unit, hence TensorFlow. We're going to see the significance of that in a moment. With TensorFlow, you're also able to access many pre-built deep learning models. When we saw types of learning, transfer learning is where you'll use a pre-built deep learning model. In other words, leveraging the patterns that one deep learning model has learned on another problem to your own problem. We'll see how we can use TensorFlow Hub to do that, which is a TensorFlow resource. Now, it's the whole stack. This is a follow-on from this point here. TensorFlow allows you to pre-process data. In other words, turn that data into numbers, model that data. In other words, build a neural network to find patterns in that data, and then deploy your model into your application. So depending on what you're building, you might want to take the deep learning model, such as in the case of our security recognition system, if we wanted to identify different types of cars, we might want to take our computer vision model and deploy it into our security camera and use that to detect cars that have maybe crashed into other cars. In my case, again, you can probably hear the sadness in my voice. It makes me emotional when I talk about my poor little car. And it was originally designed and used in-house by Google, one of the largest internet companies in the world right now that basically machine learning runs everything that they do, machine learning and deep learning. And it's now open source, which means we can leverage the tools that Google use to work on our own problems. So that's a bit of an idea of what TensorFlow is, but why TensorFlow? Well, it allows us easy model building. Now, again, this is from the TensorFlow website. We're going to get very familiar with this website. Robust ML production anywhere. So train your models, deploy them in the cloud, on-prem, which means on your server if you have one locally, in the browser or on device, no matter what language you use. Powerful experimentation for research. So if you found a new idea, such as DeepMind building a new deep learning architecture to discover patterns in protein folding, you might want to rebuild their research using a TensorFlow-powered deep learning model. And so we're going to be doing lots of this, easy model building. And we're also going to do a little bit of this throughout this course, but that's for later on. In the meantime, let's check out the tensorflow.org website. So here we go. An end-to-end open source machine learning platform. There's a lot going on here. So you've got some examples here. You can see, you can install it, you can learn it. There's the API. Probably the exercise for this lesson is to go to tensorflow.org and have a play around. Just get yourself familiar with the website. If you've never looked at this website before, there's probably almost too much here, so it can be a little overwhelming, but that's all right. Just follow your curiosity and see what's there. Let's go back here. Now, why else might we want to use TensorFlow? Now, this is Francois Chalet, and this is a tweet that he put out recently. With tools like Colab, we'll get familiar with Colab, Keras, Keras is a part of TensorFlow, and TensorFlow, virtually anyone can solve in a day with no initial investment, so that means basically for free, problems that would have required an engineering team working for a quarter is 3 months, and $20,000 in 2014, which is so true. So the resources we're going to use throughout this course, just 5 years ago, or just a little bit over 5 years ago, would have cost a fairly large amount to even get up and set up. And not only like the things that we're going to be doing ourselves would have required a whole team working for a couple of months that we're going to be getting up and running within, in some cases, a few lines of code. So this is why it's really, really exciting to be able to use TensorFlow and these other resources here to work on deep learning problems. So now, we mentioned before, TensorFlow allows you to run your numerical code on a GPU/TPU. Now, what exactly is a GPU/TPU? If we come here, this is what, if you Google the photo of a GPU, you'll get up this, graphics processing unit. These are actually NVIDIA cards. This is an RTX 3080, and I believe this is a P100. So you don't need to worry too much about these. You can install these in your own computer, like these type. These are usually built for servers. Say you have like a warehouse of different computers. This is often what you'll get when you connect to a cloud-hosted GPU, but we're getting a little bit too ahead of ourselves. The major thing you need to know about these graphics processing units is that they're very fast at crunching numbers. So when I say we want to find patterns in numbers, these type of computing chips are very fast at finding or doing numerical calculations. In other words, finding patterns in numbers, the numbers that we've converted our data into. And in the case of TensorFlow, it also allows you to use TPUs, which are tensor processing units. Now, this looks like a pretty advanced piece of hardware. If we go here, what is a TPU? Again, for these questions where you have what is something, don't be afraid to look it up. Tensor Processing Unit. Whoa. Tensor Processing Unit is an AI accelerator application-specific integrated circuit developed by Google specifically for neural network machine learning, particularly using Google's own TensorFlow software. Okay. So this is what we're going to get familiar with. And so if you think of a TPU, if graphics processing units are fast at crunching numbers, well, a TPU is probably even faster. But we're going to see throughout this course how we can get access to these chips. If you don't have, unless you're Google, you probably don't have this in your computer right now or in your bedroom or something like that. You maybe not even have one of these, but that's okay. We're going to look at resources throughout the course that we can use to gain access to these fast computing chips for free. Now, we've heard a lot about tensors, or specifically TensorFlow. And naturally, you might be asking, what is a tensor? So let's look at that in the next video. We've seen TensorFlow, discussed what it is and why we should use it, but we haven't actually discussed half of its name. What exactly is a tensor? Great question. Now, remember our slide for neural networks? I'm going to give you a little hint. Well, we kind of revealed this earlier, so spoiler alert. Remember how we started with our inputs, which is maybe some images, maybe some natural language text, maybe some sound waves, and then we create a numerical encoding. We pass that numerical encoding to our neural network, which learns patterns in that numerical encoding. And then our neural network outputs some kind of representation outputs. And then we convert those into something that we can understand. Now, the secret here is that these are tensors. Whoa. And so the most basic definition I can think of for a tensor is some way or some numerical way to represent information. Now, what that information is, that's totally up to you. But just think of it as if we wanted to encode these images into some kind of numerical form, we're going to be turning them into a tensor. And we're going to see this in practice as we write TensorFlow code. We're going to pass that tensor to our neural network. Our neural network is then going to figure out different patterns in these numbers. And then it's going to output another tensor, which is the patterns that it's learned in our original numerical encoding. And then we take this tensor, the representation outputs from our neural network, and convert them into something that we can understand. So if we take away some of the excess parts, this is the founding principle of neural networks and tensors in general. I mean, this is where the name TensorFlow comes from. If we imagine our inputs, our food image classification problem, we turn it into a numerical encoding, in other words, a tensor. We pass it to our neural network. Our neural network finds the patterns and then outputs those patterns that it's found, and again, this is another tensor, into something that we can understand. So if you imagine, this is the flow. This is where the flow in TensorFlow comes from. It starts here by creating a numerical encoding, then it flows through our neural network, then our neural network flows it on again, the output here, and then we, again, another little flow here into something that we can understand. So that's what you have to understand for the concept of tensors. If you want a little bit of an extension, I'll show you one of my favorite videos on what is a tensor. This can actually be your homework, is this video here. So this is available on YouTube. What is a tensor? So I want you to watch this video, figure out Dan Fletcher's, I'm not quite sure how to pronounce that name, but Dan, also a great name. Watch Dan's explanation of what a tensor is, and then come back to the other Dan, me, and then see if you can line these up. Remember, a tensor is a way to represent some sort of data in numerical form. So if we come back, we've covered what TensorFlow is, we've covered what deep learning is, we covered what neural networks can be used for. What else are we going to cover? We'll look at that in the next video. We've covered a fair bit in this course already, but let's get specific. What are we going to cover throughout this course? Well, I have a great tweet here from Elon Musk, Dose X machine learning. So learning ML or machine learning, deep learning from university, you get this small little brain here. Online courses such as this one, you get some activation here. From YouTube, whoa, we're really starting to activate the brain here. From articles, look at that superpower. And then from memes, I mean, this little figure here looks like they can control the whole universe. So we're strictly going to be focused on learning deep learning through memes. No, I'm kidding. As fun as that is, here's what we're going to cover. Now, this is pretty broad, but this is just like sort of a list of the topics we're going to look at. TensorFlow basics and fundamentals, pre-processing data, in other words, getting it into tensors, so turning it, say, from a picture into a tensor, building and using pre-trained deep learning models. We're actually going to be building our own, a lot of them from scratch, and then we're also going to be using pre-trained deep learning models, fitting a model to the data, so in other words, learning patterns, so fitting the models that we build and even pre-trained deep learning models to the data we've pre-processed. We're going to make predictions with our models, so using the patterns that our deep learning models have used. We're going to figure out how we can evaluate those model predictions. So if we were building a food classification app and our deep learning model took a photo of pizza and it identified it as steak and it did that 1,000 times, how can we evaluate our model's predictions to better understand them and figure out how we can improve them going forward? We're going to see how we can save our model and load it, such as if we trained a food classification model and we wanted to use it in our application, we might train it somewhere and then save it somewhere else so that we can use it later on. We're going to figure out how we can use a trained model to make predictions on custom data. So the custom data here is important because a lot of the time you'll practice training deep learning and machine learning models on data sets that have already been created for you. But the real test of where a machine learning or deep learning model, whether it performs well or not, is on data it has truly never seen before. We'll get familiar with this as we go on. And how are we going to go through all of this? Well, we have the cook and we have the chemist. Chemist, you can imagine, is very exact. Everything has to be millimeter precise or milliliter precise if you're doing some sort of chemical experimentation. And then you have the cook. Maybe the cook is your Sicilian grandmother and she's making this beautiful roast chicken dish that she's made 100 times. And of course she has the rules. She knows it off by heart. But this time she decides, you know what? I'm going to sprinkle a little more seasoning in here. I'm going to try a different set of vegetables instead of the traditional set of vegetables that I use. So the cook is a little less exact. A cook likes to experiment and try different things. And in our case, that's exactly how we're going to go through all of this. We're going to experiment. In fact, that's going to be basically our motto for the entire course is experiment, experiment, experiment. We'll be cooking up lots of code. So if we flip this in, boom, we're going to be building ourselves a TensorFlow workflow. We've seen this before. This is what I want you to get really familiar with, is that getting the data ready, turning it into tensors. Then we're going to learn how to build or pick a pre-trained model to suit our problems using TensorFlow and TensorFlow Hub. We're going to fit the model to the data and learn to make a prediction using our trained model. So prediction is where our model takes some sort of sample and then makes prediction outputs that we can turn into something like, if we fed it an image of a bowl of ramen, what does our model think that image is of? We're going to learn how to evaluate our model's predictions. Then we'll figure out how to improve our models through experimentation. Again, experiment, experiment, experiment. And then finally, we're going to look at saving and reloading our trained models. So with that being said, we know what we're going to cover. How should I approach this course? Great question. Let's answer that in the next video. We've been through a plethora of different what questions. And oftentimes you'll see in online courses and online resources, there's a lot of what going on, like what we're going to be doing. But not so often is there how you should approach this course. So we talked about a lot of different concepts, deep learning, neural networks, TensorFlow, tensors. How should you approach trying to learn these things? Well, here's some guidelines. Write code, lots of it. Follow along. So you're going to see me writing a lot of code, and I'm 100% going to make a lot of mistakes. So follow along if you can and make the mistakes with me. So our first motto is, if in doubt, run the code. If that doesn't make any sense, if you haven't written much deep learning code before, don't worry, we're going to be writing lots of it. This motto is going to be ringing in your head. As much as you're going to look in the world through the different lens of trying to figure out how machine learning and deep learning can be used with almost any problem in your life, you're also going to be hearing this in your head as well. Explore and experiment. So our second motto is experiment, experiment, experiment. This is a great follow-on. If in doubt, run the code. We want to try as many different things as possible because when we're running experiments, I'm going to emphasize trying a lot of different small experiments. Why? Because that helps us, even if the experiment fails, it helps us figure out what doesn't work. And in a lot of cases, figuring out what doesn't work is often just as helpful or even more helpful than figuring out what does. Because how rare, in terms of anything you've worked on previously, how rare is it that you got everything you needed to do correct the first time? Especially in deep learning. I mean, chances are, for the problem we saw, for the deep mind figuring out how to write a deep learning architecture for protein folding, I can only imagine how many experiments they would have done to set that up. Now, motto number 3 is going to be visualize, visualize, visualize. And what I mean by this is if you're not sure of something in the code that we're writing, recreate it in a way that you can understand it. And oftentimes that will be visualizing it in a different way. So say we turn some sort of data into tensors. What do those tensors look like? Can we turn data into a tensor and then turn it from that tensor back into data? Those are the type of things we'll want to be looking at. Now, again, I cannot stress every point on this slide is worth writing down. Ask questions, including I'm going to put inverted commas here. You can't see what I'm doing, but I'm raising my fingers up towards the sky and I'm curling them in as if I'm saying the dumb ones. Because there is no such thing as a dumb question. You'll get very smart if you ask lots of dumb questions. So make sure if you don't understand something, you can do exactly what we've done. Go here. What is deep learning? You can search that for yourself. Spend 10 minutes reading here. You'll know a lot more than what you did before you asked the question. Or ask in any of the resources that you have available. So there's the Discord chat, and I'll put some more links in another resource of where else you can ask questions. Do the exercises. So each of the code notebooks of concepts that we have, have exercises attached to them. So I want to emphasize again, try them yourself, write lots of code before looking at the solutions. Now, this course doesn't cover everything, of course. If this is your first introduction to deep learning, you're going to quickly realize how broad the field is. So if you want to learn more on something, look it up. I want you to become an expert at searching for things that spark your curiosity. Share your work. If you want to learn something, I find, aside from doing it yourself or replicating it yourself, the next best way, or possibly even better, is to teach someone else. So if there's a concept that you've learned in this course and you want to really nail it, you want to get better at it, figure out how you can explain that to someone else. So maybe you write an article sharing how you've learned how to turn data into tensors, write a deep learning model with TensorFlow, figure out patterns in those tensors, and then turn those representation outputs from that neural network into some sort of human understandable output. Maybe you want to share that with others. That's going to be a great way to really cement your knowledge. Avoid the following things: overthinking the process. So I can't stress enough, this comes back to our number one motto: if in doubt, run the code. Again, we're going to be learning so many different concepts. You're probably going to be overwhelmed at different points, but don't worry. Everyone who's learned anything has gone through the trouble of basically creating new patterns in their brain to understand the new concept that they're learning. So if you're overthinking the process, you're going to hold yourself back. And avoid the I can't learn it mentality. That's bullshit. You can learn it. All right, enough talking. I love that fire. Let's do it again. Let's code. We've got an overview of deep learning. We've got an overview of TensorFlow and tensors. It's time to get hands-on. This is very exciting. So I'm going to open up my web browser. This is the tool we're going to be using throughout basically the entire course, is Google Colab. So if we come here to colab.research.google.com. If you're unfamiliar with Google Colab, check out the Colab overview, or if you just go to colab.research.google.com, you can go to the examples tab here, and you can open up a whole bunch of different tutorials to go through and learn about Google Colab. If you're just starting out, I'd check out Overview of Collaboratory Features or the Markdown Guide. But as I said, if you want another overview, check out the overview video because we're going to be using Colab a whole bunch throughout this course. So let's get started. I'm going to open up a new notebook here because we're going to, I don't know if you can hear that, but I'm rubbing my hands together because I'm so excited. We're going to get hands-on with TensorFlow. So some of the most fundamental functions of TensorFlow. And let's give our notebook a title here. So let's go 00 TensorFlow Fundamentals. The reason I'm doing 00 at the start is because we're going to, by the end of this course, have probably about 10 or so of these notebooks. So the 00 at the front just lets us know what order they come in. So TensorFlow Fundamentals, and now let's put in here, in this notebook, we're going to cover some of the most fundamental concepts of tensors using TensorFlow. Beautiful. And we can put a little hashtag at the front. And then what I did there was I did Command MM and turned it into a markdown cell. And then if I press Shift and Enter, we get another code cell here. Beautiful. And so to enable us to write code, we're going to have to connect here. So just press the Connect tab there. And let's get a little outline of what we're actually going to do. So more specifically, this is what I do with most of my notebooks. Whenever I come to something before writing code, you're going to hear me say write code as much as possible, but I just like to give myself a little bit of an outline so I know the direction of where I'm heading. So we're going to cover, what do we have? Introduction to tensors. We might as well get some information from tensors. If none of this makes sense, don't worry. We're going to code it up by hand. Manipulating tensors. So changing the information that's stored within tensors. And then we're going to go tensors and NumPy. If you've ever used NumPy, TensorFlow you'll find has very, very similar features to NumPy. using at TF function, which is a way to speed up your regular Python functions in TensorFlow. Because remember, the whole premise of using TensorFlow is so that we can use GPUs with TensorFlow or TPUs to do faster numerical computing. That's what we're after here. And at the end, we're going to have a few exercises to try for yourself. Alrighty, let's just jump straight in. I'm going to put another little heading here. Introduction to tensors. And then I'm going to press Command MM to turn that into Markdown. Now for another cell here, I'm going to press Command MB. Oh, I didn't press Escape while I had this cell highlighted. So Escape, Command MB will give me a new cell. Now I'm saying Command, however, if you're on Windows, it's probably Control. Because I'm on a Mac, it's Command for me. So the first thing to do is to use TensorFlow is that we have to import TensorFlow. Now, I want you to try and follow along as much as you can with these videos, right? When I'm writing code, I want you to be writing code by my side. It's like we're partner coders here. And if you can't keep up because I'm writing a little bit too fast, that's all right. I've had a lot of practice writing TensorFlow code. And so, again, I've spelled TensorFlow wrong. Maybe you catch my errors before I do. If you need to slow down the video or watch something again, that's perfectly fine. I'm probably going to need to slow down my code so I don't write as many typos. So this is how we're going to import TensorFlow. TensorFlow becomes the alias TF in Python. TF is basically universal. You can put it as what you want, but use TF, trust me. And then I'm going to use print TF dot double underscore here, version, to check what version of TensorFlow we're using. If you're using Google Colab, you should be using TensorFlow 2 point something. I'm currently using 2.3.0. By the time you watch this video, there may be a newer version of TensorFlow, but everything that we do in this fundamentals notebook should still work perfectly fine. So look at that. We've already got TensorFlow ready to go. Now let's jump in and create our first tensor. Creating tensors with TF constant. Now you're going to see there's a few different ways to create tensors, but in general, you actually probably won't create many tensors yourself. This is because TensorFlow has many built-in modules, as we'll get familiar with throughout the course, such as tf.io and tf.data, which are able to read in your data sources, such as if you had a whole bunch of different images, and automatically convert them into tensors, as long as you write the code for that, that is. And then later on, our neural network models will process these tensors for us. But for now, we want to get familiar with tensors themselves, so let's start creating tensors. And what I've written here is the word scalar, which you might not be familiar with for now, but that's all right. We will learn what that is. Beautiful. So when we create a tensor with tf.constant, we get this. We return this. It says tf.tensor. It has a shape that's empty. The data type is int32. And in NumPy, this value is 7. So again, NumPy and TensorFlow are quite intertwined. Now, if we want to get the information or the doc string for what this function is, in Google Colab, you can press Command-Shift-Space. If you're on Windows, it may be Control-Shift-Space whilst you're in the function. And here we go. Creates a constant tensor from a tensor-like object. Or, if we just wanted to search, TensorFlow tf.constant. This is what I want you to get really familiar with, is just searching up something like this. And then going into the documentation, tf.constant, yes, creates a tensor, a constant tensor from a tensor-like object. All right. And then we go here, example use cases. So oftentimes, if I'm not familiar with something in TensorFlow, I'll just search it up like this. I'll find the example code here, and then I'll just rewrite that code in the notebook. But let's keep going. Let's keep writing. All right. How about we check the number of dimensions of a tensor? This is another important concept that we're going to get familiar with as we go along. So ndim stands for number of dimensions. You might be wondering, Daniel, what's ndim? So we've got scalar ndim.ndim. Number of dimensions. So 0. Number of dimensions. What does that mean? Well, let's keep going. We'll come back to that in a second. How about we create a vector? So we've got a weird word here you might not be familiar with, scalar. Now, another word you're going to come across quite often in the deep learning world is vector. So let's see what they are. Again, this is the structure of what I want to go through, is write the code first and then go through the concept, or concept code, concept code, concept code. Vector. Let's see how these two differ. We have scalar, which is a TF tensor, has shape, which is blank, dtype int32, NumPy 7. Okay. Now we created a vector, and now we passed it a Python list to TF constant, which has TF tensor shape equals 2, maybe that's because there's two items or two objects within this list. The data type is int32, and the NumPy array version is 1010, so the same as this, and the D type is int32 for the NumPy array version. Okay. All right. Now, what about if we check the dimension of our vector? So we go vector.ndim. What do you think it'll be? 1. Okay. So is that because this shape is empty, maybe 0 came from that, and this shape has 1 element, so maybe that dimension came from that? Well, let's keep going. Create a matrix. So a matrix has more than 1 dimension. Again, if these terms are unfamiliar for now, we're going to get very familiar as we go along. So a matrix, we want to go 10, 7, and then 7, 10. Two of my favorite numbers. If you ever played poker, my favorite hand is 10, 7. Matrix. Let's see what this is. Okay. TF tensor shape equals 2, 2. Does that make sense? 2 items here, comma, 2 items here. Okay, yep, that makes sense. D type is int32, so these are integers. And then the NumPy version is just the same thing here with a data type of int32. Wonderful. Now, before I write the code, I want you to have a think. If we write matrix.ndim, if the vector had a dimension or number of dimensions as 1, and if a scalar had number of dimensions as 0, what do you think the matrix will be? 3, 2, 1. Boom. 2. Okay. So I'm starting to see the number of elements in shape is starting to relate. That's where I'm drawing my own pattern between ndim. All right. Now, let's create another matrix, but this time we're going to try out. How about we try and specify the data type? So if we go here, D type, that's what we want to try and use. So let's try and do that. Create another matrix. Now, another matrix equals, how can we do this? TF constant. What do we want to put in? What are your favorite numbers? I'm going to do my favorite numbers again. 10.7. Oh, you might have noticed something different about this one already. Is that we have a dot after our number. And if you're writing in Python code, what does a dot typically mean after an integer? And 8 and 9. That'll be nice and simple. And then what did we say we were going to do? We're going to use the dtype parameter, float 16. So we're going to specify the data type with dtype parameter. Now the reason I'm getting you familiar with the dtype parameter is because by default, if we create a tensor with tf.constant, we get the data type int32. So this is known as 32-bit precision. So if we go here, 32-bit precision, which is we're not going to dive too deep into that. The concept is the higher the number of precision, the more exact these numbers are stored on your computer. So if we do float 16, it's a lower number than 32. So that means storing these numbers or storing this tensor on our computer's memory is going to take up less space. The reason I'm getting you familiar with this is because if you get a data type error in the future of your tensors being the wrong data type, you can manipulate them using the dtype parameter. So let's have a look here. Another matrix. What does this come up as? There we go. Boom. TF tensor. The shape is 3 by 2. Oh, okay. So this is rows, columns. So we have 3 rows. 1, 2, 3. And because we've specified the data type as float16, we get dtype equals float16, which makes sense. And our integers here have a dot after, so they're actually floats. And then the same goes for our NumPy version of our tensor matrix. So what do you think the number of dimensions is of another matrix? So if we come back up here, what was our number of dimensions of our matrix here? And our vector and our scalar. We've just created another matrix. If we were to go another matrix dot ndim, what do you think the output would be based on the shape here? Let's find out. Boom, it's still 2. So even though the shape here is different, the total number of dimensions, which is the element, I'm really starting to notice a pattern here. The total number of dimensions is how many elements is in the shape. Okay, I've got that down. Why don't we see, how might we increase this number of dimensions? I know how we can do it. Let's create a tensor. So typically with this nomenclature, a scalar will have no dimensions, a vector will have 1 dimension, a matrix will have 2 dimensions, and a tensor will have, we'll see what that has. Let's go tensor. Can't reveal all my tricks before we try and code them out. Remember, if in doubt, code it out. Now, to create these, you're going to have to get pretty fancy with where you put your commas. So while I'm creating this, if you're finding that you're like, Daniel, I can't really follow along, that's okay. Just wait till I'm finished here, watch what I'm doing, and then you can pause the video, replicate what I've got, and then we'll run it together, all right? Boom. And then this one has to have 2. Now you see how tedious it is creating tensors from, like, with your hands? I mean, this is why it's so helpful for TensorFlow to create tensors for us, as we'll see in future modules. Hopefully, I've got all these little square brackets and commas in the right place. So if we look at our tensor, Shift and Enter, what's it going to output? Ooh, hello. We have how many more elements in the shape? We have an extra one. Okay, so there's 3. So 1, 2, 3, yes, 2. So 1, 2, and then 3 again. 1, 2, 3. Ah, beautiful. Now, if we wanted to check the number of dimensions of this tensor, what do you think it would be? I think you might know this one. Tensor.ndim. Boom, 3 dimensions. Wonderful. Now, the important thing to note is that although we've given these different names, tensor, matrix, vector, scalar, is that all of these in TensorFlow, throughout the entire course, we're basically going to continually refer to these, no matter if they're a 3-dimensional tensor or if they're a 2-dimensional tensor, which is a matrix, we're going to consistently refer to them as tensors. So if you're getting confused when I say matrix or tensor, chances are it's the same thing throughout this course. And so, how about we write down some little definitions? What we've created so far. Nice and simple. So scalar. A scalar is a single number. A vector is a number with direction. So e.g. wind speed and direction. A matrix is a 2-dimensional array of numbers. Wonderful. And a tensor is an n-dimensional. Now, when you see n, so the n here for n dimensions stands for number. Whenever you see n, it's often referred to as number of something. So n-dimensional means it could be 0-dimensional, or it could be up to 1,000 different dimensions or more. Array of numbers. where n can be any number, a 0 dimension, as we said before, dimensional tensor is a scalar, and a 1-dimensional tensor is a vector. Beautiful. So that's what we've created so far. We've created our first 5. Have we created 5? 5 different tensors. Now, in the next video, we've created them with TF constant. Let's have a look at another way of how we can create tensors, this time with TF.variable. I'll see you then. So we've created some of our very first tensors, which is so exciting, using TF constant. Let's look at how we might do it with our TF variable. So, again, little tip here, if you want to create a new cell in Colab, you can press code or text. But most of the time I just do the shortcut, so escape, command MB. Boom. But I'm going to put a text cell here, and then I'm going to put a little heading here, creating tensors with, and then if we go backtick, TF variable. Wonderful. So let's see what type TF variable is here. We could jump straight into it, but we want to have some practice looking up the documentation. So TensorFlow TF variable. Now the first probably, I reckon at least 100 times you read something in the documentation, especially if you're new to TensorFlow, it probably won't make too much sense. But once you've had a fair bit of hands-on practice, you'll start to get used to it. So TF variable, look how many different parameters we have here, far out. Traditionally, like in practice, I don't really read all of these. I go down and I like to see things being used. So here we go, TF variable 1 dot, so that should be a float, yes, v a sign. What's that? Well, we could keep going through that, but let's get hands-on. Again, if you want more about something from TensorFlow, look it up in the documentation, come through these code examples, write them out for yourself, and just check what the inputs and outputs are of the code that you're writing. So let's go back, tf.variable. How might we create the same tensor with TF variable as above? This is going to be, as you might have guessed by the name, a changeable tensor. What's that? TF variable 10,7. So remember up here, we created a vector of 10,10. Oh, I said 10,10, 10,7. There we go. That's what we want. 10,7. Now we're doing it here. And let's have a look at this one. Unchangeable tensor. TF constant. And then we want 10,7. Wonderful. We're going to write these out. We're going to visualize them. Unchangeable tensor. Did I type out the variable names correctly? Yes, I did. Wonderful. Okay, now we get some different outputs. So the first one here is our changeable tensor that we created with TF variable. So TF variable, wonderful, shape, okay, 2, dtype. In 32, we've seen that before, NumPy, okay. Now this is tf.tensor, which is the unchangeable tensor that we created with TF constant. You see these are output in order here, so this one first, and then this one, which is exactly what we've seen above before. Shape 2, dtype equals int32, NumPy array is of that. Wonderful. What do you think might happen if we tried to change one of the elements in our changeable tensor? It's all right if you're not sure, but let's try change one of the elements in our changeable tensor. So changeable tensor 0, or let's try the index at first. What comes up is NumPy 10. So we've got the first value here, so the 0 index. So what if we wanted to set that? We want to make a tensor which is 7, 7. So we want to set that first number, 10, to be 7 also. What happens if we try to visualize it here? Okay, we get an error. Resource variable object does not support item assignment. Okay, what if we go back to this documentation? So TF variable, they've created one here, similar to how we've created ours, but they've only got one element, which is a scalar. Then they've used v.assign. All right, and then it's changed from 1 dot to 2 dots. So what if we tried that? So let's come back here. How about we try dot assign? All right. Changeable tensor and the 0th element dot assign, and then we want to change it to 7. Just 7. What do you think will come out here? Let's have a look. Ooh, wonderful. There we go. All right. So how about if we tried to change a value in our TF constant tensor or our unchangeable tensor? Now let's try change our unchangeable tensor. Let's just try to do the same change. Make it simple. Unchangeable tensor and 0th element. Well, first we'll index it as well, just to check. Same output here, NumPy 10. And what if we go equals 7? What happens there? Oh, object is not a support item assignment. Okay, so similar error to what we got up here. Oh, that's okay. We know the fix. We can just go assign 7. Oh, get that bracket back up on there. And then we'll check out the unchangeable tensor. Oh, another attribute error. TensorFlow Python framework ops eager tensor. Object has no attribute assign. So what do you think's going on here? We've got a changeable tensor, which is a TF variable, and an unchangeable tensor. Where our TF variable is changeable using the assign attribute, whereas our unchangeable tensor, which kind of makes sense if it's name, doesn't change even when we use the assign. You might be wondering, why can we change some tensors and why can't we change others? Well, it comes down to behind the scenes, when we're writing neural network code, we might want some tensors for their values to be changed, whereas we might want some tensors for their values not to be changed. So there's a variable tensor and there's a constant tensor. Now, again, we're going to reiterate the fact that a lot of the times you won't have to make the decision between using a variable tensor or a constant tensor. The decision will be made for you behind the scenes when TensorFlow creates tensors for your neural networks. But we're going to get very hands-on with that. And so speaking of TensorFlow creating tensors for our neural networks, let's have a look in the next video, which is going to be creating random tensors. Woohoo! That's exciting. I'll see you then. So we've seen how to make tensors with TF constant and TF variable. Let's see how we might create random tensors. So actually, I'll make that a size 3 heading. And I just want you to I'll point out something here that I've added to the last little section of code that we run. This is going to be a trend throughout the course, is that if there's like a little tidbit that you should be aware of, I'm going to use this key emoji and add a little note there. So rarely in practice will you need to decide whether to use TF constant or TF variable to create tensors, as TensorFlow does this for you. However, if in doubt, use TF constant and change it later if you need. So that's a little tidbit going forward. So if you ever see the key emoji with something coming after it throughout this entire course, throughout any of the notebooks that you use and the GitHub and whatnot, that's just a little tidbit to take note of for later. But let's get hands-on creating random tensors. So random tensors are tensors of some arbitrary size which contain random numbers. You might be wondering, why on earth would I ever want to create a tensor? Where's an example of one of our tensors? Like this, filled with random numbers. And I have a great illustration to show you. So let's go to our Keynote slide here. This is what neural networks use to initialize their weights, in other words, the patterns, that they're trying to learn in our data. So if we imagine this diagram here, we have our inputs. Say we had pictures of food that we're trying to classify into ramen or spaghetti. We might turn that into tensors. We'll see how to do this in a future project. So this is our numerical encoding of our images. Then we might pass that numerical encoding to the input layer of our neural network. Then our neural network might learn representations which are called patterns, features, or weights. then output those representation outputs, and then we convert them into something that we can understand rather than just tensors. But where does a neural network get these representations from? Well, in the beginning, it's going to initialize itself. Initialize is another common word you'll hear in deep learning. Initialize just means start with. Initialize its weights or the patterns it knows with random weights or random tensors. So this would be a random tensor to begin with. And then, as it sees different examples of photos of ramen and spaghetti, it's going to update its representation outputs. In other words, start to tweak these random weights and patterns to better suit our data. If we go through again, we're going to repeat this cycle with more and more examples. So if we imagine the float here, we've got images, we numerically encode them, our neural network initializes itself with random weights, in other words, a random tensor, and then as we start to show it more examples of what photos of ramen and spaghetti look like, it starts to tweak these random weights to be better adjusted to the patterns that are in our images so that our representation outputs line up better with our desired labeled outputs. So maybe in the beginning it gets these images, these two here, wrong, but then as it keeps going, it starts to learn them and it starts to get them right like these two here. So let's go back. That's a brief overview of how a neural network learns, but that's the context of where you might use a random tensor. So how might we create a random tensor? So let's create two random but the same tensors. Now, before we even write any code, we go how to create random tensors with TensorFlow. TensorFlow.random.uniform. Wonderful. So we could go through that, or we could start to write the code. Seriously, when I don't know something, that is the type of search that I will put into Google and look up. As much as I'm trying to teach you TensorFlow itself, I'm trying to teach you how to search for answers to solve your own problems. Because at the end of the day, I can only show you so much. But let's create random one, which is going to be tf.random.generator.fromSeed42. What is a seed? So the set seed for reproducibility. So we'll see what the random seed means in a minute. If you've ever used NumPy, it's very similar to NumPy's random seed. So random1 equals random1.normal. I want you to guess if we put in the shape parameter here. So if we come here, go to this first one, random uniform, shape. We've got random normal, shape 3,2. What shape will our tensor be if we were to press Shift and Enter? TF tensor, shape 3,2. Now, we've used normal here, but this is uniform. What's the difference? So output random values from a uniform distribution. What is a uniform distribution? Here we go. Wolfram.com. A uniform distribution, sometimes also known as a rectangular distribution, is a distribution that has constant probability. Whoa. So oftentimes when I read stuff like this, it takes me a long time to grasp it. If you're the same, I want you to realize that that's not necessarily a problem. It's because in practice, when you're writing these random tensors, again, a lot of it is done behind the scenes for you. What I want you to get familiar with is writing as much code as possible, like we've done here, and then starting to see what the outputs of that code is. The more and more you do it, the more familiar you will get with it. So let's create another one. Maybe we'll come up here, random2 equals tf random generator from seed 42, random2 equals random2.normal shape equals 3,2. You might be wondering, Daniel, you've just looked up uniform and you haven't done anything with it. So what is normal? Well, great question. So what is TensorFlow random normal. tf.random.normal. Outputs random values from a normal distribution. Okay, tf random normal shape. All right, what is a normal distribution? See how we're sort of just pulling the thread here? This is what I do with any problem that I'm working on. A function that represents the distribution of many random variables as a symmetric bell-shaped graph images. Okay, so that's the normal distribution. Again, you can look into this more if you want, but we're going to be practicing writing more random tensors. So, are they equal? Random 1, random 2, and now we'll use this equality operator to compare the two. Random 1 equals random 2. Are these equal? Let's have a look. What do you think? Are they going to be equal? Oh, yes we do. We have random 1, remember these come out in order, and then random 2. And so they've come from a normal distribution. This equality operator is this last one here, which is saying that the top left element is matching this top left element, true. The top right is matching here and here, so that comes out true. And then we get the same for the rest of the array. Beautiful. So I want you to know that the random tensors here, although these appear pretty random, these numbers, they're actually pseudo-random numbers. So they appear as random, but they really aren't. That's because we've set the seed here. Setting the seed says something along the lines of, hey, TensorFlow, create me some random numbers, but flavor them with x, where x is the seed. So what do you think would happen if we changed the random seed to my favorite number, which is 7? I have a dog called 7. She's beautiful. What do you think will happen here? We get some slightly different random outputs, but they're still the same between random 1 and random 2. Okay, we've seen how to briefly create some random tensors, and I mean, if we go how to create random tensors with TensorFlow, there's going to be a whole bunch of more different ways. But if we had our random tensors, or if we had just non-random tensors, what if we wanted to shuffle the order that the variables appear in here? Let's have a look at that in the next video. In the last video, we checked out how we can create some random tensors, and we tied that back to the concept of when a neural network starts to learn, if it wants to learn patterns in some sort of data set, it starts off with random patterns and then slowly adjusts them as it continually learns on more and more examples. So if we come back here, in this video, let's see how we might shuffle the order of, what should we call it, elements in a tensor. All right. Why would you want to shuffle the order of elements in a tensor? Let's go back to our example here. So let's say we were working on a food image classification problem, and we had 15,000 images of ramen and spaghetti. Let's keep it nice and simple. And the first 10,000 images were all of ramen. And the last 5,000 images in our folder, like they're in order, so the first 10,000 are all of ramen, and the last 5,000 are all of spaghetti. Now, this order could affect how our neural network learns. So if it goes through these images in order, it might start to adjust its random weights too much so to the images of ramen, because if it goes through 10,000 images of ramen, it's like, okay, well, I only have to learn what ramen looks like. It doesn't know that it has to also learn what spaghetti looks like until it goes to the last 5,000 images. So instead, it might be a good idea to just mix up all the images in our folder so that they basically have no order at all. So we might have ramen, 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 spaghetti, spaghetti, ramen, spaghetti, ramen, spaghetti, ramen. And then the neural network can be fed different examples of different images and adjust its internal patterns or weights, the random tensors it got initialized with, to learn both types of images at the same time. Let's go back to our Colab notebook and let's see how we might shuffle a tensor. So we go shuffle a tensor. So this is valuable for when you want to shuffle your data so the inherent order doesn't affect learning. Now, what we might do is create another tensor. We'll get some practice creating tensors here. Not shuffled equals TF constant. And then we might just create a very similar tensor to what we created above, 10, 7, my favorite combination of numbers, my favorite poker hand. And there we go. And 2, 5. Why not? There we go. So a little test here is if we did not shuffled dot ndim, what do you think that's going to output? Well, let's find out. 2. Okay. Why might that be? Not shuffled. Because it has a shape of 3, 2. So there's 2 elements in the shape attribute. Beautiful. So let's see how we'll shuffle this. Maybe if we just go how to shuffle a tensor in TensorFlow. tf.random.shuffle. Okay, beautiful. So randomly shuffles a tensor along its first dimension. tf random shuffle seed equals none, value. Okay, there's an example output. Let's try it out. So the value, what's value? This is how I read the documentation. So the arguments. So the value is a tensor to be shuffled. That's what we want. And the seed could be a Python integer used to create a random seed for the distribution. C random.setSeed for behavior. Okay, let's get hands-on with this. So shuffle our non-shuffled tensor. So let's go tf.random.shuffle. And then, oh, look at that. The doc string appears for us. If we wanted that on our own, we could press Command-Shift-Space. See, I'll come, In Colab, sometimes the doc string just automatically comes up if you're just chilling in here. But we can press Shift-Command-Space, or if you're on Windows, Shift-Control-Space. There we go. We just get the exact information from the TensorFlow documentation. How handy is that? So let's pass it. What does it take? Args, value, a tensor to be shuffled. Let's pass it in not shuffled. Okay. What do you think is going to happen here? Well, let's find out together. Boom. Okay, look at that order there. So if we get 10, 7, 3, 4, 2, 5, and now the order's changed up here. Okay, so there's still 2, 5, still 10, 7, still 3, 4. Okay, what it's done is if we come back up here, randomly shuffles a tensor along its first dimension. So if we look at not shuffled, it's got a dimension of 3 times 2, which is 1, 2, 3 elements. So it shuffled it along its first dimension, which means it shuffled it along this dimension here. So the 3, 1, 2, 3. So it means that the elements in the second dimension, which is 10, 7, 3, 4, 2, 5, have stayed in order, but they've been shuffled around. So 10, 7 was at the top, but now it's in the middle. 3, 4 was in the middle, but now it's at the bottom. And 2, 5 was at the bottom, but now it's at the top. Okay, now what if we were to run this cell again? I want you to take note. Actually, let's copy this. So copy that. And I'm going to add another code cell here. I'm going to run this cell here. Okay, 10, 7, 3, 4, 2, 5. Same as before, but what if we run it again? 10, 7, 2, 5, 3, 4. Okay, different order. Notice how every time I run it, it's a different order. And I mean, there's only 3 elements here, so sometimes you're going to get the same. Now, what if we were to put seed equals 42? Because if we come here, a Python integer, seed used to create random seed for the distribution. What happens if we do that? Seed equals 42. Seed equals 42. We get still different results. So what if we did tf.random.setSeed 42? Okay. 10, 7, 3, 4, 2, 5. 10, 7, 3, 4, 2, 5. 10, 7, 3, 4, 2, 5. Okay. 10, 7, 3, 4, 2, 5. Now we're getting the same order. That's quite confusing. So how might we figure this out? If we come back here, seed, we set that to 42, but we didn't get the same results. So seed, it says here, used to create a random seed for the distribution C, TF random seed for behavior. Okay, so let's click on that. Here we're kind of pulling the thread of what our problem is. We're trying to figure out how to set random seeds or random operations in TensorFlow. So operations that rely on a random seed actually derive it from two seeds, the global and operation level seeds. So I think this one might be the global level seed, and this one might be the operation level seed because it's a part of an operation here. That's my intuition. Now, its interaction with operation level seeds is as follows. Okay, so we've got 4 rules here. I'm not going to read these out, but what I want to do is put this here, and I want you to start exploring or start practicing. So this is your homework for this lesson, so this one can be here. If you see this symbol here, this means exercise. So exercise, we're going to go read through TensorFlow documentation on random seed generation and practice writing 5 random tensors and shuffle them. That's your takeaway for your homework for this lesson. It's all right. If you want to skip over that and just go straight to the next video, you can. But to really understand the concept of TensorFlow creating tensors, just go through and try create maybe 5 different tensors here with tensor with TF constant, then shuffle them, then try to get the reproducible shuffled order using TF random set seed and a combination of seed. And then figure out, just see what happens. If in doubt, run the code. You can't break it. So have a practice of that, and I'll see you in the next video. We'll see a few other ways to make tensors. In the last video, we went over the concept of shuffling the order of elements in our tensor. And we tried it out a few times, but we ran into some problems using the global random seed and the operation level random seed. But the main intuition behind shuffling the order of tensors is that if we were trying to build a food image classification neural network, and we had 15,000 images of food, 10,000 images of ramen, 5,000 images of spaghetti, and our neural network, all it saw was the ramen images first, the patterns that it learns may be too aligned with what's in a ramen image rather than a spaghetti image. So that's why we might want to shuffle the order of our images so that the patterns that our neural network learns are tuned to both kinds of images throughout the entire training cycle. So let's go back here. We also left off, last video was full on. We left off with an exercise to read through the TensorFlow documentation. Again, the first few times, or the first probably 100 times you read through the documentation, you might not fully understand it, but with a lot of practice, you'll start to get the concepts. And so what did you find? Did you try to create 5 random tensors and shuffle them? I'll tell you what I found. After reading these rules, number 4, I think, is what relates most to us. It says, if both the global and the operation seed are set, both seeds are used in conjunction to determine the random sequence. Okay, so if we come back here, if we set tf random dot shuffle, we try to shuffle so this is the operation level seed. So if we run that, okay, we get a different order each time. But then, if we set the global random seed, what do you think is going to happen? So we'll go here, global level random seed, operation level random seed. Do we get the same order every time? 10, 7, 3, 4, 2, 5. 10, 7, 3, 4, 2, 5. 10, 7, 3, 4, 2, 5. Beautiful. We could keep going, but we're just going to trust that this rule is correct. So here, we come here. Let's write down here. It looks like if we want our tensors, or maybe our shuffled tensors, that's a better way of saying it, our shuffled tensors to be in the same order, we've got to use the global level random seed as well as the operation level random seed. And then we'll put in here, if you want to put in a quote, you can do this little arrow thing here. Rule for, there we go. So again, now this might not make a lot of sense of why you want reproducible tensors, but as you start to run more deep learning experiments, you'll often find is that because a neural network initializes itself with random patterns, you could get different results every single time you run this experiment. So, to make reproducible experiments, you probably want to shuffle your data in a similar order, initialize with a similar random pattern, and then run through this experiment. But for now, just be aware that if you want to set the random seed, TensorFlow has a few rules that you have to adhere to in order to get reproducible randomness. Whoa, that's a bit of a tongue twister. So let's have a look at some other ways to make tensors. Other ways to make tensors. The first one is if you're familiar with NumPy, you can do NumPy 1s. What's this? NumPy 1s. Let's have a read. Return a new array of given shape and type filled with 1s. So for many NumPy operations, because NumPy is one of the most prevalent numerical computing libraries out there, TensorFlow has similar operations. So TensorFlow 1s creates a tensor with all elements set to 1. Okay, let's try that out. So TF1s, what happens here? Let's check the doc string. Can we do that? Yeah, there we go. TF1s, it looks like we have to pass it a shape and then a data type. So why don't we make it 10.7? What happens? Wonderful. Create a tensor of all 1s. And then we want to go maybe create a tensor of all 0s. Oh, how do you think we might do that? If we created a tensor of all 1s, how might we create a tensor of all 0s? I wanted you to try and guess this before we even bother looking it up. Let's go TF 0s. And then what shape should we pass this under? So this is in square brackets. Shape you can also pass in curly brackets here, or the curved brackets. How you'd create a tuple. 3, 4, put a space there. Wonderful. Okay, so if we wanted to create a tensor of all 1s and all 0s, we can do that using TF1s or TF0s, very similar to NumPy. And another thing, speaking of NumPy, we might as well cover that while we're here. You can also turn NumPy arrays into tensors. Whoa, into TensorFlow tensors. So remember, the main difference between, well, actually, I don't think we've covered this, but actually, let's put this here. We want text, so I'm going to push Command-M. We'll go here, turn NumPy arrays into tensors. And the main difference between NumPy and TensorFlow, this should be NumPy arrays, is that tensors can be run on a GPU much faster for numerical computing. Otherwise, they're very similar. So let's try this out. We want to import NumPy as NP, and then we want to create NumPy A. This capitalization, often you'll see a matrix created with a capital, constant sum matrix, and then often you'll see a vector with a non-capital. So that's a little tidbit there too. So we'll put that there. And then we'll go little capital for matrix or tensor, non-capital for vector. So we want to make just a simple NumPy array. Range, dtype is going to be int. Actually, we'll make it int32. So this is going to create, you might be able to guess, so NumPy A range between 1 and 25. So create a NumPy array between 1 and 25. Let's have a look at that. NumPy A. Now, how do you think you might turn this into a tensor? So if we come back to our TF constant documentation, creates a constant tensor from a tensor-like object, value. Okay, what's value? Where's the doc string for that? Value. A constant value or list of output type dtype. It doesn't really give us much, but let's try. If in doubt, code it out. A equals TF constant. Do you think we can just pass our NumPy A, this one here, directly to TF constant? I mean, what do you think is going to happen if we do this? Oh, wonderful. There we go. We've now just converted our NumPy array. So if we have a look here, the output here is an array that's of type NumPy. And then if we go here, we've just passed it to TF constant. Now it's into the form of a tensor. How beautiful is that? So anything we've got in NumPy, we can convert to a tensor by just passing it to something like TF constant. Now, what if we wanted to change the shape of this? So this is a shape 24. How about if we wanted to make it into a 3-dimensional tensor? Yeah, that sounds fun. So let's change it into 2, 3, 4. Is that the right? 2 times 3 times 4. Now, why do you think I checked that? We'll see in a second. Hey, look at that. Maybe we'll make this b equals TF constant NumPy A. And then we'll go A, B. Ooh, so there's a change shape one. Our first one, A. We've got the shape modifier there. So this is 1, 2. So 2 is the first dimension. And then 3, 1, 2, 3. And then 4, 1, 2, 3, 4. Wonderful. But the unmodified shape is just the same shape as our original NumPy array, which is just 24. So this is a vector, and this would be a tensor because it's got more than one dimension. Now, the important thing to know about shape is that if you want to readjust the shape of a tensor or an array, the new elements here must add up to give the same number of elements in the original tensor. So what if we tried here? What's going to happen? It doesn't work. Eager execution of TF constants with unsupported shape. Value has 24 elements. Shape is 2, 3, 5 with 30 elements. So if we go here, that doesn't work. We go there. Wonderful. We need it to equal 24. So what about 3 times 8? Let's try that. 3 times 8. We're kind of getting a little bit ahead of ourselves here with this reshape. Oh, look at that. Beautiful. So 3 times 8 equals 24, so that works. So this is 1, 2, 3 rows, and then 1, 2, 3, 4, 5, 6, 7, 8. 8 elements per row. Beautiful. Okay, so we've seen how we can turn NumPy arrays into tensors, and we've seen how to create tensors with all ones and all zeros. It's probably time that we get a little bit more information from our tensors. So let's make that in our next video. So getting information from tensors. All right, so have a play around, create some NumPy arrays, turn them into TensorFlow tensors, and then try to adjust their shape so they fit into a different size. And then you could even check the number of dimensions of A. But otherwise, give that a go, and I'll see you in the next video. We'll see how we can get more information from our tensors. We finished up the last video checking out how NumPy arrays, which are a very common form of representing numerical data, can be used or actually also converted into tensors. And the main difference being between a NumPy array and a TensorFlow tensor is that although they may store the same information here, so this array here, NumPy A, has the numbers 1 to 24, and this tensor here, B, has the numbers 1 to 24, is that because this one's in a tensor format, it can run on a GPU, which we'll see later on in the course is a lot faster than a non-GPU chip. at finding patterns in numerical data, that is. Let's have a look at how we'll get a bit more information from our tensors. But before we do that, I just want to show you a little tidbit. So I took a break after this lecture and came back to my notebook. And what happened was the runtime disconnected. Now you can't see it here, but we've got a green tick saying we're connected. But when you disconnect in Colab, you might find that, it's still there. But if the memory has gone, so for example, if we did A and it told us that A didn't exist, what I like to use is go to runtime and then run before. What this is going to do is run every cell before the current cell, meaning if we've instantiated some variables such as NumPy A, those variables are going to get reinstantiated and TensorFlow is going to get re-imported, etc. We don't necessarily need to do it now because, or in my case, because it seems that Colab has remembered my variables. But if you do come into that case, go runtime, run before, and as you'll see, all the cells here are going to run. Now they run pretty quickly. We get the same error we got before, but then we can just go Shift Enter, run, keep running down to where we were. And then all of the variables we've been working with will be reinstantiated. Wonderful. So with that being said, let's get back to our getting information from tensors. There will be times where you want to get different attributes of your tensors. Let's have a look. Let's have the following vocabulary at least. So we want shape. These are the most important tensor terms. Axis or dimension. And then you'll also want the size. So if we come here to our Keynote, we'll have a look at how to do those in code in a minute. But if we go on to the next slide, these are some of the main tensor attributes here. So we've got shape, axis or dimension, and then size. And the meaning here, the shape is the length or the number of elements of each dimension of a tensor. And we can get that by going tensor.shape. The rank, the number of tensor dimensions. For example, a scalar has rank 0 or 0 dimensions. A vector has rank 1 or 1 dimension. And a tensor has rank n or n dimensions, where n can be almost any number, 0 and above. And then we can get that by going tensor.ndim. We've seen that a few times. Axis or dimension. So this is how you access a particular dimension of a tensor. For example, if we wanted to index on the first dimension, tensors are 0 index, so the first dimension is actually 0, 1, etc. And then if we wanted to get all of the elements in the 0th dimension and then the 1 axis, we can use some indexing like this. We'll see this in a minute. And then if we wanted the size attribute, the size is the total number of items or elements in a tensor. And we can access that by using tf.size. So let's go back. When dealing with tensors, you probably want to be aware of the following attributes. Boom. Shape, axis, rank, size. I said that out of order, but that doesn't really matter. So probably the most important one here will be shape, but we'll see that again in practice. Let's create a tensor. Create a rank 4 tensor. Now, if I say rank 4 tensor, if we come back here, what does that mean? Rank. The number of tensor dimensions. So what might that look like? We want 4 dimensions. We come in here, we want rank 4 tensor equals tf.zeros. What does tf.zeros do? This is a little test from before. We just covered this one. 2, 3, 4, 5. So remember, this is probably the shape parameter here. So rank 4, we've got 1, 2, 3, 4 dimensions here. Now let's have a look at this rank 4 tensor. Beautiful. Now this is all zeros. So if we see here, this is 1. So this is the first axis. This is 1, 2. Then the next one is 3. So we've got within the 1 and 2, we've got 1, 2, 3. Now this will take some getting used to. The only reason I'm able to sort of deduce which is which of these elements here is because I've had a lot of practice writing different tensors. Now if we look at 4, within the 3, so 1, 2, 3, we've got 1, 2, 3, 4. And now we've got 5. So within the 4, 1, 2, 3, 4, we've got 1, 2, 3, 4, 5. Now, as we'll see later on, I know I keep saying later on, we're getting the fundamentals down pat here, is you'll probably spend most of your time dealing with lining your shapes of your tensors up. When you pass a tensor into a neural network, it typically has to be in a certain shape, and then the output tensor that comes out of a neural network, so in other words, the patterns a neural network has learned, the tensor again has to be in a certain shape. So it's good to be able to deduce different elements of a tensor by its shape. So if we wanted rank 4 tensor, let's get its 0th element. What does that look like? Which is this 3 tensor here. So see how we've indexed onto this second shape here? Now the shape changes because we're getting this set of 3 here, this set of 3 tensors. And so the shape here is 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. Again, it'll take quite a bit of practice to get used to that, but that's just a brief overview. Now, what we might do is get all of the shape, the rank, axis or dimension, and the size of our tensor. So we just saw the 0th axis. Let's go rank for tensor dot shape. You might be able to guess what this is already. Rank for tensor dot ndim, so the number of dimensions. And then let's get the size of our tensor. Before I even type any of these, you might be able to deduce what they actually are already. So what's the shape? Probably going to be similar to what we set the shape as. The ndim, remember that's the number of dimensions in our tensor. And the size is what, if we come back to our Keynote? The size is the total number of items in the tensor. Out of all of these, I think size will probably be the one you use least often, but I'm just putting it here for completeness. So if we go there, boom. So we look, these come in order again. So the shape is 2, 3, 4, 5, yep. The number of dimensions is 4, that makes sense because it's 1, 2, 3, 4, beautiful. And then the size is there's 120 elements. Now, what might that be? I'll give you a hint. 2 times 3 times 4 times 5, what do you think this is going to equal? 120. Beautiful. Okay, how about we print out some various attributes of our tensor, make them a bit more readable. So I want to show you, get various attributes of our tensor. This is what I often do to sort of create I call this pretty print statements. I mean, there is a function called pretty print, but when I'm trying to figure out or visualize my tensor data, I typically set up a bunch of print statements like this, especially when I'm inspecting the outputs of a neural network. So print, so I want to get the data type of every element. Boom, that's what I want. And then I want to get the number of dimensions, which can be the rank. And again, typing this stuff out is tedious when you first do it, but it does help visualize. I mean, we could put this into a function if we wanted to later on. Print, and now how about the shape of our tensor? That's going to be rank for tensor.shape. I'm not sure why that disappeared. Beautiful. And then now, how many elements are along the 0th axis? So elements along the 0 axis. Oh, axis doesn't have that. And we want to go rank for tensor 0 dot shape. Oh no, maybe we want shape 0. That's what we want. And then how about we want elements along the last axis. So I want rank for tensor shape. Now -1 we can use for the last axis. So instead of we have 1, 2, 3, 4 here, we could have used 3 because it's the 4th index, but we're going to use -1 just to grab the last index. That's a little trick for Python indexing. And then we want to go the total number of elements in our tensor, which will be tf size rank for, is this going to autocomplete? Rank for tensor. Well, that should be ready to go. Let's have a look. What do we get? Okay, data type of every element. D type is a float. So, okay, that makes sense because we've got 0 dot, yeah. Number of dimensions, rank 4. Yes, that makes sense. 1, 2, 3, 4. Shape of tensor. Yes, we've seen that before. Elements along 0 axis. So 2 elements there. Yeah, beautiful. Elements along the last axis. 5. That's correct. Wonderful. And the total number of elements in our tensor is TF tensor 120. Oh, NumPy 120. Now that output can be a little confusing, so I want to show you just a trick to convert it into a NumPy integer. So you can just go here. With the tensor output, for a lot of them, you can just add .numpy on the end, and we'll watch the conversion here. So this is there, or actually we might do it with and without, just so you can see the difference. I'm just going to copy that line. Boom. There we go. So the total number of elements in our tensor, that's it coming out as a TF tensor type. But if we add the NumPy on the end, we get it in this single element, which can be handy if you didn't want to have the TF tensor type. You just want the element itself. Try using .numpy at the end there. All right, wonderful. Since we now know a fair few pieces of information on how to get them from our tensors, we'll practice. One very important thing is being able to index on tensors. So we'll do a little bit of practice of that in the next video. So I'll see you then. So in the last video, we checked out how we can get various attributes from any tensor that we can create, such as the data type, the number of dimensions, the shape, and then various other attributes of it, which can be helpful when we're trying to figure out just what's going on with our tensors. Because, I mean, although we can see this one, oftentimes with neural networks, you'll be dealing with tensors that you can't actually visualize, meaning that they're so big that you won't be able to just look at them. So you need to be able to use code to find different information or different attributes about them. So now let's have a look. Say we did have a tensor like this, and we want to index it. So the beautiful thing about tensors is that, oh, we don't want that. I just want to turn that into text. So we'll go here, indexing tensors. So tensors can be indexed just like Python lists. So if you've ever done indexing on Python lists, we'll see how it relates here. But if not, that's okay, because we're just going to get hands-on as we do. That's the theme of this course. So get the first 2 elements of each dimension in our tensor. So if you have had experience with indexing Python lists, how do you think you might get the first 2 elements of each dimension of our rank 4 tensor? So remember, we've got 1, 2, 3, 4 dimensions here, and we want the first 2 elements. In our case, it's going to be 0 for every single one of them, but we want the first 2 elements of each dimension. So give that a try. If not, I'm going to start writing the code to do it, and we're going to have a look at it in a few seconds. So this is how I would get, or how you would index a tensor to get the first 2 elements of each dimension. There we go. So just like a Python list. So if we make here sum list equals 1, 2, 3, 4, and we want the first 2 elements of sum list, we go here. Use a colon, we'll get 1, 2. Beautiful. So now we can do the same, but with our tensor, we just have multiple dimensions. We separate them by column. So let's have a look at what the output of this is. Wonderful. Because our tensor is all zeros, we get 2, 2, 2, 2, and each value is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. But can you see the shape here? This is the first, the outer tensor. This is the second one on the 0th dimension. And then we have 2 here, 1, 2. And then we have 2 within these brackets, so 1, 2. And then the final 2, the elements within the most inner brackets, so 0, 0. Again, takes a lot of practice, but just look at these diagrams and start to count the tensors yourself of tensors that you can visualize. As a warning, if the tensors are too large, it'll probably separate them with 3 dots, but we'll get to that in a bit. How about if we wanted to get the dimension, or get each dimension from each index except for the final one? Now, does that make sense? So we want get each dimension from each index except for the final one. Oh, sorry, that doesn't make sense. Get the first element from each dimension, from each index except for the final one. Okay, how might we do that? Actually, let's try it with our sum list. If we wanted the first element, 1. Beautiful. Now, we want the first element from every dimension except for the final one. So let's try that. Rank 4 tensor, and we want First element from each dimension, except for the last one. Will that work? We don't have the last one there. Let's try. Wonderful. 1, 1, 1, 5. Beautiful. So that means all of our tensors kind of get flattened. All the other shapes get flattened into 1, but we've still got 5. Beautiful. We can get the same thing if we add this colon here. So this colon, if it's there without a number, it just means get the whole thing. So there we go, same output as before, 1, 1, 1, 5 for the last dimension. Now if we wanted to change this up, say we wanted except for the second last one, what do you think this is going to output? If we go here, rank 4 tensor, if we want to get the second last axis, and we go shape. So we're getting the first element from each dimension of our tensor except for the second last one. So what shape is this going to output if we run this line? Let's try. Wonderful. So there we go. 1, 1, 4, 1. Again, plenty of practice, but that's how we're going to learn things. So there we go. 1, 3, 1, 1. Then we could do the same here with the 0th axis. Beautiful. Okay, we'll convert that back so that comment there makes sense. Now, what else might we want to do? If we've got our tensor of this shape, sometimes what we might want to do is expand or reshape. So in this case, we've seen a little bit before on how to reshape a tensor, but let's practice changing or adding an extra dimension to the end of a tensor. So how about we create a rank 2 tensor, which has how many dimensions? 2 dimensions. So we can do that by rank 2 tensor. You can pause the video here if you want and try to create your own rank 2 tensor without me coding. But we want TF constant, my favorite numbers, 10, 7. And then how about 3, 4, because 3 and 4 add to 7. And now let's have a look at our tensor. Rank 2 tensor. We could even get some attributes about it. Rank 2 tensor, ndim. Again, lots of practice here, figuring out information about our tensors. Okay, the shape 2, yep, ndim, that's exactly what we want. Now, if we wanted to get the last item of each row of our rank 2 tensor, how might we do that? So again, let's remind ourselves what it looks like. Rank 2 tensor. Let's remind ourselves what our Python list looks like, sum list. How do we get the last element of a list? Sum list -1. So there we go. So if we want to get the last item of each row of our rank 2 tensor, well, the row comes first, so row, column. So we might go, rank 2 tensor, so the last item, -1. Does that make sense? Let's see. Does that get it? So 7, 4. Beautiful. That's what we want. If we wanted to add an extra dimension onto this shape here, so maybe we have 2, 2, 1, we can do so in 2 ways. And now this is helpful for later on when we're creating neural networks and we need to alter the size of our tensors so that their shapes line up. So it might not seem like it's very helpful now, but I just want to sort of plant the seed so that when we come across it in future videos, it's not like, whoa, Daniel, we haven't covered this method before. So let's go in here, add in extra dimension to our rank 2 tensor. So we want to turn our rank 2 tensor into a rank 3 tensor, but keeping the exact same information that is stored in our rank 2 tensor. So we're not going to change these numbers. We're just going to change the shape that the numbers fit into. And we can do that by going here, ... Now this is a little bit of fancy notation. You might not have seen this before. We can go tf.new axis. Let's see what this does. Oh, we need to visualize our tensor, don't we? Beautiful. So you see what that did there? That's now added a dimension on the end of 1. So let's look this up, tf.new axis. tf tensor. If we search, again, I'm just pressing Command F, you might press Control F, tf.new axis. There we go. So 1 of 8, it appears 8 times. So insert another dimension. Does it have the actual definition here? Notes TF new access is none, as in NumPy. So if you're using NumPy, you probably use none. In TensorFlow, it's tf.newAccess. It doesn't actually say what it does. Sometimes where you'll find the documentation, it can be quite hard to sometimes find the exact definition of this method, but you can kind of deduce what it does by running through the examples as we see here. So let's go in there. It's better off just to remember, if in doubt, write the code, try it out. So the other alternative to using this, oh, by the way, these 3 dots means on every previous access to this one. So this means instead of just going like this, so see how we've got access 0, access 1, access 2 in this case, add an access on the very end. We can just scrap these and go every access before the last one, include those because that's ... and add a new access on the end. So the other alternative to tf.newAccess is alternative to tf.newAccess. You might also see tf.expandDims. So that stands for expand dimensions. And then we're going to pass it rank 2 tensor. And then we want to expand it on the final axis. So -1 means expand the final axis. There we go. We get the exact same output as this notation here. It's just slightly different. So if we want to go here, tf.expandDims. There we go. We got some documentation for this one. So we have the input. We come down. It says, what is the input? The input is a tensor, and the axis is integer, specifying the dimension index at which to expand the shape of input, giving an input of d dimensions. So if we come back here, what do you think will happen if we go axis equals 0? So look at our shape there. What I might do is keep that there. We're going to retype this out. tf expand dims rank 2 tensor. We want as much practice as writing TensorFlow code as possible, right? So expand the 0 axis. So let's try that. Boom. So now, instead of being on the end, our extra dimension is at the front, and then we can even change it. We want the extra dimension in the middle. Wonderful. And then if we want to put it on the end, we can go -1. Beautiful. So we might put that there. Expand the 0 axis. And so notice, even if we run this and we check out rank 2 tensor, the numbers inside stay the same, 10, 7, 3, 4, except the dimensions change. So how those numbers are stored changes. We've covered a fair bit in terms of getting information from our tensors and also indexing our tensors. Now let's have a look at how we might. We've actually done a little bit of manipulation here too, but the next videos we might go through manipulating tensors. In other words, known as tensor operations. So if we do have elements within our tensors, how do we manipulate those and how do we combine them into different ways? So go back through, practice expanding the dimensions of tensors, practice getting different attributes from tensors that you've created. And then in the next video, we'll see what kind of tensor operations we can work with. If your data is stored in some sort of tensor format, finding patterns in those tensor formats often involves manipulating tensors. Now, again, when building models in TensorFlow, much of the pattern discovery within tensors is done for you. However, oftentimes that pattern discovery is through the extended use of a few basic operations. So let's start getting into those, otherwise known as tensor operations. We'll start off with basic operations. Now, do we have a tensor? So you can add values to a tensor using the addition operator. And by the way, when I say basic operations, I'm talking about the default Python operator, such as plus, minus, multiplication, and then if we want divide, we can go like that. Right, so we can add values to a tensor using the addition operator. So let's create a tensor equals tf constant, and we might make it 10, 7, my favorite, and 3, 4. And now if we go here, plus 10, what do you think will happen? So this is our tensor here. And if we just use the basic operation of tensor plus 10, wonderful. We get 10 plus 10 is 20, 7 plus 10 is 17, 3 plus 10 is 13, and 4 plus 10 is 14. Wonderful. Now you'll notice that the original tensor is unchanged. This is important because when we're manipulating tensors, we don't necessarily always want to change the underlying tensor. The only way it'll change is if we go tensor equals tensor plus 10. We'll reset it. Now this is going to be plus 20, isn't it? There we go. We'll come back here. There we go, tensor. But if we got rid of this, tensor, we rerun this cell. Oh, invalid syntax. And then we rerun this one. We still get the same values as what our original tensor was. And we might just press enter there so it's more succinct with how it comes out. Beautiful. So, of course, other operations also work. So multiplication also works. So if we wanted to go tensor times 10, same thing. We get 100 because 10 times 10, 100, 70, 30, 40, etc. And then subtraction if you want. So tensor minus 10 can go into the negatives. That's no problem. Tensors can store a whole range of different values. In addition to the operators, like the Python operators, we can also use an equivalent TensorFlow function. Now, what this means is that if we do use the TensorFlow function, so that means we're accessing the TensorFlow library. Let me just show you, because it's easier to talk about something if we can see it. We can use the TensorFlow built-in function too. So tf.multiply, and we want, see here, we get the doc string here. We get tf.mat.multiply, so we'll have a look at that in a moment, but I just want to demonstrate it to you. Tensor 10. We get the same output here. So if we go here, let's look up tf.math.multiply. So for a lot of these tf.math functions, so tf.math, we can do the alias of just tf multiply. So if we go tf multiply, it's just going to lead us to the same thing. Wonderful. Now, does it say here what the benefits are? It doesn't quite. But what I'm going to get you to do is just trust me here when I say that if you have to do some sort of tensor operation like this, and again, usually a lot of these will be done behind the scenes for you. But if you want your code to be sped up on a GPU, typically it gets sped up when you use the TensorFlow version of some sort of operator. So if we wanted to do addition, I mean, this is going to be very fast because it's only a small tensor. And we could do tensor plus 10. But if you want to have the advantages of TensorFlow built into your basic operations, use the TF math something tensor to manipulate your tensors. But here, again, even though we've used the TensorFlow function here, the original tensor is still unchanged. So these are the basic operators. Create some tensors, have some practice at running the addition, minus, multiplication, and division on them, and also do the equivalence of tf.multiply or tf.addition or something like that. Is it tf.addition? tf math addition? Or is it just add? Yeah, add. Okay. That's your little homework for this brief video here. But in the next one, we're going to have a look at a very important concept in neural networks, and that is matrix multiplication. We'll see how to do that with tensors. So we left off in the last video figuring out how we can manipulate our tensors with the basic operations. And so hopefully you've tried out a few of these for yourself. But now we're going to go on to matrix multiplication. So in machine learning, matrix multiplication is one of the most common tensor operations. So The ones we've been through already, these basic operations, are often referred to as element-wise operations. So that means that if we go here, for the addition, for example, we've got our tensor here, which is 10, 7, 3, 4. Now, element-wise means go through one element at a time and just add 10. So this element, add 10. This element, add 10. This element, add 10. This element, add 10. But there's a few different types. So matrix multiplication and the dot product are not necessarily element-wise. So if we go here, what is matrix multiplication? How to multiply matrices. Math is fun. I really like this domain name, actually. Let's have a look here. A matrix is an array of numbers. To multiply a matrix by a single number is easy. So 2 times 4 equals 8. Yes, that's what we've done, right? So that's element-wise. So 2 times 0 equals 0, 2 times 1 equals 2, 2 times negative 9 equals negative 18. Beautiful. However, what if we wanted to multiply a matrix by another matrix? And remember, because we're using TensorFlow, even though this is a matrix, we're referring to them as tensors as well. So I want you to read this as matrix and tensor interchangeable. But to multiply a matrix by another matrix, we need to do the dot product of rows and columns. What does that mean? Let's see an example. So the dot product is the first row and the first column. Okay, so we've got a row here times this column equals 58. Okay. The dot product is where we multiply matching members, then sum them up. So 1, 2, 3 times 7, 9, 11. Okay, 1, 2, 3 times 7, 9, 11, yes. Equals 1 times 7. Okay, yeah. 2 times 9. Yeah, 2 times 9. 3 times 11. Okay, I've got that. That equals 58. Then we do it again for the second column, and that's 64. And then again. A great website I like to visualize this is, I believe, matrix multiplication.xyz. We'll go to that. So here, beautiful. We can even customize these. So we'll go here, 1, 2, 7, my favorite number, 7, 2, 1, just to be fancy. And then maybe 3, 3, 3, because I like 3 as well. And then this can just stay the same. So might zoom in here. So let's go multiply. What happens? Whoa, we get some. So that tensor just came up there and jumped on top of that. And then if we go through, we go 1 times 2, 2 times 6, 7 times 1. Okay, so that's 2 plus 12 plus 7. How did this get to 21? 2 plus 12 plus 7. We might try a different set of numbers. How did that work? 5. Maybe our matrix multiplication demo is busted. Multiply. Let's try. 1 times 3 plus 12 plus 5. Does that make sense? So 3, 12 plus 5. Yeah, that makes sense. 15. So this is 3 plus 12 is 15 plus 5 is 20. There we go. And if we step through there, step through, wow, we get the output there. Before we even start to write code, go to this website, start practicing around, see what happens. And after you've done that for about a minute or so, or maybe 3 minutes, give yourself a few different goes. Let's go back to the notebook and see how we can do this exact operation in TensorFlow code. So I'll give yourself a second there, but I'm going to start coding so you can pause the video now if you want, try out that website and come back. So let's see matrix multiplication in TensorFlow. What if we just Google that, matrix multiplication in TensorFlow? matmul, there we go. tf.linalg, which is short for linear algebra, .matmul. Multiplies matrix A by matrix B, producing A times B. A, B. And we get a whole bunch of documentation, which is beautiful. We could read through that, or we could write the code ourselves. So, what do we have? Do we have a tensor? Print our tensor. We can print it if we want. Print, yes we do. Now tf matmul. Now for a lot of these operations, you can usually drop the intermediary here. So lin alg. This is a little trick of TensorFlow. You can just do tf.mapmul, which is what I'm about to do here. tf.mapmul, tensor, tensor. Can we matrix multiply those? Oh, yes, we can. Wonderful. We get 121, 98, 42, 37. Beautiful. Now, if you wanted to do the matrix multiplication, Python has an operator, A. Now, you see how the outputs here actually are different to if we just did, what if we did tensor times tensor? We get different outputs here. Okay. Because if we have a look at our tensor again, this is element-wise. So it's just gone 10. Maybe we'll print it out twice. 10 times 10 is 100. 7 times 7 is 49. 3 times 3 is 9. 4 times 4 is 16. Whereas with matmul, we've gone in this fancy little way here. So maybe, I've got an idea. We recreate this tensor. That could be a little exercise for you as well, is to recreate this tensor in TensorFlow and recreate this tensor in TensorFlow. So the same elements in the same shape. This would be a what? 1, 2, 3, a 3 by 3 tensor. And this would be a 1, 2, 3 by 2 tensor, so 3 by 2. And then run tf.mapmul on left tensor, right tensor. See if you get the same outputs as here. But we come back here. If you wanted to do matrix multiplication with a Python operator, we can do tensor at tensor. So the at symbol in Python actually is for matrix multiplication. Now, both of these examples work because our tensor variable, this is an important fact. This is where we come in and we check the shapes attribute. Because our tensor.shape attribute is 2 and 2. So both of them have the same shape of 2 and 2. But what if we wanted to do matrix multiplication on tensors which had differing shapes? Now, rather than just think about it, let's try. So create a tensor of maybe 3, 2. Similar to this one here. So this is 3, 2. Remember, rows come first. 1, 2, 3. Columns, 1, 2. Let's create a similar one. Create a 3, 2 tensor equals tf constant. And we want 1, 2. We'll keep this one nice and simple. 3, 4, 5, 6. Beautiful. And then we want create another 3, 2 tensor. And in this case, it can be y, tf, constant, and we'll just increase this one. So that can go from 7, 8, 9, 10, 11, 12. Wonderful. Let's have a look at both of those. X, y. Okay, so we've got two tensors here, both of the same shape, 3 by 2, and they got slightly differing elements. Now, what if we tried to matrix multiply them? So let's try to matrix multiply tensors of same shape. We could do it like that. See what happens. Oh, matrix size incompatible. In 3, 2, in 3, 2. What if we try the TF mapmul? What happens here? X, Y. Invalid. Matrix size incompatible. Same thing. 3, 2, in 0. So this is our first element here, our 0th element. And this is our other element here, our first element, which is also 3, 2. This is where we have two rules for matrix multiplication. Do these websites tell us? Why do we do it this way? Actually, this is a great example. I'm going to put this as an external resource if we come back. If you ever see this emoji in the course, this is a resource. So resource, info, and example of matrix multiplication. So check that out. If you ever see that little book emoji, that's an external resource that I definitely recommend. Now, let's go back to here. Why doesn't this work? I don't think this web page explicitly states it, but I'm going to tell you anyway. And you can look this up. You'll find this wherever you find matrix multiplication, is that there is a couple of rules that our tensors or matrices need to fulfill. So come up here. Let's put in here. There are two rules our tensors or matrices need to fulfill if we're going to matrix multiply them. Now, rule 1, the inner dimensions must match. And rule 2, the resulting matrix has the shape of the inner dimensions. So knowing these two rules, I'm going to set you a challenge. Is before the next video, we're going to go through these two rules and see how we can fix our problem here. But considering these two tensors, so we've got, if I say rule 1 is that the inner dimensions must match, what are the inner dimensions here? Maybe 2 and 3, they don't really match. So how would we get the inner dimensions of these two matrices to match? That's your challenge. If you're not sure, that's completely fine, but that's your challenge before the next video. If you can get it done, amazing work. If not, we're going to go through that in the next video. So I'll see you there. In the last video, we kind of left off on an error. And we said in this video that we're going to fix it. So let's do that. Now we tried to matrix multiply two tensors of the same shape, specifically x and y. They're both of the shape 3, 2. We got this little error here saying n0 is 3, 2 and n1 is 3, 2. So matrix size incompatible. So if we come up here, back to the rules we set ourselves, the inner dimensions must match. And the resulting matrix has the same shape of the inner dimensions. Now, if you had a go at fixing this and you got through it, excellent work. You may want to skip over this lecture. However, if you didn't make it, that's completely fine. Matrix multiplication takes a little while to get your head around. If we come over here, I've got a slide. Matrix multiplication is also known as the dot product. So when we call the code tf.matmul, and we have a matrix of some size here and a matrix of some size here, remember, a lot of the operations that we do can be on matrices or tensors of an arbitrary size, but just for illustration purposes, I've done this size here. So here's our first rule. So numbers on the inside must match. And there's our second rule. New size is the same as outside numbers. Okay. So if we come back, does that line up with what we've said here? The inner dimensions must match. The resulting matrix has the same shape of the inner dimensions. Oh no. Of the outer dimensions. There we go. Getting our own rules incorrect. So we come back. Let's have a look at what's going on here. We've got tf.matmul. We've got one matrix or tensor here, A, B, C, D, E, F, G, H, I, which is the shape of 3 by 3. Wonderful. And this will run because the numbers on the inside match. See these two 3s here with the red background? And this is of shape 3, 2. So 1, 2, 3, and 2 columns. Okay, so that matches. And then we're going to result in here. If we did the dot product, which is the same as matrix multiply in TensorFlow, we have A times J plus B times L plus C times N, and then we follow through with that rule for every single cell in these two, or every single element in these two tensors. And now the new size is 3 by 2. 1 row, 2 row, 3 row, 2 columns, which is the blue numbers here. Okay, wonderful. And then if we swap these elements from letters to actual numbers, so the same shapes here, we take 5 times 4. Okay, this is the same as A times J. Yes. 0 times 6. Okay, 0 times 6. Yes, which is the same as B times L. Wonderful. And then we have 3 times 8. Which is the same as C times N. All right. Now, again, looking at these diagrams, they're quite, for the first, I would say, 20, 30, 50 times you look at dot products and matrix multiplications, it takes a lot of repetition to get used to. But then if we have 5 times 4 equals 20, plus 0 times 6 equals 0, plus 3 times 8 equals 24, so we add these three up, we get 44 in the top left. Repeat the same for each element. and we get this resulting matrix here. Now, the live demo we've already had a look at. Matrix multiplication.xyz. This is what's happening here. If we reset and multiply, we take that, we flip it on the top, then we go here, we get 20, and we get the next two elements, and the next two, and the next one. So this is a moving diagram of what's going on here. So let's go back to our code. Let's fix it up. Let's make it work. So knowing our two rules, number one, that the inner dimensions must match, and that the resulting matrix is the same shape as the outer dimensions, how might we get this to work? Well, we're either going to have to change the shape of this matrix or change the shape of this matrix. Again, I'm using the term matrix and tensor interchangeably here. Or we're going to just have to create an entirely new tensor with the same shapes on the inner axes. So let's see it in action. Let's change the shape of y. So we can change a shape using tf.reshape y, and then we enter the shape that we'd like. In our case, it is currently 3, 2. So maybe we change it to 2, 3. And let's see what happens. Ooh, wonderful. Let's see the original y. Beautiful. So we can see that the 9 has come up to here in this one. And we've now got 10, 11, 12. So this has got 2 rows and 3 columns. Okay. So maybe we go try to multiply x by reshaped y. So x, and we might have to put matrix multiply here so we know what type of multiplication we're doing. X, tf, reshape y, and then shape 2, 3. Now you see what's happening here? So if we remind ourselves what shape x is shape 3, 2. Let's pay attention only to the shapes. tf.reshape y shape equals 2, 3 dot shape. Paying attention to our rule that the shapes of the inner dimensions, so this tensor multiplied by this tensor, the inner dimensions must match. Does that rule get fulfilled? To me it does, because we've got an inner dimension of 2 here and an inner dimension of 2 here. Let's test it out. Beautiful. It looks like that worked. So we come here, we want to make a new cell. What if we tried to use tf.matmul on this? So if we go tf.matmul x tf.reshape, and then we want y shape equals 2, 3. Is this going to work as well? Beautiful. Now we get the same outputs there. Now hold on. Now do you think if we were to reverse this, it would work as well? Now I mean we reshape x to be a different shape instead of reshaping y. If in doubt, code it out. So x tf reshape x, we're going to change that to be 2, 3 this time. And we're going to not change the shape of y. Let's see what happens. Ah, what happened there? So let's see. We'll just put a little note here. Try change the shape of x instead of y. So you see here how this one has the shape 3, 3, but this one has the shape 2, 2. That's because in this operation, we multiplied 2 tensors with the shape 3, 2 and 2, 3. So the resulting tensor finishes with the dimensions of the outer dimensions. Whereas in this case, if we go tf.reshape x, shape equals 2, 3, y dot shape, we also want the shape here. This is our other rule of matrix multiplication. Because we reshaped x, the resulting matrix here ends up in a shape of 2, 2, because it becomes the outer dimensions. So see here, back to our rule, numbers on the inside must match, New size is the same as outside numbers. Okay, so in both these cases, depending on which tensor we reshaped, the matrix multiplication works, but the resulting output is different. Now, that's a very important point. When you're dealing with matrix multiplication or dot products, it really depends on which tensor you manipulate in terms of what your output would be. So see here how different these two outputs are? Again, we're multiplying the same numbers, but just in different shapes. So that's an important concept to be aware of. And now, we can do the same thing with reshape as with transpose. So let's have a look. This is another important tensor transformation. So we can do the same with transpose. However, as you'll see in a second, transpose is slightly different to what reshape is. So transpose, and if we do TF reshape X, shape equals 2, 3. So this is the transpose tensor. They're the same shape as reshaping it. However, you'll notice with the transpose is that, well, let's get X, the first one as well. It starts off as 1, 2, 3, 4, 5, 6. Then the transpose is 1, 3, 5. The odd ones are up the first row, and then 2, 4, 6. And then the reshape is 1, 2, 3, 4, 5, 6. So the difference between transpose and reshape is that transpose flips the axes, whereas reshape just shuffles the tensor around into the shape that you want. So if we go here, TensorFlow transpose. TF transpose, here we go. Transpose A, where A is a tensor. Wow, that's a great description. Permutes the dimensions according to the value of perm. The returns tensor's dimension I will correspond to the input dimension perm I. If perm is not given, it is set to n minus 1 to 0, where n is the rank of the input tensor. Hence, by default, this operation performs a regular matrix transpose on 2D input tensors. Okay. So we see here 1, 2, 3, 4, 5, 6, transpose. Now the shape is 3, 2. Again, we could try a bunch of different examples, but let's go back and write some different code here. So what we might want to do is, because transpose also changes the shape of our X tensor, let's try matrix multiplication with transpose rather than reshape. So TF mapmul TF transpose X and Y. What might be the output here? Let's find out. 89, 98, 116, 128. Now see how that is different here? Now that is because transpose flips the axes rather than shuffles around the elements of a tensor. This can be quite confusing. However, this kind of data manipulation is a reminder that you're going to spend a lot of your time in machine learning and neural networks reshaping your data in the form of tensors to both prepare it to be used with various operations such as feeding into the model, and once you get it out of the model, to be able to deduce patterns from it and convert it into something human understandable. Now, again, the numbers that we're dealing with are just basically toy numbers. To see an example of how matrix multiplication is actually used, this is a great example. This may seem an odd and complicated way of multiplying, but it is necessary. I'll give you a real-life example to illustrate why we multiply matrices this way. So, example, the local shop sells 3 types of pies, and then we have details here. And if you go through this, this is actually a dot product to work out the value of sales for any given day. Now, this is just a small example here, but in the case of neural networks, they're actually going to go through an absolute multitude of these different numerical transformations to find patterns in our data. The good news is, most of the time, is that once we've set up our neural network code, once we've gotten our tensors into the right shape, a lot of these are done behind the scenes for us. So, with that being said, let's finish this video here. And in the next video, we'll go through a little bit more. We'll really cement down, or we'll get some more practice with transposing and reshaping different matrices and practicing matrix multiplication. So I'll see you there. We've had a little bit of hands-on practice with matrix multiplication and transposing and reshaping different tensors. We're going to do one more video on it to really nail it down. So let's call this one the dot product. And we want to turn that into a markdown cell. Beautiful. So let's go here. Matrix multiplication is also referred to as the dot product. And now you can perform matrix multiplication using, we want tf.matmul matrix, which is short for matrix multiplication, or we can do it with tf.tensor. We haven't seen this one yet, but they essentially do the same thing, just with different parameters. So we come here. We've also gotten hands-on with matrix multiplication using matrix multiplication.xyz, and we've seen this colorful example of the dot product. But let's once again get a little bit more hands-on with some code. So let's see how we might use tensor dot. Again, I'm spelling tensor wrong. I'm going to do that throughout this whole course, aren't I? There we go. So perform the dot product on x and y. Now this requires x or y to be transposed. We've also seen how transposing results in different outputs than reshaping. And transposing is flipping the axis, whereas reshaping is just reshuffling. So if we come here and if we reset this, I want you to have a guess at what type of operation this is. Is this a reshape if I go like that and flip it? Or is that a transpose? I'll give you a hint. What did we do? We had to flip the axes to get it up like that. So in that case, it's going to be a transpose. Now, let's use tf tensor dot. And actually, before we do that, let's remind ourselves of what x and y are. X is a tensor of shape 3 and 2, and y is a tensor of shape 3, 2. They have increasing elements from 1 through to 12. Beautiful. Now, if we go tf transpose x and y, oh, I've typed y as a mini case. There we go. Tensor dot, oh, missing argument axes. So we want to type in on the first axis. Beautiful, 89, 98, 116, 128. Now if we look up tf tensor dot, what is this going to tell us? Tensor contraction of A and B along specified axes and outer product. Tensor dot, also known as tensor contraction, sums the product of elements from A and B over the indices specified by A axes and B axes. Now again, you can read through this if you'd really like to, or you can practice coding it. I would suggest doing both. Now, in this case, you might notice that we could use transpose or reshape. However, we get different results. Now, let's try matrix multiplication by transposing y and reshaping y. We've done it with x. Let's try it with y. So, perform matrix multiplication. There's going to be a lot of repetition when manipulating tensors because we want to get practice. Y transposed. So tf matmul, let's take x and we'll transpose y. Transpose, there we go. Now perform matrix multiplication between x and y reshaped. tf.matmul. You might be wondering why I'm just continually showing you different ways of manipulating matrices. It's because you're going to spend a lot of your time reshaping tensors and matrices into the shape that you want them. So if we can get as much hands-on experience as we can, it might not mean too much to us now because we're just working with toy data. It means later on down the track when we have to reshape and manipulate our tensors and matrices is that we've got all of this practice under our belt. Wonderful. So we see we get different results from transpose and reshape. Now, to really demonstrate the fact here, or the fact that calling reshape and transpose on y don't necessarily result in the same values, is that we're going to go through the same steps we did up here before for x. But let's make it a little bit more pretty. So check the values of y. This is how I really try to understand things. And transposed y. So if I am writing some code, as I've said before, and I'm wondering why I'm getting different outputs of my tensors and the calculations that I'm making aren't really sort of making sense in my head. By the way, this /n is for new line. As I've said, one of the most common errors you're going to get in writing neural network code is misshaped tensors. And even more like sort of just as common, but deceiving error that is when your tensors line up with shape, but the outputs that you're getting, so you get no error message, it just works. So it's important then to be able to investigate what's going on and figure out, that's called a silent error, is that when your code works, like no error gets outputted from the code itself, but the results just clearly aren't correct. So this is the sort of thing that I will do to investigate those silent errors. TF transpose Y, that's what we want to do. So I'll create some sort of print statement like this, and then I'll use this to really get my head around what's going on. So this is our normal Y, 7, 8, 9, 10, 11, 12, beautiful. Now this is reshaped, again, just reshuffled. We bring the 9 up here, we move the 10 across, the 11 comes up there, the 12 goes on there, so 7, 8, 9, 10, 11, 12, beautiful. Now this is the transposed, so all we've done here is just flip the axes. Let's recreate this one, nice and simple. So 7, 8, 9, 10, 11, 12 over here. We'll just let that run through. This is a great way to just visualize. Let me reset this. 7, 8, 9, 10, 11, 12. Okay, we come back to this tab. You see how we've just got the same tensor here? 7, 8, 9, 10, 11, 12. This is the same over here. Beautiful. Now watch. This is a transpose. We're going to bring this up, flip it, boom. That's what has happened here. You see? Except this one is upside down in this case. So it just displays it slightly differently, but the shape and where the values end up, in this case, is what's going to happen if we were to write, say, some code like this. So if we go tf.matmul, x tf transpose y. Beautiful. There we go. So this is a sort of investigative work that we do. We've had a fair bit of practice now transposing and reshaped. If you're still unclear what the difference is between transpose and reshape, or you're wondering, which one should I use? Well, most of the time, these operations will be done behind the scenes for you. So if you write neural network code, it's going to do a lot of matrix multiplication behind the scenes to figure out different patterns in numbers. What sort of patterns are they? Well, remember, here's a simple example of the kind of patterns you can work out with matrix multiplication. But again, it'll be different depending what problem you're working on. But generally, whenever you're performing a matrix multiplication on two different tensors and the shapes of the matrices or tensors don't line up, you will transpose one of the tensors rather than reshaping them. So I'll write that here. Generally, when performing matrix multiplication on two tensors and one of the axes doesn't line up, you will transpose rather than reshape one of the tensors to satisfy the matrix multiplication rules. Alrighty. So again, if there's anything that doesn't quite stick out or make sense, I would definitely encourage you to create a whole bunch of different tensors. Try to use tf.matmul on them. Try to use tensor dot if you want, or try to even use the @ operator between them. Generally, if we're using TensorFlow, we're going to be using matmul. But get some errors, fix the shapes with transpose and reshape, and see what kind of different outputs you get. So we've covered matrix multiplication. Now let's have a look at, if we've got the default data type is often int32. So sometimes, depending on what data we're working with, the data type might not be int32. So what if we had to change the data type of a tensor. That's what we'll look at in the next video. I'll see you there. All right, so as we said in a previous video, the default data type of most tensors will be int32, depending on how they've been created. However, sometimes you'll want to change the data type of your tensor. So let's see how we'll do that. So we can create a new tensor with the default data type, which is float32. Yeah, let's start off with float. Now, I just said that the default is int32, but if we go, the default data type will actually depend on what data is inside your tensor. So if there are floats inside your tensor, we will have b.dtype tf float32. Now if we create c equals tf constant, now in here we want 710, and this is going to be c dtype int32. Wonderful. So in the current version of TensorFlow that I'm using, which is tf, I believe it's 2.3 version, 2.3.0, you may have a slightly different version depending on when you're watching this video. At this time, if we create a tensor with floats inside it, they're going to be of float32 type. And if we create a tensor with integers inside it, they're going to be of tf.int32 type. Now, let's say if we wanted to change from float32 to float16. Now, this is called reduced precision. Let's go 32-bit precision. What does this mean? So I'm reading a book about OpenGL ES development. A float in Java has 32 bits of precision, while a byte has 8 bits of precision. This might seem like an obvious point to make, but there are 4 bytes in every float. Okay. So that's in Java. That's not what we want. So 32-bit precision tensor versus 16-bit precision tensor. Mixed precision. Here we go, TensorFlow. Why did we ever doubt the TensorFlow documentation for having something? Mixed precision is the use of both 16 and 32-bit floating point types in a model during training to make it run faster and use less memory. Okay. By keeping certain parts of the model in 32-bit types for numeric stability, the model will have a lower step time and train equally as well in terms of evaluation metrics such as accuracy. Using this guide, this API can improve performance by more than 3 times on modern GPUs and 60% on TPUs. Today, most models use float32 dtype, which takes 32 bits of memory. There we go. However, there are 2 lower precision dtypes, float16 and bfloat16, each which takes 16 bits of memory instead. Beautiful. Modern accelerators can run operations faster in the 16-bit dtypes. Okay, so the main takeaway from this is that in TensorFlow, the default is 32-bit precision, right? However, we can also do, with modern pieces of hardware, we can also do float16, which takes 16 bits of memory instead. And modern accelerators, which are talking about hardware accelerators, so when we run our code on hardware, can run operations faster in the 16-bit dtypes. That is what's exciting. So, in our case, if we wanted to change our numbers from 32-bit precision, in other words, storing this tensor in 32 bits on memory, we wanted to change it to float16, how might we do that? Well, let's have a look. We can use tf.cast. And then we're going to pass it our original tensor, and then its new dtype is going to be tf_float16. Oh, and then we want to do b, find out b. Wonderful, dtype equals float16. The original b, what we might do is type out b, and then b.dtype. So we'll reinstantiate b up here, or maybe it's better just to go d here. Yeah, that's a better idea, Daniel. Wonderful, look at that. We got float32, and now D is the same as B, but it's been stored as float16. So, again, might not matter too much for tensors of only 2 elements, but if we had a tensor of 1,000,000 elements, and we reduced the floating point size from 32 to 16, we've basically halved the amount of space our tensor is taking up on memory, allowing a hardware accelerator to make calculations on it, potentially twice as fast. Now again, that scale may be different because there's a lot of different things that go into computing scale and speeds and whatnot. But that's the concept I want you to imagine, is that although these numbers here take up less space on memory, they may be able to compute faster. And the same thing goes for if we wanted to change from int32 to float32, we can do it in a very similar manner. So let's go change from int32 to float32. So we can go e equals tf cast. Which one do we make? C dtype equals tf float 32. Now let's have a look at E. Beautiful. So C was originally, there we go, dtype equals int32 and 710. We just changed it using tf cast. So E is now, take C and turn it into a float 32. Beautiful. And now we can take E float 16 equals tf cast E dtype equals tf float 16 E float 16. Wonderful. So there are many different data types in TensorFlow. So if you ever come across the need to change your data type of a tensor because some calculations aren't working correctly, tf cast is going to be your friend. So with that being said, let's have a look in the next video. We're going to go aggregating. We'll see what that means. So have a play around with this one. Create some tensors of float type, of integer type, and then change them from, you can go from float 32 to float 16, or you could go from int 32 to float 32. See how many different combinations of data type you can create and change before we see how we can aggregate our tensors. Welcome back. Now, after the last video, I took another little break. And so what you see here is when the cell numbers are empty. I just want to show you this. This is, rather than going straight onto the next video in practice, I just want to show you how I actually work with Google Colab notebooks every day. Is that when you leave it for a while, all your information in Colab is going to shut down so that Google's compute resources can be allocated to other people who want to use Colab. So you see here, I haven't got a connection. But if I decide to run a single cell, Shift and Enter, it's going to allocate some memory to me. Basically a computer in Google's warehouse full of computers somewhere around the world. And once it's ready to go, boom, we're connected. However, if I try to run this cell above here, TF is not defined. So I haven't imported TensorFlow. So what I often do is, we saw this in a previous video, but it'll work better now because see here, we've got 0, 1. These are the first cells I've tried to run in this notebook since taking a break. Let me do, if I wanted to run, I could do restart and run all. So that would run all the cells in this notebook. Or I could just do run before, which is what I usually do. It's going to try and run all of the cells before whichever current cell that you're on. But boom, we get our type error right back up the top here where we created our changeable tensor with tth variable and we deliberately caused an error. So if that happens, your errors are not going to fix themselves, but then we can just go back to here and then we should be able to run all of our cells. I'm just continually pressing Shift and Enter. Should be pretty quick because we're not processing much data here, but we'll go right down to where we were, aggregating tensors. Oh, we got another error. That's all right. We'll keep going. Oh, we've covered a fair bit of ground here. Are we at? Yes, here we are. So we're back to where we were. So aggregating tensors. Now let's have a look. What does aggregation mean? Define aggregation. A group, body, or mass composed of many distinct parts or individual. A galaxy is an aggregation of stars and gas. The collecting of units or parts into a mass or whole. The condition of being so collected. Well, that doesn't really help us with understanding tensors, but we're going to see hands-on what aggregation means. In the concept of, or in the topic of tensors, so to me, aggregating tensors equals condensing them from multiple values down to a smaller amount of values. That's how I conceptually understand aggregation. You can create your own definition, and in fact, I actually want you to start doing that more and more with as you get more familiar with the world of deep learning, is to, of course, there's going to be agreed upon definitions in the field, but I also want you to start conceptualizing your own definitions in a way that you best understand things. But let's see how we might start aggregating our tensors. The first way we're going to do is by getting the absolute values. So this is actually probably not the best form of aggregation to start with, but we're going to include it here anyway, just for completeness. So we create a tensor. What were we up to? E. We might recreate D here, TF constant, just because Daniel begins with D, and it's aside from the number 7, D is probably my favorite. Sorry, number 7 is probably my favorite number, and D is probably my favorite letter. So fun fact about me. There we go. Get the absolute values. Beautiful. So, we just created a new tensor. And if we wanted to get the absolute values, we can go tf.absd. And we'll see what this does. Beautiful. So the absolute values are basically just take all the negative numbers in one tensor and turn them into positive numbers. So if we see here, let's check out the docstring. I'm pressing Shift Command Space to get this docstring. Computes the absolute value of a tensor. Given a tensor of integer or floating point values, this operation returns a tensor of the same type where each element returns the absolute value of the corresponding element in the input. Beautiful, so that's your formal definition. And then we've got some example use cases. So let's actually start to see a few more versions of aggregation. Let's go through the following forms of aggregation. We'll turn that into a markdown cell, and we'll come down here. The first one I want to go through is get the minimum, and then we might want to get the maximum of a certain tensor. We might want to get the mean of a tensor, and we also might want to get the sum of a tensor. Now, I've shown you a few different ways of how you can explore different methods in TensorFlow. So if you wanted to start with a tensor and find the minimum, the maximum, the mean, or the sum, how might you research? So if we go here, find the mean of a tensor in TensorFlow. Here's a little hint. If you were to search that, you can pause the video now, skip and go ahead and try to create your own tensor, do these 4 things, and then come back and we'll compare notes, all right? But otherwise, if you're going to watch on, let's start by creating a random tensor so that we can practice each of these 4 things here. Create a random tensor. We might create a larger tensor. Yeah, how about we do that? With values between 0 and 100 of, how long should we do it? Of size 50. Let's do that. So E equals TF constant. We'll do it using a NumPy random array. So again, this is going to just be return random integers from low inclusive value to high exclusive value. So we can just go 0 to 100, size equals 50. Now this should give us a tensor. Beautiful. 50 values between 0 and 100. And we might go how do we check the size of our tensor? Let's practice. And then how do we check the shape of our tensors? And then how do we check how many number of dimensions our tensor has? Beautiful. So we get size is 50, beautiful. The shape is also 50, and the number of dimensions is 1. All right. Now, how about we start with finding the minimum? So we're going to go find the minimum. To find the minimum of a tensor, you can do reduce min, pass it a tensor. Put the output there. Now, this is going to be a little bit of a trend with TensorFlow aggregation, is that the reduce underscore, in some, like NumPy, if we did MP min, I believe, we can just go 0. But TensorFlow tends to put reduce underscore min in front of its aggregation methods here. So we'll get rid of that one. So knowing that this is the way to find the minimum, how do you think we might find the maximum? Let's find it anyway. Find the maximum. TF reduce max. Wonderful. So there's 97. So that makes sense because we have values between 0 and 100. So our lowest value so far is 0 and the highest value is 97. And find the mean. Let's go TF reduce mean of E. And wonderful. So 48 is about the average. So get the sum of a tensor. Let's have a guess. Find the sum. TF reduce underscore sum of E. And there is the sum of our tensor. Beautiful. Now, there's a few other things that we can do, such as I'm going to put a little challenge here. I want you, of our E tensor, before the next video, I'm going to put a little emoji here. Exercise is to, with what we've just learned, find the variance and standard deviation of our E tensor using TensorFlow methods. So, if you're not sure what variance and standard deviation are, this challenge has two sides to it. First, you have to find the code to find the variance of our E tensor, and then you have to look up what variance and standard deviation are. So, go and give that a try, and I'll see you in the next video. We finished up the last video with a little challenge. So, did you figure it out? Did you find the variance and standard deviation of our E tensor using TensorFlow methods? I hope you gave it a try, but if not, we're going to check it out here. So find the variance of our tensor. Now, as you might have guessed, we can do TF reduce var E. Oh, has no method reduce var. Is it variance? Has no method reduce variance. Oh, TensorFlow variance. I typed TensorFlow wrong. Okay, we can do the reduced standard deviation. Have I led you on a wild goose chase? Yes, I totally meant for all this to happen. TFP. So what we might need to do is, what's TFP? This is what I like to do, is just figure out, go down the rabbit hole. TFP, TensorFlow probability. Okay. How do we import it? Can we do import TensorFlow probability as TFP? There we go. And then we might do tfp.stats.reduce variance of E. What was that method again? We come back here. This is the type of research I want you to start practicing. Okay, tfp.stats.variance. There we go. Wonderful. Okay, so there's the variance there. I'm going to put here, won't work. And then if we wanted to find the standard deviation, so let's put a little note here actually. To find the variance of our tensor, we need access to TensorFlow probability. And then we go here, find the standard deviation. See, I thought that you would be able to just do reduce variance. So I've learned something there too. Apparently, we need TensorFlow probability to find the variance. Now, I believe we can find the standard deviation here. Reduce STD. What's happened here? TF math reduced STD. Does it not have an alias? What if we do tf.math.reduce STD? must be either real or complex. So if we come here, input tensor. What's wrong with our tensor? Reduces input tensor along the given axis. Unless keep dims is true, the rank of the tensor is reduced by 1. Input tensor, the tensor to reduce, should have real or complex type. Does it have to be a float? This is a good little challenge. I'm glad I issued this exercise. We can work this out together. So where's our, here, dtype int 64. You know what I think this method might need? Is if we cast our E tensor as dtype tf int 32, this might work. Int 32. Input must be real or complex. Maybe float 32. There we go. Okay. So this is what I mean. Things may not be as they appear when you go through the TensorFlow library. So up here, we've got a few relatively easy methods compared to what we had to do here. But this has been a great practice as to how you might go about researching and trying things out to make something work. So if you ever get that error that we got just before, let's write this again. So tf math.reduce std e for our tensor. So type error. If you ever get the type error message, come to the documentation, which is what we did here. All right, so there's tf math reduce std. And check out the types that they're using in the example workflows. So see here, the reason why I picked up that we might need to change our tensor to data type float 32 is because they're using floats in their input sample here. So there we go. Returns the reduced tensor of the same dtype as input tensor. Note for complex or complex 128 input, the return tensor will be of type float 32 or float 64 respectively. So usually, a lot of the time when you're working with TensorFlow, float 32 is generally sort of the standard type throughout the entire library. So if you need to change the type of your tensors, chances are it might have to be in float 32. But that was a good practice in exploration. Now in the next video, let's see how we're going to find the positional, maximum, and minimum. You might want to try this out now that you've had your expert problem-solving skills upgraded in this video. See how you might find the positional maximum and minimum of a tensor. I'll see you in the next video. So I was all ready for this video to jump straight into finding the positional maximum and minimum. However, after a little bit more exploration of the TensorFlow documentation, which can be a bit of a beast to tame, I found that we didn't actually have to jump through some of the hoops we did in the last video to find the variance. So look at this. I thought that we might just be able to go tf.reduce variance. It turns out we can find the variance of our tensor in a very similar way than what we've done here, finding the standard deviation, which is strange because with these methods, you can get rid of the math, but with the variance and standard deviation, you require the math. And so we've both learned something here. So I want to just show you here, if we want to go find the variance of our E tensor, we go tf math.reduce variance E, just exactly like we've done here in the documentation. And if you're ever stuck, you can just go through the documentation here, like tf.something, and just read up all the different methods. I mean, we're working with tf.math, so you might want to even try a fair few of these just to see what happens with what you're working on. But anyway, let's go back here. We'll find the variance. Input must be real or complex. How did we fix that? We'll go tf.cast. Let's change this dtype to tf float 32. And, oh, we forgot a little bracket on the end. Wonderful. We get a very similar number up here to our variance that we found using the TensorFlow probability. So, turns out we actually don't need access to TensorFlow probability. However, what we just went through was a great exercise in figuring things out. I mean, at first you'll try something and it might not work, and then you'll find a fix to it. Then you'll find that, hey, the fix probably wasn't even the best way of doing it. We did a little bit more research and we found we wanted to find the variance without inputting any other libraries aside from TensorFlow. We can just do it like this. But anyway, let's get into finding the positional maximum and minimum. Now, when might this be helpful? Well, you're going to see this a lot when your neural network outputs prediction probabilities, which we haven't seen yet. But if we go here, so remember our little example where we got our images, we input it into some numerical encoding, goes through our neural network, finds the patterns in there, adjusts its random weights that it initializes with, it updates its representation outputs. And then here, oftentimes the representation outputs are referred to as prediction probabilities. So in this case, 983 is the highest number, 0.04, 0.013. So imagine if above here, if this column was, say, ramen, and this column was, say, spaghetti, and this column was, say, not ramen or spaghetti. So in this case, this number, the highest output, this is our ramen column, would be dedicated to ramen because the first index here, the 0th index, the highest number goes to ramen. And then if we wanted to turn this row into labels, we might go ramen, spaghetti, not ramen or spaghetti. Which one has the highest value? The index where spaghetti occurs. And then for this one, which is no food, so ramen, spaghetti, no food or spaghetti, this is the highest number. So we might want to get this index. So that's what I mean by finding the positional maximum minimum. At which index of the tensor or of this row does the maximum value occur? So in this row, it occurs at the 0th index. In this row, it occurs at the first index. And in this row, it occurs at the second index. But let's have a look how we might do that in code. So the first thing we're going to do is create a new tensor. So create a new tensor for finding positional minimum and maximum. We go here, f equals tf random. We'll create a random tensor with uniform this time. We'll give it a shape of, we'll get it 50 long. Let's have a look. Beautiful. Now I wonder if we go here, tf random set seed equals 42. Do we get the same numbers? So this one is, you help me remember what's this first number, 6645621. Okay, beautiful. So if you use random seed 42, you should get the same numbers as me. Don't worry too much if you don't, if something's changed between now and when you watch this video, but we just need a tensor with 50 random numbers and we can work with this. So if we wanted to find the maximum element position of f, meaning at which index does the maximum value occur? So I'm going to guess, let's have a quick look. There's 948. Can we beat that? Yes, we can. There's 967. So that'll be about, maybe 43. Let's try. TF. So find the positional maximum. Now, the positional maximum is often referred to as argmax. So I believe it's the same in NumPy, mp.argmax. If we wanted to find the docstring here, returns the indices of the maximum values along an axis. Same with argmax. Returns the index with the largest value across axes of a tensor. So let's do it. Let's put in our 42. Oh, so we were close. Now, if we were to index on our largest value position. So what I mean by this is if we grab our f tensor and then we find argmax f, what value are we going to get? Boom, it's that value there. And then if we go find the max value of f, tf dot reduce max f. Do all these values line up? Wonderful. So this should, now let's check for equality just to be safe. If we go argmax tf, argmax f, does this equal, we might put a little assert here, because this will error if they don't equal. No error. And then if we take away this assert, we should get true. Beautiful. So this is we're indexing. Does this make sense that they are equal? Because look, we found the positional maximum, which gives us position at index 42, which is this one. That's the maximum value of this tensor. And then we can index on our largest value position. So it's saying, hey, take the F tensor and grab position 42, or grab the value from position 42, which is this. Yes. Now, if we use just our reduce max method, which is saying, hey, find me the max value of F, we get this value, and then we check to see if they're equal. Beautiful. Now, another one you might use, I don't use this one as often, is finding the minimum. So wherever the positional minimum occurs in here, can we find it? There's 0.03, that's pretty low. So maybe it's that one. Or there's 0.009. So I'm guessing that might be at, let's go 21 or 20. So find the positional minimum. We want to do TF, you might be able to, if argmax finds the maximum, what do you think finds the minimum? If you guessed argmin, 100 points for you. Boom, so position 16, let's find out what it is. Find the minimum using the positional minimum index. So F, TF, argmin, F. 0.009. So that was actually 16. There we go. So that's index 16. Beautiful. Alrighty then. So what we might do in the next video is we can see how we can squeeze our tensor. In other words, removing all single dimensions. So have a go at this. Maybe create your own tensor. Can be as big as you like. And practice around using the argmax and argmin methods to see if you can find the minimum, maximum positional values of your tensor. And I'll see you in the next video. How'd you go? Did you create your own tensor? Did you find the minimum and maximum positions? I hope you did. But for now, we are on to the next part, which is squeezing a tensor. Oh, we're going to give our tensors a big hug. In other words, removing all single dimensions. You're going to fall in love with tensors by the end of this course if you haven't already. Now, what we might do is, as always, we need to create a tensor to get started. Now, I might go here, G. Are we up to G? Yeah. E, F, G, H, I, J, K, L, M, N, P. I won't do that again. No promises, but I like to sing. Now, if we go here, what have we got? So I'm creating a similar tensor to what we did before, random uniform, but in this time, we're going to use the shape parameter to add a few single dimensions right to the start. So if we check G, look at this. So we have just, actually, let me use our faithful random seed as 42. Beautiful, we're getting the same numbers there. Yep, 6645, 621. Maybe I'll know that off by heart by the end of this course. And so we have here, the shape is what we have to pay attention to with squeezing. So this is shape 11150. So see here, we've got a few square brackets, 1, 2, 3, 4, and then the innermost square brackets is where the big dog 50 is sitting. Now, what we're going to do with squeezing, it's actually quite a fun little concept. So if we go G shape, we get that. Now, if we were to go G squeezed, that could be our TensorFlow wrapper name, G squeezed. TF squeeze, and now, actually, we'll check the docstring. Removes dimensions of size 1 from the shape of a tensor. Now, if I were to run this, what do you think G squeezed new shape is going to be? I'll give you 3, 2, 1 to guess. And now let's check. Boom. So there we go. So what squeeze does is, we just read that before with the docstring, but we'll read it again. Removes dimensions of size 1 from the shape of a tensor. So if your tensor has too many single dimensions and you want to just reduce it, so get rid of all these extra dimensions here and reduce it back to its essence, you can use the squeeze method. So that's a little tidbit there. Nice and quick video, this one. And the next one, we're going to cover one-hot encoding. So I'll see you there. Okay, so if you wanted to one-hot encoding tensors. Now, what is one-hot encoding? Let's check this out. What is one-hot encoding? If you've done any machine learning before, you might have come across one-hot encoding, but it's a very important concept in terms of preparing data. This is a great website, by the way, Machine Learning Mastery. So let's check what this says. There, okay. So this is a great example. We'll create our own in a minute, but let's just have a look here. So we've got 3 columns, red, green, blue. So row 2 has a 1 for red and 0 for the rest. So that is one-hot encoded for red. Row 3 has a 1 for green, but 0 for red and blue. So that is a one-hot encoding for green. And row 4 has a 0 for red, a 0 for green, and a 1 for blue. So that's a one-hot encode for blue. So that's a great way to turn, if we just remember, what do we have to do when we're passing our data to neural networks? We have to find a way to numerically encode it. One-hot encoding is a form of numerical encoding. So if we had the colors red, green, blue, and we wanted to pass it to our neural network, it would look at that and go, you know what? I'm very smart. I can find out patterns and numbers, but when you pass me words, red, green, blue, I can't understand them. So we could one-hot encode those words. Red could be 1 for red, 0 for blue, 0 for green, and so on, and then pass those as a tensor to our neural network. So let's have a look how we might do that in code. What we should do is create a list of indices. So values, pretend this is, let's get our sum list. Sum list can be 0, 1, 2, 3. In other words, maybe we go, could be red, green, blue, purple. And now, if we wanted to one-hot encode this, we can go one-hot encode our list of indices is tf.onehot sum list. We're missing one positional argument. All right, let's look up the docstring. What does this say? tf1hot returns a one-hot tensor. If on value is not provided, it will default to a value of 1 with type dtype. Okay, where's the example? Here we go. For example, indices equals that, depth equals 3. We need to pass a depth parameter. Okay, so the output's going to be 3 pi 3 because this is 3 long and the depth is 3. So let's figure this out. Depth. If we have 4 elements here, what I've kind of given it away here, so pretend you can't see that. Well, it's going to be 4. Let's try it out. There we go. So do you see what's happened here? What kind of tensor we've created? We've transformed this tensor, sum list, into one hot encoded version of itself. So for the first row, this relates to the first element. So it's got a 1, as you see, for where 0 occurs, but then 0 for all of the other values. And now for this one, we've got this refers to this value here. It's got 0, yes, and a 1 because this is a number 1 here, and then so on for the other 2 values for each rows. Beautiful. Now, a fun little thing that we can do is that if we wanted to change this from, you're rarely going to use this in practice, but I want to show you anyway because it's cool. If you wanted to get rid of, rather than using 1s and 0s, we can use on value and off value and pass them different values. So let's go specify custom values for one hot encoding. If we want to do tf1hot sum list, depth can be 4, and then on value can be, yo, I love deep learning. And then the off value can be, let's go, what could we do? I need something fun here. I also like to dance. Boom. Let's see what this comes out with. Oh, yo, I love deep learning. I also like to dance. 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 Yo, I love deep learning. I also like to dance. Did you know I like to dance? So, have a practice with TF1 hot. Maybe create some of your own on values, off values. Again, rarely will you ever use them when you're passing them to a neural network, because a neural network, what does it love? It loves numbers. But yeah, this is just a little fun exercise to practice one hot encoding. Now, if we look up the tf.1hot, I believe it requires, so the indices, the indices have to be a tensor of indices. Okay, well, that makes sense. So yeah, go through the example there, create your own list of indices, and then one hot encode it, practice around, see what happens if you change the depth parameter, and then change the on value and the off value. And I'll see you in the next video. Did you have some fun creating one hot encoded tensors with different on and off values? I hope you did, and I hope you're loving deep learning. We actually haven't covered too much deep learning yet. We're still in the fundamentals, but I do believe you do like to dance. So by the end of this section, you're going to be able to dance through your way through TensorFlow code. And speaking of which, let's do a little bit more dancing through, there are some math functions. I just want to show you how to use a few more of these that you may come across. There's a lot here, as you see, tf.math overview. We've got a whole bunch here, but let's practice with a few more. We can never get enough practice. We might go a few common mathematical operations, a squaring, log, and square root. So let's see how we'll do that. First things first, let's create a new tensor. So this time we might go H, I believe we're up to. So TF, I'm going to show you a new way to create a tensor. 1 to 10. Nice and simple. Oh, let's see it. There we go. Now, if we want to square it, how do you think we might do it? TF square H. Beautiful. So we get just the square of all that. So 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, etc., etc. And then if we wanted to find the square root, let's find the square root. We come over here. Maybe we go square root. Will this show us? There we go. TF math square root. Beautiful. Let's try that. Now, I believe it may have an alias. We can just skip the math part. Oh, what do we got here? Invalid argument error. Value for attribute t of int32 is not on the list of allowed values. Okay, this is good. So again, we're coming across a value error where it's saying that int32 is that the type of our tensor. Yes, it is. Int32 is not in the list of allowed values for this function. So we want b float, half float, double, complex 64, complex 128. Okay, let's change it into a float. TF cast, and the d type is going to be TF float 32. Oh, forgot again. Boom! Look at that. There we go. Actually, let me put this one above here so that you'll know for future reference is that this is going to be will error. Method requires non-int type. So if we put here just h, we get an error. Wonderful. How about we find the log? So we go here, find the log. Now, again, TensorFlow, oops. We want to go up here and search for log. TF math log, wonderful. Computes the natural logarithm of x element wise. Has it got an alias? I'm pretty sure we can skip the math part, but if not, we can try it out. So find the log, TF log of h. Has no attribute log. Oh, do we need math for this one? We do. Oh, again, we get the same error as above. So what do we have to do here? Value for t of int32 is not on the list of allowed values. What do we have to do? I'll give you a hint. We have to turn it into a float, or at least one of the allowed values. We've got some rules here. So we go here, tfcast h dtype equals tf.float32. Will this work? Wonderful. There we go. So that's just an example again of how many different functions you're going to find in TensorFlow, and a little bit of practice again, as I can't stress this enough, is how much practice we're going to need sort of just making sure our tensors are in the right data type. So have a play around with some of the functions in tf.math and see how many of them, pick 3 and try them out. The ones that we haven't covered so far, and see if you come up against any errors like this, what you can do to fix them. So that's a little challenge before the next video. We've covered a whole bunch so far, and we've even seen before how tensors can interact with NumPy arrays, but let's have a dedicated session on tensors and NumPy. So if you've done any numerical computing before or any type of data science or machine learning, you've probably used NumPy. So if we come here, what is NumPy? Not going to dig too much into this because we want to get focused on using it. But chances are, there we go, the fundamental package for scientific computing with Python. So NumPy is a fundamental library for any type of numerical computing with Python, and it's all built upon the NumPy array. So TensorFlow interacts beautifully with NumPy arrays. And we can see an example of that by, if we create a tensor, this is what we've seen before, directly from a NumPy array. So if TensorFlow is built upon the tensor, NumPy is built upon the array, and the beautiful thing is that they basically have full interoperability. I believe that's a word. That's like a fancy word for they work together quite nicely. So there we go. We create an array here, and then we pass it to tf.constant to turn it into a tf.tensor. Beautiful. And now we can convert it back from a tf tensor to a NumPy array. So convert our tensor back to a NumPy array by just going np array j, and then we can check the type here by going type np array j. There we go. So np array j turns it into a NumPy array, and then when we check the type, it turns into a numpy.nd array, which is NumPy's base type, just like TensorFlow's base type is tf.tensor. All right. And we can also do the same thing as the cell above by convert TensorJ to a NumPy array using, if we go j.numpy, we've also seen the NumPy method in Tensor before as well, .numpy, and then if we check the type, j.numpy, we go here. Beautiful. So we can convert it back to a NumPy array there. Now, where this might be helpful is sometimes if you have, say if we have, let's rewrite j to be tf constant, it's just a single number there. If we wanted to have access it just as the float on its own, we can actually do .numpy, and there we go, that'll give us access to it there. And if we want to go there, so the beautiful thing about being able to really easily convert our tensors to NumPy arrays and NumPy arrays into tensors is that if there's some sort of functionality that we want to use with that doesn't work with our data in tensor types, we can convert it to a NumPy array and use it there, and vice versa. So if we delete that, let's see, there's one more thing you should know, and that's default types of each slightly different. So if we want to create numpyj equals tf constant. We'll create this directly from a NumPy array, just as we've done before. It's going to go np array same as above, 3, 7, 10. Wonderful. And then if we want to go tensor j equals just tf constant, we'll create this one directly from a Python list, 3, 7, 10. Now, if we want to go check the data types of each, now we've had some practice doing this, so you might be able to know if we wanted to check the data types of NumPy j and tensor j, what might we use? If you guessed we use the dtype attribute, you'd be 100% correct, tensor j. And if you didn't guess correct, well, that's all right, we get to practice. Boom. So there we go. So if we create a tensor from a NumPy array, the default type is float64. Whereas if we create a tensor from a Python list or directly through TensorFlow, the default type is going to be float32. Now, the reason why this is important is because, remember, we actually had some errors up here where we had to change the type of our tensors from a certain data type to another data type. So this is where I want you to be aware is that if you do convert your NumPy arrays into tensors, they may have a different data type to compared to if you created your tensors directly from TensorFlow. So just be aware of that. One of the main issues you'll run into when computing with different tensors is different data type issues. So treat this as your heads up. But that's a quick reiteration of tensors and NumPy. Remember, NumPy is a fundamental package for scientific computing with Python, and chances are when you're doing machine learning and deep learning, you're going to run into NumPy somewhere. So keep in mind, TensorFlow works beautifully with NumPy arrays and vice versa. Welcome to neural network regression with TensorFlow. Now, we've seen some of the basics of TensorFlow in the previous section. Now we're going to get hands-on building some neural networks with TensorFlow, specifically neural networks for regression. Now, before we get into things, I'm going to start this lesson off with a slide called Where Can You Get Help? Now, this is very important because learning a new concept is challenging, of course. So, that being said, if you do get stuck, here are the steps I want you to take. First of all, follow along with the code. I'm going to be writing it with you. Remember our motto, if in doubt, run the code. If I'm going too fast, that's all right. Slow the video down, then try it for yourself. If I'm going too slow, you can speed the video up and beat me. If we're writing TensorFlow code, don't forget in Google Colab, you can press Shift Command Space to read the docstring. That will get you a little bit of information about any of the functions that we're running. And then, if you're still stuck there, if the docstring doesn't have that great of an explanation, remember, most docstrings in TensorFlow have examples of different code, so try it for yourself. But then, still stuck, search for it. You're going to become very familiar with these two resources here, Stack Overflow, and of course, the TensorFlow documentation, which is forever improving, forever getting better. So it's very vast, but with a lot of experience, hands-on practicing, checking it out, you'll start to get much more familiar with it. Then, once you've learned some things from searching for it, don't forget to try the code again. Remember, back to the motto, if in doubt, run the code. You can't break anything. And finally, if you're still stuck, ask a question. I'm going to emphasize here, including I'm putting inverted commas. You can't see my face in this video, but I'm doing the inverted commas symbol with my fingers. The dumb questions. Don't forget the Discord chat. Ask a question if you're stuck. Very important skill to have is asking the right question. Now, with that being said, if we're going to do neural network regression with TensorFlow, you might be thinking, what is a regression problem? So let's have a look at a couple of examples of what regression problems are. Here we go. Some example regression problems. Say we're trying to predict the house or the sale price of a house we're interested in. So how much will this house sell for? If we've got a house down the street and we want to try and predict how much it's going to sell for, we might ask ourselves, how much will this house sell for? We just said that, didn't we? Another regression type problem is, how many people will buy this app? Or how much will my health insurance be? Or how much should I save each week for fuel? Now you'll notice a trend here with these questions. It's how much or how many. That's one of the key points of a regression problem. It's predicting a number of some sort. And if you're thinking about in terms of price or numbers in these types of questions, well, there are other types of problems where a regression, we can turn them into a regression problem, such as trying to predict the coordinates of where the boxes should be in an object detection problem. So these are numbers here. So say we've got 1390, so that would be on the x-axis. This corner, the top left corner of this particular box here, should be at 13 pixels in, but 90 pixels down, and so on for the top right corner, the bottom right corner, and the bottom left corner. And then again, we could do the same with these corners here, the top left. Remember, this is the perpetrator who hit and run on my car. So if I was going to build an object detection model to look at security footage around my home to see if I can find the people who hit and run on my car, I might train an object detection model, specifically a neural network regression, to try and predict the corners of where the bounding box should be around my target object. So this is what I want you to start thinking about. Although we have a kind of a one-liner definition for regression problems, predicting a number, is that a lot of the time in machine learning and deep learning, how you sort of think about the problem will definitely define how you approach that problem. And again, if you're not satisfied with the definitions here, this is what we can do. So what is a regression problem? Regression analysis. Here we go. In statistical modeling, regression analysis is a set of statistical processes for estimating the relationship between a dependent variable, often called the outcome variable, or one or more independent variables, often called predictors, covariates, or features. Okay, so we want to predict the relationship. So say this line, that's the relationship there. So the dependent variable, in our example problem of trying to predict the house price, our dependent variable might be the price of the house. So the house price is the outcome we're trying to predict. And the independent variables, often called predictors, covariates, or features, might be the number of rooms in the house, or the number of bathrooms, or the number of garage spaces, or all three of those combined. So the independent variables, so we might have 10 different houses with 10 different numbers of bedrooms, 10 different numbers of bathrooms, and 10 different numbers of garages, and 10 different house prices. And we might want to build a model to take in all that information and then predict what the house price might be. So with that being said, we're going to get into more examples of this later on as we write code. But let's have a look at what we're going to cover. Broadly, of course, we're going to be writing lots of code to do these things. We're going to cover the architecture of a neural network regression model, so specifically the building blocks of a neural network regression model, the input shapes and output shapes of a regression model, in other words, the features and labels, or, in Wikipedia terms, the dependent variables and the independent variables. We're going to look at how we can create custom data to view and fit. We're going to take care of the steps in modeling, such as creating a model, compiling a model, fitting a model, and evaluating a model. If all of these don't make sense right now, don't worry. We're going to get very hands-on with them and they'll start to make sense as we code them. We're going to look at different evaluation methods for regression models. And finally, we're going to look at how we can save and load our models so that if we do train a machine learning model and we save it, we don't have to go through that process of retraining. And if we want to load it into our applications going forward, we can do that using our save and load methods. And finally, how are we going to do this? A big emphasis between the chef and the chemist. Chemist is very exact, whereas what's a cook do? A cook tries things out, a cook experiments, pours in little bits of different flavoring. We're going to be cooking up lots of code. So with that being said, here's what we're going to cover. In the next video, let's have a look at what the inputs and outputs of a regression problem or neural network might look like. So if we're dealing with regression problems, well, we're trying to build neural networks to solve regression problems, what might be our inputs and outputs? Remember, in machine learning and deep learning, a lot of the time your focus will be on defining your inputs of your algorithm and what the outputs of your algorithm look like. So let's say we wanted to predict the sale price of this house. Now, this is an actual house that was up the road from me, not far from where I live, that was up for sale. And say I wanted to build a machine learning model to try and predict what I should offer if I was going to auction, what this house should sell for. So again, here's our little diagram of what we're going to be focused on. We have the inputs. So what might our inputs be if we're trying to predict what our house might sell for? And what might the outputs be? So if we're just looking at this diagram, and if we want to build a machine learning algorithm, we might have to build this ourselves. But first, let's focus on the inputs and outputs. So maybe we've got our house, and we know a few things about it. The number of bedrooms, the number of bathrooms, and the number of garages that it has. And we might have a whole bunch of other houses that are nearby, and we know what their sale prices are. What might we do with that? So we know these, okay. If we come back to our definition of a regression problem here, we're trying to figure out the relationships between a dependent variable, often called the outcome variable, and one or more independent variables, often called predictors, covariates, or features. Okay. So in our case, our independent variables might be the number of bedrooms, 4, the number of bathrooms, 2, and the number of garages, 2 as well. So for our machine learning model or deep learning algorithm, we're going to have to encode these in some numerical way because we can't just pass 4 bedrooms, 2 bathrooms, 2 car spots. So we'll put them into a numerical encoding, and as you might see here, this is a one-hot encoded. We've seen this before in the TensorFlow basics section. And so if we had this array here, or this tensor, this vector could be number of bedrooms. So it's 0, 0, 0, 1. Now what that would mean is that, does it have 1 bedroom? No. Does it have 2 bedroom? No. Does it have 3 bedrooms? No. Does it have 4? Yes. So we put a 1 there. And in this case, does it have 1 bathroom? No. Does it have 2 bathrooms? Yes. Does it have 1 garage? Yes. So 0 in case of one-hot encoding encodes for not that thing, and 1 encodes for that thing. So that might be our numerical encoding. Wonderful. We put these into here, and that's our inputs to our machine learning model. And these are often called input features, or in Wikipedia terms, predictors, covariates, or features. So features is probably the most dominant term that I use in practice and we're going to use throughout this course. If you ever hear input features, it's some kind of information about the data we're using that goes into our machine learning algorithm. And so in our case, if we want to put our inputs into a machine learning algorithm, so often one, and you'll find this in deep learning a lot, is that often an algorithm for your problem already exists. So that means someone has built something that has worked before for their problem, might be very similar to your problem, and you can utilize that for whatever you're working on. However, if it doesn't already exist, we can see how we can build our own. That's what we're going to be practicing. We'll see how we can build our own. But later on in the course, we're going to see how we can use algorithms that already exist. And finally, if we have a look at what our outputs might be, we might, if we're trying to predict the sale price of this house here, based on the fact that it has 4 bedrooms, 2 bathrooms, 2 car spots, and it's on a pretty big piece of land, if we wanted to make an offer, we're using our algorithm to figure out how much we should offer at auction. Our algorithm's telling us we should offer $939,700. Now, where does it get this predicted output from? If we have a look at what it actually would sell for, $940,000. So we weren't too far off here. We'll figure out some evaluation metrics to compare predicted outputs of our deep learning models to the actual outputs of what they should be, for regression problems, that is. Now, this predicted output comes from looking at lots of these actual outputs. So remember how we talked about supervised learning? Well, this is an example of supervised learning. So we might have 100 or 1,000 or tens of thousands of different homes with all of their input features and their actual sale price. And then we might feed these inputs and outputs to our machine learning algorithm, and it's going to learn the relationships. Remember, we come back to our definition of a regression problem. Regression analysis is a set of statistical processes for estimating the relationships between a dependent variable, right, so our sale prices, and one or more independent variables, so our input features here. So after our machine learning algorithm has looked at many, many examples, comes from looking at lots of these, of input features and outputs of house sale prices, it's going to learn the relationships between the input features and the outputs here. And then for use cases where we would like to predict the potential output of a home that we don't know the actual sale price for, we can feed its input features into our algorithm and have a suggested output of what the sale price or what we should pay if we were going to auction. So this is just an example of what regression inputs and outputs look like. We're going to have some practice writing code to do this very shortly. So another big point is once we've defined our inputs and outputs, and I can't emphasize this enough, is this is what we'll be focused on a lot of the time in machine learning and deep learning, is the blue parts here, defining our inputs, defining our outputs. And now another key term is when we're talking about inputs and outputs, is input and output shapes. So say here, we were taking our input features, numerically encoding them, feeding them to our machine learning model as inputs. Our machine learning algorithm works out the patterns or utilizes its already learned patterns to produce an output, aka the sale price of our home. What might be the shape of our inputs? Because remember, our numerical encoding is going to be in the form of a tensor. And this output here doesn't look like it, but it will also be in the form of a tensor. So here we go here. We've got bedroom, bathroom, garage represented as a tensor. And in this case, the shape is going to be 3 because we've got 3 input vectors here. Now, don't be confused by this outer bracket here. Because we've got 3 input features, the shape of our input layer to our machine learning model is going to be 3. 1 for bedroom, 1 for bathroom, and 1 for garage. We'll represent this as a tensor. And for our outputs in our regression problem, in this case, can you guess the shape? Is going to be 1. So in our case, for each example that we're going to pass through our machine learning algorithm, each sample will have an input shape of 3. So we need number of bedrooms, number of bathrooms, number of garages. And each sample will have an output shape of 1 for the price of what we're trying to predict. And now this is just for our housing price prediction example. We can adjust these. So here, the bedroom, bathroom, garage, to be almost as many different inputs as we want. But usually for a regression problem, the output shape is often 1 because we're trying to predict some sort of number. So again, if we come back to Wikipedia terms, we're trying to figure out the relationships between a dependent variable, often called the outcome variable, and one or more independent variables. So in our case, these are our independent variables, and this is our outcome variable, or our dependent variable. Now, with that being said, we've covered inputs and outputs of our regression problem. Let's now have a look at what that might look like in terms of building or writing neural network code. We'll have a look at it in the concept of an architecture of a neural network regression model. Recall in a previous section that we covered the anatomy of neural networks. So essentially every neural network that you build will have an input layer, some number of hidden layers, and an output layer. And for your input layer, this is where your data goes in. Now, hidden layers is plural on purpose or optional plural. It can have 1 up to 100. Some neural networks even have 1,000 hidden layers. It really depends on what problem you're working on. And now that's where the deep and deep learning comes from. So if you imagine if we had 10 of these hidden layers laid out here, or the more we had, the deeper our deep neural network would be. And then for the output layer, this is where the outputs or the learned representation or prediction probabilities of your neural network come. And within the hidden layers is often where your neural network is learning patterns or weights in the data. And so keeping this in mind, if we have an input layer, a hidden layer, and an output layer, what might the architecture of a neural network regression algorithm look like if we wanted to build one with TensorFlow? So this is what the typical architecture of a regression model in TensorFlow will look like. So in our case, we have a few hyperparameters here. Remember, a hyperparameter is a setting that you as a data analyst or a machine learning engineer can change. So we might have the input layer shape, the hidden layers, the neurons per hidden layer, output layer shape, hidden activation. We haven't covered that yet. The output activation, the loss function, and the optimizer. Now, we haven't covered the bottom half of this little graph here, but that's okay. We're going to get very familiar with that as we write code. And now I just want to emphasize that I've adapted this from page 293 of the Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow, book by Aurélien Guérin, which is a phenomenal book. This is probably going to be my number one external resource to go along with this course, is this book. I've read it end to end in its entirety, and I'd highly recommend it if you're looking at learning more with TensorFlow. But that's beside the point. We're getting hands-on here. Now, in terms of the typical value for each of these, the input layer shape, we've covered this a little bit before. So if we were trying to predict the sale prices of different houses, we might have an input layer shape as the same as the number of input features that we have. E.g. would be 3 for number of bedrooms, bathrooms, and car spaces in housing price prediction. Hidden layers, the value you have here is very problem specific. The minimum is 1, the maximum is unlimited. Again, the neurons per hidden layer is going to be problem specific again. So if we come back to our anatomy of neural networks, so this has 3 hidden neurons. So not only can you customize how many of these layers that you have, you can customize how many of these little circles here, also referred to as neurons. So you could have 100 neurons here times 100 layers, and that would be a very deep model. Now, the output layer shape, this is the same for the desired prediction shape. For example, 1 for our housing price prediction problem. Hidden activation is usually ReLU, which is rectified linear unit. Output activation, this is going to be problem specific, but these are some typical values here. The loss function for a regression model is, the default one is usually mean squared error or mean absolute error / Huber loss, so which is a combination of mean absolute and mean squared error. If you have outliers in your data, again, we haven't covered these 4 here. We're going to see what they mean shortly. And then the optimizer, which is a way of how our neural network improves its predictions, is usually going to be stochastic. Oh, that's a fun word to say. Stochastic gradient descent. Stochastic is a fancy word for random. Or the atom optimizer, which is a very good default value. So let's have a look here what this looks like in TensorFlow code. We haven't written any of this, so don't worry if it feels foreign to you. We're going to write a lot of this going forward, but I just want to relate the architecture of a regression model, see what we're going to start working towards. By the end of this module that we're covering, this section, you're going to be able to write these yourself. So let's have a look. This is the input layer. So the input layer is in the blue, so we see the shape is defined here as 3 because we're working with our housing price prediction. The hidden layers is in this other little blue shade here. So these are known as hidden layers. So we've got an input here and then an output here. Remember, all neural networks have some sort of input, some sort of output. Then the hidden layers, in our case, we have 1, 2, 3. And if we look for the neurons per hidden layer, is often this first number. So we have it in green. In our case, we've got 100 neurons in the first hidden layer. We've got 100 neurons in the second hidden layer. And again, the same for the third hidden layer. Now our output layer shape, we can see here in the yellow. This is the same shape as our desired prediction shape. In our case, this would be a great output shape for our housing price prediction. Then we have the hidden activation parameter. In our case, it's the ReLU, which is a rectified linear unit. So that we can set that using the activation parameter. And then for our output activation, which is just simply the output activation function for our output layer, we've decided to set this one as none. And then for our loss function, if we come down here, we've got step 2, which is compiling a model. So this is step 1 is we created a model. Step 2 is we have to compile it in TensorFlow. Again, we're going to be writing a lot of this code going forward. So we define our loss function. This measures how wrong our neural network's predictions are. So when it's learning the relationships between our independent variables and our dependent variables, in other words, the number of bedrooms, bathrooms, and car spaces and the sale prices of our homes, This loss function is going to measure how wrong our neural network's relationships are. And the optimizer here, in our case, we've set it to, which is in the black square here, we've set it to the atom optimizer, is going to inform our neural network how it should improve our patterns to reduce the loss function. So again, if we look at this in the context of our housing price prediction problem, we see we have the input features here, which is going to go into our input shape. They'll pass through the hidden layers, which will learn the patterns between the input features and the output variable. And then it's going to come out into our output layer, which is going to output something like this. And then the loss function is going to tell us, or tell our neural network, how wrong the relationships between these and this is. And then the optimizer will tell our neural network how to improve the patterns it's learning between the input variables and the output variable. And then here, the fit model is telling our model to look at a whole bunch of different examples in the training data for 100 laps of the data. So that's what the epochs variable stands for. Again, a lot of things we haven't covered here, but as I said, we're going to be writing a lot of code. And actually, I think it's about time we did that. So we've looked at some code here. We haven't written code, so we've gone against our rule. If in doubt, write the code. Let's see how we'll create some of this. And yeah, we'll create some data for regression problems. We'll write some code, and we'll get hands-on with neural network regression models. We've covered some of the fundamental principles of regression modeling with TensorFlow, specifically what is a regression problem. But now let's see how we might write some code to actually do that, or to actually work on our own regression problems. So I'm going to start a new web browser here. I'm going to come to colab.research.google.com. I'm going to create a new notebook. Now we'll wait for this to load up. Just going to zoom in here. There we go. Now I'm going to call mine O1 Neural Network Regression with TensorFlow. And I'm going to add the little video tag here. This is the notebook that I'm writing during the videos. If you want the ground truth notebook, so the notebook that I'm getting the information for this video off, remember you can go to the course GitHub, which is github.com/mrdburke/TensorFlow Deep Learning. This will be linked throughout the course. At the moment, while I'm recording this, it's still a work in progress. But if you come here to O1 Neural Network Regression in TensorFlow, you'll have all of the information we're working on in a very succinct manner. So there's a lot more annotations in this one. In the notebook that we work on during the course, this one here, we're going to be focused on writing code. So if you want all the commentary around it, check out the course GitHub, specifically the notebook without the video tag at the end. So I'll just close that. And here we go. So let's write our title in Markdown. So Introduction to Regression with Neural Networks in TensorFlow. Beautiful. I'm going to turn this into Markdown by pressing Command MM on my Mac. Might be Control MM if you're using Windows machine. So we're going to write here, there are many definitions for a regression problem, but in our case, we're going to simplify it. Predicting a numerical variable based on some other combination of variables. Even shorter, predicting a number. That's what we're going to do. We're going to be writing neural network code. Did I spell anything wrong here? Probably. Definitions is wrong. Predicting a number based on some other numbers. Nice and simple. Actually, that's probably a definition for neural networks in general. But this is what we're going to start with. And we had a lecture before that was what we're going to cover, so refer to that one. But let's just get started. We need to get hands-on by, first we're going to need some data. So how about we do that? What should we start with? Import TensorFlow. So we need to import TensorFlow as TF, and then we're going to check our TensorFlow version. So for this course, we need 2 point something, so 2 plus. And you'll notice here that we're not connected to a Colab instance just yet. But the beautiful thing is, as soon as we run a cell, it's going to automatically connect to a Colab instance. So we'll import TensorFlow here. Wonderful. 2.3.0. So this is the version that I'm on. If you're watching this at a later date, you might be on a later version, but as long as you're 2 point something, you should be right for this series of videos. Let's start off by creating some data to view and fit. So we had a look at what is a regression problem before, regression analysis, and it looked something like this. So we have the blue dots could be our data points, and our regression model is this red line through the middle. So that's the relationship that we're trying to learn, right? Between a dependent variable and one or more independent variables. So let's create some data that looks like this. How might we do that? Let's try NumPy as NP, and we'll also import matplotlib.pyplot as PLT. So we need to create the features, which we'll call X. Again, nomenclature for features is generally called X in the form of a capital. So this is NP array. We're going to just create this manually. Maybe we start from my favorite number, 7, or specifically -7, -4, -1. You might be able to work out the pattern of these numbers that I'm creating as well. That's what I want you to start thinking about, is that whenever you're viewing data, before you write a machine learning model or some sort of deep learning model to figure out patterns, see if you can understand them yourself. What's your gut feeling? So NP array, we'll create our labels as well, which is typically defined by Y in a lowercase. So we'll go here, 3.0, 6.0, 9.0. Now, if you were trying to figure out the relationship between X and Y, what might you do? There we go. We've got X and Y. Now, if we want to visualize it, remember one of our other mottos is visualize, visualize, visualize. We're going to see that a lot throughout the course. Boom. Plot.scatter. Okay. We've got a very simple line here. So you could think of X as our independent variables and Y as our dependent variable. If we have a look at our regression analysis little diagram, ours looks something like that, but just this has got many more samples. We're starting nice and simple. So there we go. Now, what might we want to do that? So let's try work out the pattern between X and Y just as it is. So X is -7 where Y is 3, and then X is -4 where Y is 6, and -1, 9, 2, and 12. Are you sensing a relationship here? How might we manipulate X to get Y? Well, I'll tell you the rule I just figured out. Y equals X plus 10. Does this work? X plus 10. Do we get Y? Beautiful. So if we want to go Y equals X plus 10, true, 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 true. Beautiful. So the relationship we would try to get for our neural network to learn is this here. This is the relationship or the function between our X and Y. In other words, our input features and our labels. In Wikipedia terms, our independent variable and our dependent variable. So let's have a look at what our input and output shapes. So if we were to build a model between X and Y, what might be the input and output shapes of our model? If we come back to our Keynote, remember we defined our input shapes for our housing prediction problem or housing pricing prediction problem. If we were to take in these independent variables, number of bedrooms, number of bathrooms, number of garages, so bedroom, bathroom, garage, the shape would be 3, and then the output shape would be 1. And remember, these will vary depending on the problem you're working on. So in our case, our problem, if we just want to predict this simple line here, it varies from the problem we're looking at here. So if we had 3 input variables for 1 output variable here, what might be the shapes of our input and output variables for this problem? let's create a demo tensor for our housing price prediction problem. This is a very, very important point for all the neural networks that you build. So I want you to pay attention to this one. So the house info equals, let's create a tensor. Remember, our input shapes to neural networks, often numerical tensors, but this one we'll just treat it as a string tensor for now. Garage. And now the house price is going to be TF constant 939,700 or something like that. And now let's check out house info and house price. Okay, there's our shape. Beautiful. So what we've done is we've just converted here this demo input and output shape into actual tensors. Wonderful. So the input shape is going to be 3 and the output shape is going to be 1 because we're using the house info to predict the house price. Now in our case, we want to use X to predict Y. So, let's have a think. What might be the input shape? So if we go input shape equals, maybe it's X dot shape, and the output shape equals Y dot shape. Let's check the input shape and the output shape. 8 and 8. Does that make sense? Because really we want to just know what the Y is based on this sample of X. And really we just want to know what the Y is here based on this sample of X. So what if it was just one sample? So if we did X0, we want to use X0 to predict Y0. So -7 to predict 3. And we also want to use X1 to predict Y1. Just like in our housing price demo, we want to use one house to predict the price of one house, or the input features of one house to predict the price of one house. Same for this sample problem. We want to use one input feature of X to predict one Y value. Same again here. So what if we check the shape of this? From this, it seems that our inputs and outputs have no shape. How could that be? I mean, it's because no matter what kind of data we pass to our model, it's going to take an input and return as output some kind of tensor. But in our case, because of our data set, it's only two small lists of numbers here. We're looking at a special kind of tensor. Do you remember when we went over the different types of tensors that you might come into? We're looking at scalars here. Specifically a rank 0, well, scalars is specifically a rank 0 tensor. So if we go x0.ndim, it has 0 dimensions. So that's why it has no shape. So let's take a look at the samples individually. So x0, y0. Wonderful. So in our case, we're trying to predict or build a model that's going to take as input -7 and produce as output 3.0. So this is where you're going to run into a whole bunch of input and output shape trouble, is when you get examples like this that don't really make sense. But how I want you to think about this is we're going to use one X value to predict one Y value. So keep that in mind. And in the next video, we'll see how we might create a model to do so. In the previous video, we created some sample data, so some sample input features, and some sample labels. And what we're trying to do is model the relationship between X and Y, in other words, the relationship between our features and labels. And we checked out our input and output shapes, which are kind of confusing, because when we checked out the shape of our, in our case, NumPy arrays, actually, let's turn these into tensors. How might we do that? Turn our NumPy arrays into tensors. So remember, from our TensorFlow fundamentals section, we can turn NumPy array or NumPy arrays into tensors by just passing them to TensorFlow.constant or TF.constant. And then if we wanted to check the x.shape, y.shape, we'll just print x and y actually. So there we go. Now our NumPy arrays are in the form of tensors. Beautiful. And we got a little confused when we checked the input and the output shape. So let's do it again while they're in tensor form. So input shape equals x0 dot shape and output shape equals y0 dot shape. Input shape, output shape. And we got a little confused because they have no dimension here, because what we're doing is when it has no dimension, it's a scalar value. So it's a single value. But then we figured out by just investigating our data that we want to use one input value to predict one output value. So that's our input and output shapes there. Now, how might we build a model to do that? How might we, not scatter, x, y. How might we build a model to figure out the relationships here? Well, we haven't covered that, so if you don't know the answer to that, that's perfectly fine. But let's start with steps in modeling with TensorFlow. That's what we're going to cover here. So, the first one is number one, is creating a model. In here, you're going to define the input and output layers, as well as the hidden layers of a neural network. And if you're using deep learning, that is, of a deep learning model. Wonderful. Number two, we have to compile a model. We need to define the loss function. In other words, the function which tells our model how wrong it is, and the optimizer. The optimizer tells our model how to improve the patterns it's learning, and evaluation metrics. So what we can use to interpret the performance of our model. Beautiful. And then finally, 3 is fitting a model. So this is letting the model try to find patterns between X and Y, or features and labels. Beautiful. So we have 3 steps here. Now if we come into, we've got a beautiful diagram here, which is steps in modeling with TensorFlow. Whoa, look at that. A beautiful, colorful diagram. Step 1 is we have to get our data ready. So if we were working on an image classification problem to figure out what type of food is in an image, we'd have to turn it into tensors. But in our case, we already have our data in tensors because if we have a look, we've turned X and Y into tensors. So our data is already in tensors. Wonderful. Now, step 2, once our data is in tensors, we can build or pick a pre-trained model to suit our problem. We can use pure TensorFlow or TensorFlow Hub. We'll see that in a later video. So that would be step 1 here, would be creating a model specified to your problem. Wonderful. Then we fit the model to the data and make a prediction. So that would be down here, fitting the model. But actually, in TensorFlow, building or picking a pre-trained model often involves step 1 and 2 are very synergistic with each other, meaning if you do create a model or pick a pre-trained model, once you instantiate it, you basically always have to compile it. That tells TensorFlow that, hey, I've got this model instantiated, I've got it set up, now I'm compiling it, I'm telling you that I'm ready to use it. So then we go on to step 3, is to fit the model. Wonderful, model.fit. We might fit it to the training data. We might let it look at the training data 5 times. And then we have number 4 is evaluate the model. So once the model has found patterns in the training data, we might evaluate our model on the testing data. And then if we keep going, we can improve via experimentation, and then we can save and reload our trained model. But let's go back here. let's see how we might actually go through these 3 steps here. And what I'm going to do, I'm going to turn these into bold so they're just a little bit more pretty. Because that's what we're doing here. We're creating art. So what I might do is set the random seed so we have some reproducibility. tf.random set seed. 42. I'm going to use 42, which is if you're wondering why I'm using 42, it's the answer to the universe. I'll let you look that one up. And then we're going to go number 1. Create a model using the sequential API. You might be wondering what that means, but we'll get into that in a second. I'm going to write the code first. Model equals tf.keras.sequential. And then we're going to open bracket. And then we have, so this is basically saying to TensorFlow, hey, I want to create a model and I want you to sequentially go through the following. We're going to just make this with one layer. tf.keras.layers.dense. We're going to have 1. There we go. You might be wondering why I'm using 1. Because in our case, what do we want to do? We want to build a model to take as input 1 number and predict 1 number. So that's why I have 1 here. We go down. We're going to go step number 2. Compile the model. So model.compile equals loss equals tf.keras.losses.mae. So in our case, we have loss. MAE is short for mean absolute error. So let's have a look. Remember, if you don't know something, mean absolute error. What is this? So in statistics, mean absolute error is a measure of errors between paired observations expressing the same phenomenon. What about, do we have images? Comparison of 2 observations where x1 equals 2, mean absolute error. This is what you're going to come across. You're going to come across a whole bunch of different explanations. But what the best thing to do is to just check them out and see if something catches your eye. So examples of y versus x include comparison of predicted versus observed. Comparisons of predicted versus observed. All right. Subsequent time versus initial time. And one technique of measurement versus an alternative technique of measurement. What if we looked up just the function that we wrote, tf.keras losses.mae? Here we go. Computes the mean absolute error between labels and predictions. Wonderful. So y true, y pred. All right. And there's the function. So it's the mean of the absolute of y minus y pred. So I'm guessing that y prediction is the prediction our model makes, and y true is the actual value it should be. So we make it the absolute value here, so it's a positive number, and then we get the average from that. Okay, so mean absolute error is just saying there's the absolute, and there's the mean. So it's just saying, on average, how wrong are our predictions? Oh, okay. That's a little bit easier than what it first looked like. Now the optimizer is, we're going to set it as tf.keras optimizers.sgd. Now, SGD is short for stochastic gradient descent. Wonderful. Now, again, if you're not sure what SGD is, go, what is stochastic gradient descent? So I'll let you go through those in your own time of what stochastic gradient descent is. But just what you need to know for now is that an optimizer tells our neural network how it should improve. And then we'll go here, and we want metrics is, we're going to use MAE as well. Now, a lot of functions in TensorFlow, if they have a shortcut name, MAE or SGD, you can often use a string variable to define the fact that you want to use that specific function. So in this case, we could remove that and write SGD. But we're going to remove that. There we go. So that's our compile done. And now we're going to fit the model. which is model.fit. And we're going to fit it on X and Y for 5 laps. So this is what the fit function takes. So we create the model, we compile the model, and we fit the model, aka telling our model, look at X and Y and try and figure out the patterns. And you've got 5 opportunities of going through all of the X values and all of the Y values and trying to find those patterns or figure out the relationship. If we set this to 100, we'd say you have 100 opportunities of going through all of X and all of Y. But because we want to keep our experiments nice and short to begin with, we'll only set it to 5. All right. So before we run this, we did say that we use the sequential API. How do we find out what sequential means in TensorFlow? So if we wanted to find out what the docstring of this method here is, oh, there we go. Colab automatically opens it up. But in my case, I'm going to press Shift Command Space as it goes here. So sequential groups a linear stack of layers into a tf.keras.model. Sequential provides training and inference features on this model. All right. So we get an example of how we can create a sequential model. Now, in TensorFlow and Keras, there's 2 different types or 2 main types of creating models. We've used the sequential API here. So we can go TensorFlow, Keras. Now, this is if I already know what the difference is between the sequential and functional API is. That's a little reveal of what we're going to look into. But this is how I'd find out information about TF Keras sequential. I go here. Sequential groups a linear stack of layers into TF Keras model. Now there we go. tf.keras.sequential equals layers equals none. Here's a whole bunch of different guides I could go through to figure it out. I could go through some tutorials if I wanted to. And there's actually, the documentation is showing us a different way. So we could create, this is what I also do sometimes. I just copy the code sample. I come back to my notebook. I copy it here. And then below it, I'm going to write exactly what it writes out here. So model equals tf.keras.sequential. And then I do here model.add.keras.layers.dense 8 input shape. Now this gives me the feeling of writing this actual code. Input shape 16. And then so on, so on. Now I want you to think about, if you've seen this example here, how might we convert our own example into this? So let's try. We'll go, we've got our sample here. We might go model equals tf keras, and again, looking at this one, dot sequential, wonderful. And then model.add, looking at this, we want to put this in there. Model.add tf.keras.layers.dense 1. So there we go. We've just got reproduced the exact same thing here. Now, the reason why I'm showing you this is because in TensorFlow, there are actually a fair few ways to do things. So this is with the sequential API. You can put your layers, you can use the .add method to add them to your sequential model, or you can put them into a list, as we've done here, and add them to your layer. So tf.keras.layers.dense.1 would be the same as adding that there. Does that make sense? If not, that's all right. Have a little bit of a play around, have a practice, check out we'll delete this cell here because we're going to use this methodology for the time being. Have a look at the TensorFlow documentation if you'd like to have a little bit more practice. Rewrite all of this code for yourself. But let's get back into here. We've set up our model here, steps in modeling. We've created a model, we've compiled the model, and it's time to fit our model. So you're ready to run your first neural network of this entire course. I hope you are. So let's try it out. 3, 2, 1. Oh, look at that. So we get a warning here. What does this say? Dense is casting an input tensor from dtype, from float 64 to the layers dtype of float 32, which is new behavior in TensorFlow 2. Okay, the layer has dtype float 32 because it defaults to float x. So we discussed this before. of if you intended to run this layer in float 32, you can safely ignore this warning. If in doubt, this warning is likely only an issue if you are porting a TensorFlow 1.x model to TensorFlow 2. No, we're not doing that. To change all your layers to have dtype float 64 by default, we can set the backend to float 64. How might we just change our layer or our input data to dtype equals float? Because you see how we create it with NumPy? The default data type is float 64. So let's change the dtype to tf float 32. And same again, dtype equals tf float 32. With dtype float 32, not. Or what if we go tf.cast, and then we go pass here, dtype equals float 32, and then we'll do the same here, tf.cast, dtype equals float 32. There we go. We'll change this with dtype float 32. So now we have float 32 tensors. What if we were to run this model again? Remember, this warning was telling us that the layer uses float 32 by default, but originally our input, x and y, were float 64. Let's run this again. Boom, wonderful. So this goes very quickly. So you can see here, this is what the output is when you're going to fit a model, is it tells us this is lap 1 of the data, lap 2 of the data, lap 3, this is how long it took, and this is our loss function, so how wrong our machine learning or our deep neural network is when we're trying to predict x and y. So right now, on average, when our model uses an x value to predict y, it is wrong by 11.5, and then it slowly improves to be wrong by 10.9. And then because we've set our metrics to be the same as the loss function, we get the same output here. So this is loss, this is our evaluation metric. Now, if we wanted to use our machine learning model to make a prediction, let's check out x and y. So right now we have a trained machine learning model. So this is tried to work out the patterns between x and y by doing 5 laps over the data. So let's remind ourselves of what x and y are. There we go. So -7, 3, -4, 6, -1, 9. Now, try and make a prediction using our model. So let's go model.predict. This is how we can make a prediction with our trained model. If we wanted to make a prediction on x equal to 17. So if we had another value on the end here, right, if we added x equals 17 to the end here, what do you think the output should be for y? If you guessed 27, you'd be correct, because that's the pattern between our x and y, is that y equals x plus 10. So let's see what our model learned. Our model predicts that if we had an x value of 17, the y value should be 12.7. Now, that's pretty far off, but as we can see from our loss and MAE values, that actually reflects what our model's training output has shown us here, is that on average, our model predicts something that is basically 11 points off where it should be. So if we wanted to, let's go ypred equals model.predict, have a look at ypred. So this is on average 11 points off where it should be. Ypred plus 11, because I'm getting this value here. What does that give us? 23.7, so it's still off. So, we fit a model. Now, it doesn't find the correct patterns between x and y. So what we might look at doing in the next video is seeing how we can improving our model. So let's check out that in the next video. We finished up the last video with you writing your first neural network with TensorFlow code. Specifically, we stepped through the steps in modeling with TensorFlow. We created a model, we compiled it, and we fit the model to our data. However, Our neural network didn't turn out very well. I mean, we tried to make a prediction on a new piece of X data, and the output was pretty far off where it's supposed to be. You might be thinking, hey Daniel, we kind of stepped through this code relatively quickly without discussing the concepts behind it, and you'd be 100% right with that, but there's a reason for it. If we come to our Keynote, we checked out this slide, Steps of Modeling with TensorFlow. We had a brief look at our workflow, what we're sort of working on throughout this course. We had an even briefer look at the steps in creating a model, compiling a model, and fitting a model, and then, of course, evaluating it. Well, we do have a bit more of an in-depth guide as to the steps in TensorFlow modeling, more specifically talking through the code we wrote. Now, this is an important point I want to emphasize, and it's going to be a theme throughout the rest of the course, is that I would rather you learn the concepts by writing code than by looking and reading a slide. So I'll say that again. I would much rather, I held this slide back because I would much rather you write code than spend time reading slides. So if we got the steps here, number 1, construct or import a pre-trained model relevant to your problem, compile the model. In the compilation, we define the loss, we define the optimizer, we define the metrics. Number 3, we fit the model to the training data so that it can discover patterns. Epochs is how many times the model will look at the training examples. And number 4 is evaluate the model on the test data. Now, these steps don't necessarily come in this order all the time, but generally, you can adapt them to whatever problem you're working on. So with that being said, we've built our first neural network with TensorFlow, but it didn't perform very well. Let's have a look at how we might improve our model. So I want you to take a guess. We've got 3 steps. We're creating the model, compiling it, and fitting it. Based on what you've seen so far throughout the course, what do you think are some steps that we could do to improve our model's performance? Now, if you're not sure, that is completely fine. I just want you to have a think about it before we start going through it. Remember how we define a model? It's got a number of different hidden layers. It's got a number of different hidden neurons in each of those layers. And we fit it for 5 epochs, which means it looks at the data 5 times. So they're just a few little hints, but let's get on to here. If we wanted to improve our model, let's take a look at the 3 steps we used before to create a model. I want you to think about this, is that when we create a model using these 3 steps, we can actually improve a model by altering how we went through each of these. So when we create a model, we can improve it via steps in the creation. When we compile a model, we can improve it by steps in the compiling. And when we fit a model, we can improve the model by steps in the fit method. So let's write that down. We come here, we can improve our model by altering the steps we took to create a model. So number 1 is creating a model. If we wanted to improve our model here we might add more layers, increase the number of hidden units, also called neurons, within each of those layers, within each of the hidden layers. And we might change the activation functions of each layer. Number 2, when we're compiling a model, here we might, ear. I've written ear up here. Ear, we might. Here, we might change the optimization function, or perhaps the learning rate. We haven't looked at this parameter yet, or hyperparameter, should I say, but we will in a second. Learning rate of said optimization function. And number 3, when we're fitting a model, here we might fit a model for more epochs. In other words, let our model look at the training data more times. So leave it training for longer. or on more data. So give the model more examples to learn from. Now, this is a very brief overview of how we might improve our model. We do have a dedicated slide for looking at this. So improving a model from our model's perspective, that is. So we might start with a smaller model, and then we might build it into a larger model. Now, before we continue with this, we've discussed the concepts of improving our model. Now, what I would rather do, instead of going through each of these one by one, is let's start to code this larger model. So we'll do that in the next video. I'll see you there. Welcome back. We finished the last video by looking at this slide here, comparing our smaller model to a larger model. Now, there's a few key differences between these two. You'll notice in step 1, here the larger model has 3 hidden layers. Well, a total of 4 layers, but we've added 3 layers here to the beginning. Whereas this one only has 1 layer. This larger model has 4 layers, so we've increased the number of hidden layers. The number of hidden units, or the neurons, in each of the hidden layers is 100, whereas this one only has 1 hidden layer with 1 hidden neuron. And then if we come down here to step 2, compile the model, let's have a look. What's the main difference here? The main difference, the loss is the same, but we've changed the optimization function from SGD to Atom. So if you're not sure what the Atom optimizer is, just for now, remember, the optimizer tells our model how it can improve. And the Atom optimizer is a very common and very useful optimizer. So this will often be the default optimizer that you start with. We've also got a LR parameter here in our optimizer where this one doesn't have it. So LR is short for learning rate. In other words, when our Atom optimizer tells our model how to improve, how much should it improve each step? So the higher the learning rate, the more the Atom optimizer pushes the model to improve. Whereas the lower the learning rate, so say for example, if we had more zeros here, the lower the learning rate, the smaller the steps our optimizer tells our neural network to take to improve. And now finally, in fit the model, we see here, we've got fit X-train subset, Y-train subset, whereas here we've got X-train full, Y-train full, and epochs equals 100 versus epochs equals 5. So what you'll often do with your datasets is split them into a subset, say for example 10% of your training data, rather than the full data set. So you can run many smaller models to make sure that they work before upgrading to a larger model. Because this larger model here may take more time to run or time to figure out patterns in the data set than our smaller model. And what do we want to do as data analysts and machine learning engineers is we want to run as many experiments as possible to figure out what doesn't work before we increase the parameters of our experiments and try run some larger models. So let's see. We're going to do it one step at a time. Let's recreate this larger model, but as I said, we'll start it. We won't change every single thing. We won't change the number of layers to begin with. We won't change the optimizer. Let's just see if we can improve it by increasing the number of epochs. So this is a very similar model to what we've built. Let's do one upgrade to it by letting it look at the training data. Rather than 5 times, let's let it look at the training data 100 times. So if we come back, so let's rebuild our model. So number 1 is create the model. Again, you could scroll up if you wanted to, but I'm just going to recreate the same model we created before, tf.keras.sequential. And if you can't remember each of the 3 steps, so create the model, compile the model, fit the model, don't worry, because this may be the first time, or very likely is the first time you've ever written this code. However, by the end of the course, after you've built, I'm not even sure how many we're going to build, I think it's well over 100. Once you've built 100 plus models, these steps you'll start to be very familiar with. And even now, like I've built probably thousands of these, I still make mistakes and I still get things wrong and have to tweak them. So what we've done is we've created the model, which is just the exact same step we did before. It's a sequential model. meaning it's going to run from bottom to top. So you're going to pass through this one layer. We've defined our loss function as mean absolute error. We've defined our optimizer as stochastic gradient descent. And then here, we're going to define our evaluation metric as mean absolute error as well. And now, this time, in step 3, fit the model, we're going to go, this time, we'll train for longer. We go model.fit x, y, epochs equals 100. So this is the exact same model as we created before up here. The only difference is here, we've changed epochs from 5 to 100. So remember, the final loss and the final MAE for this after 5 epochs was around about 11. So let's just remember 11. That's the number we're trying to get lower. That's what we're trying to improve by increasing the number of epochs. So let's try run this model. You should be very excited too. Oh, see what I mean? I've written thousands of these, but I still get it wrong. It's optimizers, not optimizer. I missed the S on the end. Run it again. Beautiful, look at that. Oh, nice and quick. How exciting is that? Epoch. So if we come down here, scrolling everywhere, right up to the top. So we see here, we've got epoch 1 out of 100. And then this is where our previous model stopped after 5 epochs. So again, the error is very similar. It's very close to 11. But then watch, as we increase the number of epochs, so 6, 7, 8, 9, 10, that's double, has the loss gone down? It has. So we're getting closer to 10 after 10 epochs. And now let's keep going down to 50 epochs. Here we go, 50, so about halfway through. Oh, we're almost at 7 loss. Okay, let's keep going all the way down. And we get to 100. Wow. Okay, so we're just below 7 here. This is amazing. So just by altering one hyperparameter of our model, specifically the number of epochs it's gone through, we've decreased our loss and our MAE, mean absolute error, from around about 11 to around about 7. So let's see what our prediction is going to be. So remind ourselves of the data. So we have X and Y. What did we try to make a prediction on before? We tried to make a prediction if we added another value here, 17, which should come out to be about 27, based on the other values of X and the other values of Y. Let's see if our model's prediction has improved. So we go here, model. If we want to make a prediction, predict, we pass it 17. The predict data has to be in the same format as the training data here, so it's in a float there. And ready? 3, 2, 1. Boom. Oh, yes, look at that. So much closer. 29.73 to what it actually should have been is 27. So much better than before. What did we get before? Let's come up here. We got 12 before. So, which is, it should have been 27. That's about 15 off. So we've reduced our error to be about 3 off. How cool is that? By just tweaking one little parameter of our smaller model and turning it closer towards being a larger model. Now, what if we were to alter another one of our model's parameters? What I'll do, before I do that, before I write the code, I'd like you to give it a try. So you see here, we've got our model code here. I'd like you to rewrite this cell. However, this time, keep the number of epochs at 100. I want you to choose one thing from this larger model slide here. It could be the optimizer to change. You could add in here one hidden layer, or you could add in all 3 to the creating a model step. But I'd like you to try one change. And then in the next video, I'm going to go through one of the changes. I'm not going to let you know which one. But just try one of these for yourself and see if it improves our model's results. Just go through the exact same steps that we've done here, creating a model, compiling the model, fitting the model, except this time, maybe add in a hidden layer here, tf_kerers ... I'll let you complete that, or change the optimizer to Atom and see what happens. So give that a try. And in the next video, I've got to decide what change I'm going to make, and we'll see if we can improve our prediction even further. Welcome back. In the last video, we saw how we could improve our model's prediction capabilities by just increasing the number of times it looked at the training data. Now, an important point to note here is that although we've seen a couple of ways of how we can improve our model, it's not always the case that any one of these parameters here, or hyperparameters, will result in an improvement. So I also issued you the challenge to see if you could change one of the hyperparameters here in creating the model or compiling the model and fitting it to the data, keeping the number of epochs the same, and seeing what happens. So depending on what you tried, it might have improved the model, might not have, but let's see if we can make another change to improve our model. So now I'm going to write some code to get even closer towards our smaller model becoming our larger model. My change, I'm going to choose by adding an extra layer here. So rather than 3 layers, I'm going to make the smallest change possible. And this is what I'd like you to think about as well going forward, is that you don't necessarily always have to add 3 hidden layers or add 10 hidden layers. You can just adjust one thing on your model, try it out, and see how it goes. In fact, that's how I would like you to run your experiments, is many, many small changes rather than always doing extremely large changes. Because otherwise, if you do too big of a change, you might not be sure what caused the improvement or non-improvement of your model. So let's go here. Let's try, I'll keep that output there. So this time, create the model, this time with an extra hidden layer with 100 hidden units. So let's go here. Model equals tf.keras.sequential. Open a list. I like to come back right to the start here and tab in tf.keras.layers. Now 100, and the activation on this one is going to be ReLU. We'll have a look at what that is in a later video, but if you want to test yourself at researching, have a go at just searching what is ReLU activation, or however you want to pronounce that. So tf.keras.layers, dense 1, beautiful. Now we're going to, number 2 is compile the model. Whenever you create a model in TensorFlow, you have to compile it. Compile the model, model.compile. The loss is going to be tf.keras losses MAE, and the optimizer is going to be tf.keras optimizers.sgd. Now I just want to show you a little tidbit to prove that it works, is if you didn't want to write this out, you can change this to be MAE. That should work. Fingers crossed. And then metrics is going to be, metrics has to be within a list as well. Metrics is going to be MAE. Now 3 is going to be fit the model. We've got our data, model.fit, x, y. So the features come first, as you see here, model.fit. This is the doc string. X equals our features, y equals the labels. And then we're going to go epochs equals 100. So the only difference we've made to this model above is we've added this hidden layer here. So that's the one change we've made. So let's see how it goes. Shift and enter. Beautiful. Oh, would you look at that? Right from the start. Remember our first model, after 5 epochs, had an error of about 11? Well, this one's hitting about 10. But then after 10 epochs, it's already just above, it's already below our other model without a hidden layer. So this one finished off with a loss of just around about 7 and an MAE of around about 7 as well. Remember, mean absolute error is about, on average, how wrong are our model's predictions. So if we come down here, what did we finish up with here? Oh my goodness, how cool is that? Our next model, by just tweaking one little thing, by just adding an extra hidden layer here, that's all the change that we made, we've basically cut our MAE and our loss in half. So let's remind ourselves of the data. So we have X, Y. Remember, the little prediction test that we've been trying to make is if we had another X over here, which was 17, just increasing in the same way that these numbers are increasing. Let's try to make a prediction. So we want model.predict, and we want to make a prediction on number 17 to see what the Y value might have been. Oh, okay. So it should be 27. But now we're seeing it's 31.2. If we come up here, it seems that our previous model did better. It got 29.7, which is closer to the actual value it should be, 27, because y equals x plus 10. I wonder why that is, even though our loss and MAE are lower. What it might be doing is our model is overfitting, meaning it's learning the training data too well. So it's learning the patterns between X and Y far too well. So when it sees a new X, it's just relating it back to what it knows. And the error that it's producing during training is not a really valid representation of what it's actually doing. See, the real way we evaluate our machine learning models is not the metrics it gives us from the training data. It's the metrics we get from data it's never seen before. Now, if we come back to our improving a model section, we saw a number of different concepts here, but let's step back through them. And I want to emphasize, as we've seen in practice, not all of them lead to an improvement of our model. And as we'll see going forward, sometimes the metrics you see here during training aren't necessarily representative of what you'll see for data the model hasn't seen before. So we're going to cover that in a little bit, but I just want to go back and step through some of the concepts that we've looked at for improving a deep model. So the first one is adding layers. We just saw that. We added one layer, and we got improved metrics during training. So when I say during training, it's when you call the fit function. However, in practice, trying to predict on a sample our model hadn't seen before, the results weren't as good as when we didn't add an extra layer. Another way to improve a model is to increase the number of hidden units. We also saw that. If we come back to our model here, we could build another one by going 50 instead of 100, and we see how this goes. So we'll train the model. That experiment ran nice and quick. Again, we're getting a fairly low loss and a fairly low mean absolute error, but the real evaluation is on a sample that the model hasn't seen before. And we get an even worse value. So we come back here. Again, this is just a great example of how improving a model, or the steps that we're looking at here, don't always result in an improvement of our model. Another way is to change the activation function, which we've tried here. So by default, if we have a look at our docstring, let's see this in practice. Activation, if we go here, get the docstring, the activation is none by default. So what if we just did that? None. And we run. What do we get here? Okay, so we get a slightly higher loss value than before and a slightly higher MAE, but again, those are just metrics during training. We want to evaluate our model on a sample that it hasn't seen. Oh, we're getting closer. 29.5. That's strange. We've reduced the number of hidden units and taken away an activation function, and we're seeing an improvement. We come here, change the optimization function. So in this example of the larger model, we're using the Atom optimizer rather than SGD. So let's go back to our code. And how about we change this from SGD to Atom, and we run it again. Oh, so we get a slightly higher loss than before compared to using SGD, but let's remind ourselves of the data. The training data we already have labels for. So what if we had a new sample that was 17? We want to figure out its label, make a prediction. 31, okay, so it's worse again. Change the learning rate. All right, so we have Adam and it has a parameter LR. The learning rate is, if the optimizer tells our model how it should improve, the learning rate tells it by how much. So Adam's learning rate, by default, Command-Shift-Enter, is 0.001. So how about we increase this? We'll increase it by 10. And for this function here, learning underscore rate can be learning underscore rate, or it can be the abbreviation LR. So let's run this again. Oh, wow. Look at that. Our loss and MAE are barely even 1. So theoretically, this model should be really good. Oh, 26.2. That's our best model so far. Because remember, predicting on 17, the ideal value should be 27. So in our case, adjusting the learning rate of our optimizer has resulted in the best change so far. So that's an important point. I want you to keep these things in your mind as we go through. And again, if you've only just experienced this for the first time, I'll give you a little hint. The learning rate is potentially the most important hyperparameter you can change on all of your neural networks. So just keep that in mind going forward. Don't worry too much about it now, but just if you want to take one note from this slide, just write down the learning rate is the most important hyperparameter of many different neural networks. So let's go here. So fitting on more data. So in this case, we have X-trained subset and X-trained full. Well, in our case, we don't actually have more data than X and Y. So maybe that's our next experiment to try, is creating a larger data set. So for now, we only have 8 samples. So in practice, you'll probably have a lot more samples when you're building your neural networks. Let's come back. We've got one more, is fitting for longer. Now, this is the first one we tried, and it's actually probably one of the most easiest to try because we just adjust this from 5 to 100. So now we've seen a few different ways to improve our models and fit them to the training data. Let's have a look in the next video. We're going to have a look at a probably just as important as fitting a model to data is evaluating a model's performance. So we've seen here our test example of trying to make a prediction on a sample the model's never seen before. And we keep getting this different number, but how exactly do we tell how good our model's predictions are, or how good the patterns it's learned or the relationships that it's learned between X and Y? Let's check that out in the next video. In the previous video, we checked out a whole bunch of different ways of how we can improve our model. We even tried a few of them, well, most of them actually. We adjusted the number of hidden layers, we changed the optimizer, we changed the learning rate, and we saw that the learning rate actually had probably the biggest influence on how our model performed. And we changed the number of times our models look at the data by altering the epochs. And in practice, this is actually a fairly common workflow. So let's write this down. In practice, a typical workflow you'll go through when building neural networks is we'll start off with build a model and then fit it, evaluate it, and then tweak a model, fit it, evaluate it, and then tweak a model, fit it, evaluate it. Yeah. And now, looking at this, you might think, well, have we actually done this? And the good news is we have. Well, that's just what we went through in the previous video. We created a model, we compiled it, and then we fit it, and then we had a look at the things that we can tweak in our models. We tried adding a layer, so we tweaked our model, we fit it, and then we evaluated it. We tried increasing the number of hidden units, then we fit it, then we evaluated it. We tried changing the activation function, the optimization function, the learning rate. We didn't try this, fitting on more data, but we're going to see that in this video or maybe the next one. And then we tried fitting for longer by increasing the number of epochs. And because you can alter each of these, they're referred to as hyperparameters. Remember, a hyperparameter is like a dial on your neural network that you can adjust to see how it improves. whereas a parameter is usually the patterns a neural network learns. So these are the things that we don't code ourselves. So let's go back. Let's see some other ways for evaluating our model. We tried by making a prediction on an example the model hadn't seen before, but what are some other options that we have? Well, when it comes to evaluation, there are 3 words you should memorize. When we're building models, you want to experiment, experiment, experiment. But when we're evaluating models, it's visualize, visualize, visualize. So that's the most important step when we're evaluating our models. Now, what should we visualize? So, it's a good idea. What I mean by visualize, we'll see in a second. Visualize, but you can probably guess. It means when we're looking at things like this, it can be hard to really understand what's going on. But when we put them in a way that we can visually see what's going on, so we might visualize the data. So ask ourselves, what data are we working with? What does it look like? We might also visualize the model itself. What does our model look like? We might visualize the training of a model. So how does a model perform while it learns? And we also might visualize the predictions. We've done this one of the model. How do the predictions of a model line up against the ground truth? The original labels. We tried this one. So this is lining up this prediction here against what it should actually be. So if we try to predict on 17, that's our x value. We know that y equals x plus 10, so it should be 27. Let's really dig into these steps here a bit further by working on a little bit of a larger problem, which is going to suit this step here, so fitting on more data. But first, we'll need to make a bigger data set. And we can do that. Let's set up another x. We'll use TF range to create a range of numbers between 100, negative 100, and 100 with a step of 4. Let's see what this looks like. Beautiful. So we have 50 numbers here that start from negative 100 and increase by 4 all the way up to 96 because the maximum was 100. So 50, how many did we have in our previous x? Oh, it's not saved up here. There we go. So 8. So we got 5 times as much data. That's a good amount for now. And to do so, we're going to need to make labels for the data set. So y can just equal x plus 10. This is the formula we want our model to learn. This is a pattern we want our model to learn. Now let's have a look at y, just as before. There we go. Negative 90. Yep, negative 100 plus 10 is negative 90, all the way up to 106. So we had the same shape. So one y value for every x value. Beautiful. And now, what should we do? So it's a good idea to visualize the data. All right. So let's visualize the data. What we might do is create a plot. So import matplotlib.pyplot as PLT. Google Colab completes that for us. So plt.plot x, y. What does this look like? Oh, wonderful. How about we get that in a scatter plot? I think that's a better plot for this type of data. Yep, we should have dots there. Now, before we trained our model on x and y, and then we evaluated it on a sample our model hadn't seen before. Now, this is one of the most important concepts in machine learning and deep learning in general. And it's probably better explained using 3 sets. So before we get into visualizing the data, the model itself, the training of a model, and the predictions of a model, and even further into evaluating our model, let's take a look at the concept of the 3 sets. Now, if you're familiar with machine learning, you may already know what the 3 sets are. And so I would like you to apply your knowledge of the 3 sets And actually, we're probably only going to use two sets. So split X and Y into a training and a test set, only if you're familiar with it. If not, just go straight into the next video. If you are familiar with it, split X and Y into an 80% training and a 20% test set. We'll see how to do that in the next video. Welcome back. In the last video, we touched upon the concept of the three sets. So let's dig into what I mean by that. So go here. Now, in practice, in machine learning, you're often not going to fit and evaluate on the same data set. And what I mean by that is what we did up here. We started with X and Y, and we just fit the model to all of the data in one hit. And then we had to evaluate on our own custom sample. Whereas when you actually work on machine learning problems, you're often going to have three different sets of data. You're going to have the training set. So the model learns from this data. Now this is typically, depending on what problem you're working on, typically 70 to 80% of the total data you have available. And then we want a validation set. So the model gets tuned on this data. So this is where you would tweak different things. So if we come back up to here and we built a model, we fit it, we evaluated it, then we tweaked it. So say changing the number of hidden layers or changing the optimizer, you'll often test how these tweaks affected your model's performance on the validation set. So this is typically 10 to 15% of the data available. Again, this will generally depend on how much data you have. And then finally, you have the test set. So the model gets evaluated on this data to test what it has learned. This set is typically 10 to 15% of the total data available. So if you had a go at creating your own training and test set, you might have split it. I think I said 80 and 20%. So that's another valid training and test split. If you are going to drop one of these sets, usually you'll get rid of the validation set and you'll only have a training set and a test set. Again, will depend on how much data you have, will depend on the experiments you're running, but we've spent enough time talking about these. Let's get into coding them up. So here, if you want another analogy, you've got the slide here. We have three data sets, which is possibly the most important concept in machine learning, is to have the training set, which could be, if you were studying at university, your course materials, so the things you learn throughout the semester. The validation set is the practice exam, and the test set is your final exam to evaluate the knowledge you learned throughout the semester. And what we're going for here with the three data sets, the training, validation, and test set, is generalization. So this is the ideal state we want our machine learning model or deep learning model to be in, is the ability for a machine learning model to perform well on data it hasn't seen before. So if you've learned well the course materials throughout the university semester, you should be able to perform well on the final exam. So something you haven't seen before, if you've learned them well. Now, this is exactly what we want for our machine learning models to do, is we want them to learn patterns on the training set so that it can perform well on samples that it has never seen before. In other words, perform well on its final exam. So let's go back. Let's see how we might code these in practice. So check the length of how many samples we have. So len x, this is the data we're working with. We created this just before. By x is TF range, negative 100 to 100. Wonderful. Now, knowing this, we're going to skip our validation set for now. We'll see it later, but because we only have a relatively small sample, 50 is pretty small in the world of deep learning. What's a large one? Well, again, I would say minimum 100 plus samples for deep learning, but we'll see in future videos different sizes of samples. Now, the training set is typically 70 to 80% of the total data we have available. Why don't we use 80? And that means we're going to create a test set. So in other words, the final exam of 20% of the total data available. So how might we do that? Well, we can go here, split the data into train and test sets. Xtrain, you'll often see, or this is going to be the notation for a training data set throughout the course, is just with the train tag after. This is very common in practice. Sometimes you'll see something like train data equals this. They usually just mean similar things, and the same for xtest equals or test data equals. So just going forward, if you see different variable names for training and test data, they're often the same thing. Different ways of representing the same thing. And then we'll go xtest. So this will be the training data. So we want the first, because we're working with 50 samples, we want the first 40 training samples. This is 80% of the data. Wonderful. And then xtest is going to be the last 10 samples. So last 10 testing samples. 20% of the data. Beautiful. And here we'll create ytrain as well, just in the same format. And we'll also create ytrain here. Oh, we've got a space there. Oh, we've got a space there too. Y40. Wonderful. And we can have a look at length of xtrain and len xtest. So this should be 40 and 10 respectively. Beautiful. So what we've done is we've created a training data set and a test data set. We've also got ytrain, which are the training labels, and ytest, which are the test labels. Ytest is not defined. There we go. See? We're catching errors together. Beautiful. So we've got training features, testing features, training labels, testing labels. Now, what should we do? How about we go back to what our steps are in evaluating? So when it comes to evaluating, we should remember 3 words: visualize, visualize, visualize. Wonderful. That's our data evaluation motto. It's a good idea to visualize the data. All right. Well, we did that before we split our data into training and test. But now let's visualize our data split into training and test samples. So how about we go here, visualizing the data. And we'll go, now we've got our data in training and test sets. Let's visualize it again. Now, if you're wondering what I'm putting here, when I write text in Colab notebooks or in Jupyter notebooks, depending on what you're using, I often write like text cells. These are just kind of notes to myself. Or if I had to share this notebook with someone else, it's information so they know what's going on, kind of like a comment, but just in a text format that's easier to understand. So that was a little bit of an aside. Let's write some code. So we want to set up a matplotlib figure, because this time we're going to be plotting 2 samples of data, our training and test. So 10.7 is my favorite plot size. So plot training data in, what's a good color? Blue. Plot scatter. We're going to go xtrain first. So we need to plot xtrain and ytrain. We can use the C parameter of plot to set as B for blue. And then we're going to label it with training data. Wonderful. And now we're going to plot test data in my favorite color, green. Plot scatter, xtest, ytest. We're going to set the color to G for green. And we'll set a label as testing data. Beautiful. And we want to show a legend so we can tell the different data apart. And we'll put this little semicolon at the end so we don't get the matplotlib output. Shift and enter. What does this look like? Ho-ho! There we go. We've got a very similar plot to just above. So this one here. Except now we have our training data in blue and our testing data in green. So anytime you can visualize your data, your model, your anything, it's a good idea. So that way it's much easier to understand. Well, in my case, I find looking at something like this much easier to understand than looking at something like this. All these numbers in a tensor. So in some cases, you won't be able to plot your data if you've got more dimensions than just X and Y. Sorry, X there, Y there. Now, what are we going to do? Referring back to our concept of 3 data sets, in our case, we haven't got a validation set. We've got a training set, which is the blue, and the test set, which is the green. So what we want to do is build a neural network to take in the training data here, to learn the relationship between X and Y, and then we want to feed in, we want our model to learn the relationship in the training data so that it can predict our test data. So if we fed it in the X values of our test data, we want our model to be able to predict the Y values, so where this green line should be. So now we've visualized our data in our training and test sets, let's build a model in the next video to figure out the patterns in the training data so we can make predictions on the testing data. Welcome back. In the last video, we split our data into training and test sets. And then we had a go at, did I spell that right? Nope, again, another spelling mistake. Plenty of them throughout the course. We had a go at visualizing our data, more specifically comparing our training data to the testing data. And we want our model to learn on the training data, and we want our model to be able to predict the testing data. In other words, given X, what's the Y value? So let's have a look at how to build a neural network for our data. Now, we've actually already done this. So if we scroll back up, we built a neural network very similar to what we need right up here. So let's recreate something like this. Nice and simple neural network, one layer, and we'll create it, compile it, and fit it. We'll come back down. Beautiful. So step 1, I told you we're going to get lots of practice creating a model. Create a model. So model equals TF, Keras, sequential. And then we'll put in one layer, TF Keras, layers, dense, one hidden unit, because remember, where our X and Y vectors, or tensors, we're using one X value to predict one Y value, hence why our dense layer has one hidden unit. 2, we're going to compile the model, model.compile. We need to set a loss function, TF Keras losses.mae. And we're going to set an optimizer, which is telling our model how it should improve. Optimizers, SGD, stochastic gradient descent. And we're going to set the metrics to be MAE. Wonderful. Number 3 is fit the model. I'm going to do model.fit on xtrain. This time is different. We want to fit on the training data only for, let's go 100 epochs. So notice here, the important point, we're fitting on the training data, which is this blue line here. So we want our model to learn the patterns in this training data to be able to predict the patterns in the test data. So before we fit the model, I'm going to comment out this line, and I'm going to hit Shift and Enter. I'm going to instantiate our model here. Now, because what I want us to have a look at is visualizing the model. So we can get an idea of what our model looks like before we've even run it by running model.summary. Oh, what happened here? A value error. This model has not yet been built. Oh, why is that? Build the model first by calling build or calling fit with some data, or specify an input shape argument in the first layers for an automatic build. Now, you might see why I commented out this line. I did this on purpose because I wanted you to see this error. So build the model first by calling .build. So we could go model.build, and we see what that might do. So builds the model based on input shapes received. We could define the input shape there. So that's one option. That's the first one. You could try that out for yourself. Or we could specify an input shape argument in the first layers for an automatic build. So with that in mind, let's see how let's create a model which builds automatically by defining the input shape argument in the first layer. Let's see what that might look like, because this is something you'll do quite often in practice, is defining the input shape. Usually your neural networks can determine the input shape. So this is what I mean by input shape, is this parameter here, input shape. Usually they can figure it out, the input shape, on their own. However, sometimes you'll need to manually define it, depending on what problem you're working on. So let's see how we might do that. So we'll set the random seed. So TF random set seed for as much reproducibility as we can. So we'll create a model. This is just the same as above. And we're going to go model equals TF Keras sequential. Remember, a sequential model just runs from top to bottom. We're going to go TF Keras layers dense 1. Now here's what we're going to do. The input shape argument, we need to define that. So how might we find the input shape? Remember, what are we trying to do? We're trying to predict y based on x. So what is the shape of the data that we're passing our model? X.shape. 50, but we want just one sample of x.shape. It's a scalar value. So what if we do, what is x0 and y0? What do they look like again? They're just one number. So in our case, the input shape will be 1, because we're passing it one number to predict one number. So there we go. We've specified the input shape argument. Now, again, the shape might be different depending on the input tensor you're passing in. You might have 3 different variables. So you could pass the input shape as 3. But for our case, we have one input for one output. That's what we're after. Now, we might go, number 2 is compile the model. Model.compile loss equals TF Keras losses MAE optimizer equals TF Keras optimizers dot SGD stochastic gradient descent metrics equals mean absolute error. So if we run this, just the same model we've created before. This is also the same as above. Now let's check out our model.summary. Whoa. Okay, we've got a few things going on here. So calling .summary on our model shows us the layers that it contains, the output shape, and the number of parameters of each layer. So the output shape here is, remember, we want one input for one output. So the output of 1, that makes sense. The layer here is a type dense. So another word for dense is fully connected. So if we go here, fully connected layer, images, what this means in a fully connected layer is that all of the neurons here connected to all of the neurons in the next layer. So that's what fully connected means. And in TensorFlow, a fully connected layer, when you see that, is the same as a dense layer. So dense is just another word for dense connections, if you see all those connections there. And then we've got parameter numbers here. Now, there's a few different things here. We've got total params, trainable params, non-trainable params. So let's define what each of these are. So the total params is total number, as you might have guessed, of parameters in the model. These are the patterns that the model is going to learn. So remember when we had a look at our overview of a neural network, it creates tensors of different values, so patterns. The total number of parameters are how many different patterns our model is going to try and learn within the relationship between, where's our X and Y data? Here. the relationship between our X and Y data. So we come down, and the trainable parameters, these are the parameters, the patterns, the model can update as it trains. So in our case, the total number of parameters here, 2, is equal to the trainable parameters. That means all the parameters in the model are trainable, so they can be updated. You might be wondering, when is ever total params different to trainable params and different to non-trainable params? Well, later on in the course, when we import a model that has already learned patterns in data, what we might do is freeze those learned patterns. So in that case, it might have a whole bunch of non-trainable parameters because we want that model that has already learned on data to keep its existing patterns. We just want to train a few parameters and apply it to our own problem. So let's write this down. Non-trainable params. So these parameters aren't updated during training. This is typical, as we discussed, when you bring in already learned patterns or parameters from other models during transfer learning. We haven't covered transfer learning yet, but we will in a future video. So this is a little bit of an overview of what you get of calling .summary. Now, if you want to have a look at what the actual parameters are in a dense layer, you're going to probably find something called a weights matrix and a bias vector. So if we go here, neural network, weights, and biases. Here we go. Fundamentals of neural networks on weights and biases. So if we look at this, basic neural network structure. So within our hidden layer, here, we've got hidden layer 1, hidden layer 2, hidden layer 3. We have a whole bunch of different parameters. Where's the weights and biases metric? There's a lot of good stuff going on here. Weights and biases. This is the type of research that you're going to have to do. Maybe that's not the best article, but weights and biases is a great website. Here we go, neural networks, biases, and weights. We'll try another one. Or I got a better question. So here's an example of how to do better research. Is what were we actually looking for? Now I gave away there that it's a weights matrix and a bias vector. But what were we actually looking for to begin with? We don't know what the trainable params are. So if we search, what are the trainable params in a neural network? Learnable parameters. Here we go. Trainable params. Much better question. So if we come back here, this is an example of how to rephrase what you're looking for to find out in a better way. So if we come here, learnable parameters, Keras, Python Deep Learning, trainable params. There's a video there. Have we got here? Model.summary. There we go. Trainable params. This model has far more, 2,515. There we go. If you recall from that episode in our first convolutional layer, we haven't looked at convolutional layers yet, giving us a total of 2,515 learnable parameters. I'll leave you to do some more research here, but that's a great way to phrase a question. I have an external resource for you here while we're at it. So this is one of my favorites. We'll create the resource emoji. Resource. If you want to learn what the actual parameters are here that's going on, remember, we're focused on writing this code. If you want to learn what's going on in the background, I recommend this resource. One, you could ask a question like this to Google, or you could go to this resource for a more in-depth overview of the trainable parameters within a layer. So this will be one of the extra curriculum for this section. Check out MIT's Introduction to Deep Learning video. So we go MIT Introduction to Deep Learning. And there's a full-blown course. Here we go, Introduction to Deep Learning, intro to deeplearning.com. I'll leave this video, by the way, in the resources section. So intro to deep learning. Oh, they might be uploading it. Oh, it's a 2021. Look at that. So this is the video I'm talking about. By the time you watch this course, they may have the 2021 version. I will share the most relevant one to the course. So this is intro to deep learning. If you want to learn what's going on behind the code, so the trainable params here, you can find out in that video. Otherwise, I got an exercise for you before the next video. In this course, oh, dancing emoji. You can dance if you want, but here's your exercise. Exercise. So try playing around with the number of hidden units in the dense layer, and then see how that affects the number of parameters, total and trainable, by calling model.summary. I'll give you a demo. So if we were to change this from 1 to 3, shift and enter, and then hit model summary, look what changes, 3. So that gives me an inkling that there's 2 trainable parameters per hidden unit. That's all I'm going to let you know for now, because I want you to have a go at going through an external resource, as well as adjusting the hidden units on your own and seeing what comes out. For now, all you need to do is think about these parameters as they are learnable patterns in the data we're working with. So with that being said, let's fit our model to the training data. Let's fit our model to the training data. We can do this by going model.fit. We commented this out before, actually. So just the exact same thing here. We can call that here xtrain, ytrain. Epochs equals 100. And I'm going to set a little parameter here called verbose equals 0. Remember, how can we check what that does? Verbose equals 1 by default. What does verbose do here? What does it say? Epochs verbose. 0, 1, or 2 for verbosity mode. 0 equals silent, so that means there will be no output. Progress bar, 1, that's default. Note that the progress bar is not particularly useful when logged to a file. So verbose equals 2 is recommended when not running interactively. So verbose equals 0. Oh, what happened there? We didn't even get any outputs. Because we set verbose to 0. If we set it to 1, we can watch our model train. Look at that! We'll set it back to 0. Now remember, because we're running this continually, every time we call fit, it's going to fit for an extra 100 epochs. So we've actually just fit our model for 200 total epochs. Now if we call that again, that's 300 total epochs because we've called 100 3 times. To reset that, we'd have to go up here, reinstantiate our model, get the summary. I might change this back to 1. Model.summary, and then we're going to fit it, and then we're going to leave it at that, and we'll continue on in the next video. Welcome back. We finished the last video by fitting our model to the training data for 100 epochs. We set verbose equal to 0 so we don't get any output. Now, I did also set a little exercise here. Try playing around with the number of hidden units in the dense layer and see how that affects the number of parameters, total and trainable, by calling model.summary. So let's try that out. If we call, or we'll just get a summary of our model. So model.summary. Okay, and notice this number here continually increases because we've created a total of 14 sequential models so far, at least in this Colab instance. So as I said before, when you first start writing models, you may not get familiar. By the time this number approaches 100 plus, we've created 100 plus sequential models, maybe we'll be pretty familiar with what's going on. And we had a look at the total params, trainable params, and non-trainable params, which are the patterns in our neural network, and the parameter numbers here per layer. And if you wanted to learn a little bit more about what they actually are, we've got this extracurricular resource here, so MIT's Introduction to Deep Learning video. Now, let's do a little exercise. If we were to change this to 10, we'll get model summary. Okay, number of parameters equals to 20. If we fit our model, takes almost no time at all. Wonderful. We get a summary of our model. Notice here that sequential went from 14 to 15 and dense went from 19 to 20 because we instantiated a new model here. And then we've got a different output shape and a different number of parameters. So because we've got 10 hidden units in our dense layer, there seems to be 2 trainable parameters per dense hidden unit. Now, there's one more way we can visualize our model, and that's using the plot model function from Keras utility, utils, or from tensorflow.keras.utils. Let's import plot model, and then we can go plot model, and we'll check the docstring here. Is it going to come up? We'll just error it out. So sometimes when you write an import statement and the function hasn't quite been import yet, checking out the docstring by pressing Command-Shift-Enter or Control-Shift-Enter on Windows might not come up until you've actually imported that function. So that's why I just ran it. It's not going to run anything. It's going to error out because it's missing one required positional argument, but that's all right because we can check it here. Convert a Keras model to dot format and save to a file. Okay. What's the example? tf.keras.utils.plotModel model. Let's have a look at what it looks like. Model equals model. Ah, okay. So we've got an input layer. It's going to pass that to our dense layer. All right. So if we go show shapes. So if we look at what this parameter does, def plot model, model to file. If we wanted to save this as an image, we can plot it to, we can set the to file parameter. But if we want to see the shapes of our model, show shapes is by default set to false. So we want this to be true. Remember, a lot of the time we'll spend with our neural networks making sure our input and output shapes are correct. So in our case, we have a dense input layer with an input of 1 and a dense output layer with an output of 10. Although this type of model here is relatively simple, this plot model function is going to be very handy later on when we start to create more complex models with more hidden layers. So we see here, we've defined the input shape as 1. So that's why we have an input shape as 1. And our output shape is 10 because we have 10 hidden units in our dense layer. Now, how might this change if we create a tf.keras.layers.dense 1? And I'm going to name it output layer. And this can be name equals input layer. And I'm going to name the whole model as name one of many models we're going to build. All right, model.summary. Now, notice how this changed. Model is one of many models we're going to build. Of course, you can name it something more specific to your problem, but you also see how we've changed the layer names. So before that was like dense 20 or something like that. We've now got a layer with the input layer name, and we've now got a layer with the output layer name. Now, this is very helpful if you have models with, say, 20 or even 5 layers. It's confusing if you're not sure which layer is which. So then we fit our model. One of many layers we're going to build. Oh, the value error. So we can't actually call our model that. So that's an invalid name. So let's just call it model 1. Model summary. Fit the model. That worked. Wonderful. Model summary again. There we go. Model 1. Layer, input layer, layer, output layer. And let's see how this updates. Plot model. Beautiful. That makes a lot more sense. So the input layer input is 1. Then we've got an input layer with a hidden size of 10. Then we've got an output layer of 1. So the input this layer takes is 10, and the output it gives is 1. Now, again, looking at this might seem quite confusing, but as I said, as we go on, as we start to build more models, as we start to visualize them, it's going to start to make more sense. So with that being said, let's stick with our theme of visualize, visualize, visualize. And in the next video, let's check out how we might visualizing our models' predictions. So have a go at creating your own different models. Maybe add some hidden layers here, give them different names, change the number of hidden units you have here, and then fit it to the data, get a summary, see how high you can get this number of trainable parameters, and then plot the model here using the plot model utility. And I'll see you in the next video. In the last video, we saw how we could visualize the different layers in our model and also get a summary of the layers in our model, which included the number of total parameters, the trainable parameters, and the non-trainable parameters. Now, let's have a look at how we might visualize our model's predictions so we can further evaluate how our model is performing. And so, to visualize predictions, if I could type correctly, it's a good idea to plot them against the ground truth labels. So in practice, you'll often see this in the form of something like y test or y true versus y preds or y pred, whatever you want to call it, where this is the ground truth versus your model's predictions. And so to do this, we'll first have to make some predictions. So we've got a trained model. So let's look at how we'll make some predictions to create y pred. Now, it's important here that y test is usually the nomenclature you'll see for the test labels. Same with y true. And y pred is also a very common nomenclature, a variable name, for when you're making predictions with your model. Or y preds, whichever you want to do. So model.predict, and we're going to predict on the test data set. So let's have a look. Y pred, see what our model comes up with. Okay, wonderful. We get a tensor in the same format as y test. There we go. So here are the ground truth labels, and here are our model's predictions. So in an ideal world, these would be the exact same numbers. So if our model learned the data perfectly and could predict the test data set 100%, these numbers would line up with these numbers. So rather than going through them one by one and comparing, let's see how we'll visualize them. So maybe we want to, how could we do this? How about we build a plotting function to figure this out? This is in case we wanted to, we're building a function because if we wanted to visualize our predictions going forward, we're probably going to reuse this plotting function. So let's create a plotting function. And this is actually, I'll put this down as a tidbit because I want you to remember something like this. I'll put a little key here. Oh, where'd my key emoji go? That's what we want. So note, this is just a Python concept in general too. If you feel like you're going to reuse some kind of functionality in the future, it's a good idea to turn it into a function. Nice and simple concept there. So if we did want to plot it, so let's go maybe def plot predictions, and then it's going to take some training data, which will by default equal xtrain. It'll also take some training labels, which will be ytrain by default. We also want some test data, which can be xtest by default. And then what do we want? Test labels. Yes, we need that. What comes after that? Oh, of course, we'll need the predictions. So the predictions can be ypred by default. Wonderful. And we'll give ourselves a little doc string here. So what can we call it? plots training data, test data, and compares predictions to ground truth labels. Nice and simple. We could talk about we could put in the doc string what the different variables are, but I'll leave that up to you. And so I want to start by creating a figure. We'll set the fig size to my favorite size, 10.7. Also a great hand in poker. Plot training data in blue. So that we're just basically taking the same plotting code as above. So this is where this is coming from. I'm not just pulling this out of the air. We're just functionizing this. You could just copy this and bring it down. But since we're in the habit of writing code rather than copying pasting code, let's get some practice. So we want a scatter plot here. And we're going to do train data and train labels. So we're just taking this, train data, train labels, and we're going to put the C into blue, and we'll give it a label of training data. Wonderful. And then we'll go plot testing data in green. PLT, we want a scatter plot. Again, the plots will differ here based on what kind of data you're working with. So scatter is pretty good for the problem that we're working on here, just a nice and simple regression. So label equals testing data. Beautiful. And here's where we're going to add the extra dimension or add the extra data set. We're going to plot models predictions in red. Nice and simple color scheme. Plot, scatter, and we want to compare them to the test data. So remember, we're passing our model to make the predictions. We passed it the X, so our predictions already have the X data built in, and they're predicting the Y value. So for our scatter plot for the predictions, it's going to, on the X-axis, plot the test data, which is X test, and then on the Y-axis, we want to plot the predictions. We'll give that a nice color of red, beautiful. And the label can be predictions. And of course, we want to show the legend just in case. We know the color scheme, but in case we wanted to share this plot with someone else, show them how beautiful our model is going, that should work. So plot predictions, train data, X-train. I mean, we could look at this all we want, but hopefully Python will tell us if we've got something wrong here. Now we're going to go plot predictions. We could almost just call this as it is if all the variables are set up. Plot predictions. Boom. Oh, look at that. How good. That's some good predictions there. Now you see how this is, at least to me, I'm not sure, you can agree or disagree if you want, but to me that's something to really visualize how well our model is performing. So ideally, these red dots would line up perfectly with the green dots. But to me, that looks like something, hey, if I wanted to present this to someone else, they could pretty quickly pick up what's going on in terms of how good our model is. Now, of course, depending on the scale of this graph here, this distance here could actually be something that's way off. Now, that is where we'd want to actually compare these numbers in a different way. So I might just fill out this so we know what's going on. So train data equals X-train. We don't have to do this, but this is just for completeness. Train labels equals Y-train. Test data equals X-test. And then we go test labels equals Y-test. And then finally we finish the predictions with Y-pred. Wonderful. All right. So from the plot, we can see that our model's predictions aren't totally outlandish. However, as we said before, the distance here between these two, depending on the scale, could be a fairly large error. So the way we can figure this out is with some evaluation metrics. So let's cover that in the next video. So evaluating our model's predictions with regression evaluation metrics. So maybe before the next video, you can have a play around. Try and see if you can get that red line closer to the green line. And how you would do that is you would try to improve our model. So you go back up here, maybe add an extra layer, maybe change the optimizer, maybe fit it for longer, and see how close you can get the red line to the green line. Maybe you can get them to fully overlap. But otherwise, I'll see you in the next video. Welcome back. In the last video, we saw how we could evaluate our model's performance by visualizing the predictions. Now, that's one great way to do it, but the next best way, or you can actually say these are on par depending on what kind of problem you're working on, is to evaluate our model with evaluation metrics. Now, depending on the problem you're working on, there will be different evaluation metrics to evaluate your model's performance. And so, since we're working on a regression problem, two of the main metrics you'll see. Now, again, there are plenty. You can look these up. However, two of the main ones you're going to run into are MAE, which is mean absolute error. We've been using this one so far, which is basically saying, on average, how wrong is each of my model's predictions. And then you have MSE, which is mean square error, which is very similar to mean absolute error. However, you square the average errors, and find out. Yeah, so take the errors from your model's predictions, square them, and then find the average. So that being said, let's before we implement these with TensorFlow, let's have a look at the Keynote. Here we have a slide for some common regression evaluation metrics. So let's start off with the mean absolute error, MAE. Here's the formula here, written in fancy mathematical notation. Now this is just saying these are our labels here, and xi, which could also be represented by y with a little hat. We'll see that in a second. Depends on where you find this formula. I think I just found this one on Wikipedia. What this is saying is these are our labels and these are our predictions. So across all of this, when you see this means sum of this little fancy looking E here. I think it's a Greek symbol for sigma. Now I want to give you a little tidbit here for math. So math kind of gets a bad rap, but it's actually a beautiful way of representing nature. So when you see these symbols, and I know when I first started in deep learning and machine learning, I saw Greek symbols like this and it would freak me out. But it's basically the same thing as learning code. So it wasn't until I started to replicate these formulas in writing actual code that I really started to understand them more. And so when you see this is sum of n starting from the first sample. So across all of our samples, so take the label, minus the prediction, get the absolute value of that, meaning that if the label is say 10 and this is 20, so this number would be negative 10, but we want the absolute value. So it's going to be, remember, if we did tf.abs, which is absolute, it would be positive 10. And then divide it by all of the predictions that you have. So all of the samples that you're making predictions of. And when you see this in combination, so this sigma notation here with n, in combination with the divide by n sign here, we'll see another form of it in a second. This is kind of like a fancy way of writing average. And this is the absolute error. And so we can do this in TensorFlow code. We're going to see this in a second. And when to use this metric? Well, this is a great starter metric for any regression problem. It's very easy to understand because it's just basically saying, I like to think of it as, on average, how wrong are our model's predictions. So then we go to the mean square error. So again, this is a very similar way, this little setup here, of writing the exact same thing as you see here. So when you see 1 on n in combination of sigma with an n on top, this is another fancy way of saying mean. And this here is another very similar way of writing, take our labels and minus the prediction. When you see a y like this with a little hat on top, this is often standing for, remember up in our, we created ypred. So this y with a hat means ypred or y predictions, and we square it. So see here we took the absolute value. In this one, we just square it with this little 2 here, and we can write the TensorFlow code to do that. And when should you use this one? Well, this is a great metric to use when larger errors are more significant than smaller errors. Why? Because of this little square here. So if you've got a model and making an error of, say, an absolute error of 10 is okay, but an absolute error of 100 is just a catastrophe, you might want to use MSE because it's going to amplify the error value for larger errors or larger values because of this little square here. And then finally, we've got Huber, which has a little bit more complicated formula. We won't dig too far into that, but again, we can write this in TensorFlow code. But Huber basically takes the combination of MSE and MAE, and it's less sensitive to outliers than MSE, so mean squared error here. So with that being said, these are some common regression evaluation metrics. Take note of this slide. You'll see these in practice. There are many more. However, let's get hands-on and start writing them with code. We'll come down here. All right. So how might we start? So if we wanted to evaluate our model using evaluation metrics, one quick way that we can do that is evaluate the model on the test set. We've got our trained model here. We can go model.evaluate, x-test, y-test. Because if we pass the test data set here, remember we want to train on the training data set, evaluate on the test or validation data set. So we come here, check the docstring, returns the loss value and metrics values for the model in the test mode. So if we run this, what's it going to give us? Comes in the order of loss and then evaluation metric. So where did this MAE come from? So if we come back up here, when we created our model, remember when we compiled it? We set metrics equals MAE. We also set loss to be MAE. So for our model, in this case, because the loss and the metrics are the same, the evaluate method is going to return the same figure. So there we go. Now, that's one quick way to start evaluating it. How about if we wanted to run one of these evaluation metrics on their own by not calling the evaluate method? We just want to compare the prediction array that we have, ypred, to ytest. Let's see how we might do that. So if we come up here, we want another cell, and let's go calculate the mean square error. Actually, let's do absolute error first because that's what we have already. Now, before I do this, I want to issue you a quick challenge. I want you to see if you can figure out, we've got this slide here. We've got the TensorFlow code for how to calculate the mean absolute error. I want you to see if you can use one of these to calculate the same value as we've got here. So you're going to have to compare ypred to ytest. So probably try type out the code here and then read its docstring and see how you might use these values to calculate the mean absolute error. So give that a go, and I'll see you in the next video, and then we'll go through it together. How'd you go? Did you manage to calculate the mean absolute error? If you had a go and you figured it out, well done. If not, let's see how we might do it. So if we come back to the slide, we've got the code here, tf.metrics mean absolute error. Maybe we'll try this one because we've already seen this in our loss function. So let's see what this is. We'll start exploring the TensorFlow library. So tf.metrics.mean absolute error. There we go. Oh, here we go. Computes the mean absolute error between labels and predictions. Beautiful, that's what we want. So that's the function that it actually implements. So loss equals mean absolute ytrue minus ypred. Beautiful. Now how might we use this? Okay, loss equals tf.kerras.losses.mean absolute error ytrue minus ypred. Now metrics.mean absolute error looks like it's the same as tf.kerras.losses.mean absolute error. Well, I mean, it should be because it's the same formula, right? Now, ytrue, ypred. Do we have ytrue? We don't have ytrue, but we do have ytest. So let's type that in, ytest and ypred. And actually, we might save this. So MAE equals that. And we'll set up the parameter names. Ytrue equals ytest and ypred equals ypred. See what happens. Oh, that's interesting. Now, MAE here gave us one overall metric, whereas this is showing us we've got a metric for each of our test labels and predictions. Why might that be? Well, we've actually got our predictions here and our test labels here. So what if we did y-test minus y-pred? What happens there? Do we get the same output? Nope, we get a very strange output there. What if we did y-pred minus y-test? We don't get the same output there. What's going on here? Let's have a look. Y-pred, y-test. Now, is it because this is not a tensor maybe? Y-pred? Let's turn this into a tensor and see what happens. So TF constant y-pred. Because if we do that, have a look here, this is what happens. TF.constant y-pred. Okay, so now that's in a tensor format. Yep, that's what we want. And this is in a tensor format. Beautiful, this should work. We go here. Oh, same output as before. Let's have another look. What's the difference between these two? We'll go through it step by step. TF tensor shape equals 10, 1. dtype equals float 32. Now this is TF tensor shape equals 10, comma. That might be where I see. So they're not in the same shape. Now, this is a very important tidbit. So if we ever want to compare different tensors, remember how we did in a previous video, we had to reshape our tensors so that they could be in the same format or the right shape to do a dot product. Well, this is very similar when we're doing or running evaluation metrics. A lot of the time, TensorFlow is very smart, but it can't interpolate the fact that our y-pred tensor actually has an extra dimension here compared to our y-test tensor. So, do you remember how we can remove the one dimension here of our y-pred tensor? If not, that's perfectly fine. Let's revisit the squeeze method. So if we go tf.squeeze and then pass in y-pred, what happens? There we go, much better. Gets rid of that one dimension there. So now our tensors, y-pred and y-test, are of the same shape. So let's redo this, calculate the mean absolute error. We could copy and paste that, but we're going to practice rewriting it. So calculate the mean absolute error. So let's see what happens if we go MAE equals TF metrics dot mean absolute error. Yes, that's what you want. Y true equals Y test. We're comparing, and again, this is another thing for all types of evaluation metrics. It usually involves comparing the Y true labels, so the true labels versus predictions. MAE. Oh, we forgot to TF squeeze our predictions. Shift and enter. Wonderful, look at that. How beautiful. So we get the same result as our evaluate function up here. Nice. Remember how I said a lot of the time you'll be spending your efforts reshaping tensors to make sure that they're in the right shape or the right format for whatever function you're trying to work with. Now we've done the mean absolute error. How about we try the mean squared error? So I'm going to leave this as a challenge for you. Calculate the mean square error. So just as we've done before, we've got the formula here, mean square error. Try out this function here and see if you can calculate the mean square error before the next video. How'd you go? Did you manage to calculate the mean square error? If not, let's see how we might do that. We'll go back to our little keynote here. And we can see here mean square error, MSE, is very similar to mean absolute error. So tf.metrics.mean square error. Let's go back here and go MSE equals tf.metrics.mean squared error. Y true equals the test labels. And y-pred equals our predictions, our model's predictions, that is. MSE. Run. What's going on here? We should have one value. You know what we didn't do? we didn't remove the single dimension from our predictions. So let's do tf.squeeze. We're going to go here and let's see what happens. There we go. Okay. Now, MSE will be typically higher than MAE because if we come back to the formula here, it's because of this little square here. So the errors are typically larger, so the resulting singular metric will be larger generally than MAE. So if we come back, when should we use it? Well, MAE is a fairly intuitive metric. It says on average, how wrong are our predictions? However, when larger errors are more significant than smaller errors, so for example, if being 100 off is far worse than being only 10 off, you may want to pay more attention to the MSE. Now, you could try Huber, but I'm going to leave that to your own extension. For now, since we're going to be running some modeling experiments in some upcoming videos, it's probably a good idea to, because we also functionized our way to visualize our predictions, let's functionize. I mean, this is pretty simple, but let's make a little function for mean absolute error and mean squared error so that we can use both of them going forward. So let's, right here, make some functions to reuse MAE and MSE. Def MAE, it's going to take in some Y true labels and Y pred labels. And then it's just going to return tf metrics.mean absolute error. Y true will equal Y true and Y pred will equal Y pred. Nice and simple. And then the same thing for MSE. Y true, Y pred equals return tf.metrics.mean squared error. Y true equals Y true and Y pred equals Y pred. Beautiful. Now, do we need to do that? Not necessarily. However, it's good to have some helper functions ready to go for when we run some experiments. So let's do that in the next video. So for the past previous videos, we've made some predictions with a trained model. We've visualized them, so compared our model's predictions to the test dataset. We've also evaluated our model's predictions with regression evaluation metrics, such as mean absolute error and mean squared error. Now, the next logical step you might be thinking is, how do we get these error values lower? So how do we minimize the difference between our model's predictions and the test labels? So in other words, get these red dots to be closer to the green dots. And so that's what we're going to tackle in the next couple of videos. More specifically, we're going to be running experiments to improve our model. Remember our workflow that we've discussed in a previous video? Usually start by building a model, fit it, evaluate it, tweak it, fit it, evaluate it, tweak it again, fit it again, and then evaluate it again, so on and so on. So if we come back to our Keynote, if the Machine Learning Explorer's motto is visualize, 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 in other words, taking a look at our data, taking a look at our model, taking a look at our model's training, we haven't done that, but we will see that in a future video, taking a look at our model's predictions, and visualizing these wherever possible, well, the machine learning practitioner's motto, because we're an explorer and a practitioner, is experiment, experiment, experiment. And so that's what we're going to do. We're going to try run a series of experiments to see if we can improve our model following this workflow. We've already built a model. We've already fit it. We've already evaluated it. Now it's time to tweak it a little. We'll refit it. We'll evaluate it again, tweak it, fit it, evaluate it. So let's see what this might look like in practice. Or if we remember back, what are some ways that we can improve our model? The top three are probably, you'll see, get more data. So get more examples for your model to train on. In other words, more opportunities to learn patterns or relationships between features and labels. Number 2 would be make your model larger. We've seen this briefly before. So in other words, using a more complex model. That's what you'll often hear larger models referred to as, more complex. So this might come in the form of more layers or more hidden units in each layer. Remember how we added some extra layers to our models before? We also increased the number of hidden units in each of the layers. And number 3 is train for longer. So give your model more of a chance to find patterns in the data. So with these in mind, how about, since we've got our data set already, we've got X-train and Y-train. This is our data set. How might we design? We can't really get more data unless we just artificially make our data sets bigger. So we'll rule this one out. But we can make our model larger, so use a more complex model, and we can train for longer. So let's design some experiments that we could do. How about we do 3 experiments? Let's do 3 modeling experiments. Now, what might you design? How about model number 1? What could we do for this one? So how about we do the same as the original model, 1 layer, but trained for 100 epochs. Number 2 could be model 2. This could be 2 layers trained for 100 epochs. And number 3, model 3 can be 3 layers, or maybe we won't change that. We'll keep it at 2 layers trained for 500 epochs. So 500 chances to look at the data. So see how we're just tweaking one parameter for each experiment. So the first one is 1 layer trained for 100 epochs. Then the second one, we're increasing the number of layers, but keeping the number of epochs the same. And for the third one, the difference is between the second model is the number of layers is the same. However, we're training it for longer. This is sort of the mindset I want you to start getting in. When you run your modeling experiments, start with, say, a baseline model, and then change one of the parameters for your next experiment, then do the same for the next experiment, and so on. You might want to, actually, I'll issue you a little challenge, is after you've seen us setting up these experiments, maybe you can create your own 4 and 5. So you can design them yourself. That would actually be some great practice. But let's get started. So the first one we want to do is, we'll create this. We're going to go build model 1. So what did we say? Same as the original model, 1 layer trained for 100 epochs. So we're going to set the random seed for as much reproducibility as we can get. Favorite number, 42, answer to the universe. So step 1 is create the model. So model 1 equals tf keras. You could scroll up and see the first model that we built, or you could just take my word for it that it was just a singular layer here. Tf keras layers dot dense, not 1. There we go. And what's step number 2? When we're creating a model, we've created a model, what do we have to do? We have to compile it. So let's compile the model. Remember I said you're going to get a lot of practice writing this sort of code? Because that's what I want. I've said it before, and I'll say it again. I'd rather you learn concepts from writing code than from looking at slides. So the optimizer is going to be tf keras optimizers dot. What do we build the first model with? Oh, look at that. We get a fair few options here. Now, there's actually a fair few optimizers built into TensorFlow. The main 2 ones that I regularly use is Atom and SGD. So we can go SGD. I'll let you research the other available optimizers that TensorFlow has. We'll set the metrics to MAE. Now if we go here, fit the model, model1.fit. We're going to go X train, Y train. Now, 100 epochs. That was the experiment design we were going to set up. So should this work? I think it should. Let's go. Shift and enter. Oh, look at us. Already modeling experts, sorry. So there's our first modeling experiment built. Now, what might we want to do if we're running experiments? What does a scientist do? Well, they track their results. So how might we do that? We've done it before. We created some functions before. What's the first one we might use? How about we visualize, or at least make some predictions with our model, and then we visualize them. Great idea. Make and plot predictions for model 1. So how do we make predictions with our trained model? We can we'll set up the prediction variable. We can call model1, .predict. And we're going to make predictions, remember, on the test data, because our model has never seen the test data, and we're interested in how our model performs on data it hasn't seen before. That's the real value of machine learning. Plot. We have a function, plot predictions. Oh, look at this. Look at us making our functions so we can just easily call them back again. Predictions. This is our docstring here. Plots training data, test data, and compares predictions to ground truth labels. Now, we hard-coded some of these parameters, so the only one we have to change is the predictions variable, or predictions parameter. So predictions is going to be ypreds1, because we just created that. ypreds1. Let's see what it looks like. How'd our model 1 go? Oh, not too good. So we can see there's quite a large difference here between our testing data and predictions. Remember, ideally, these would line up here, but that's all in the nature of experimenting. We're going to try and improve it. So what else could we do? Well, we also created some functions to calculate evaluation metrics. Thank you, past us, for creating such easy-to-use functions. So create model 1 evaluation metrics. So we want MAE1 for model 1, by the way, equals MAE y test, and then we're going to pass it in ypreds1. Beautiful. And then we're also going to do MSE1 equals MSE y test ypreds1. And let's see what this looks like. MAE1, MSE1. Oh no, what did we do wrong here? We forgot to squeeze these variables. TF squeeze to get them into the same shape. Now, I guess what we could have done, if we knew that all of our prediction tensors had to be squeezed, remember, what does this do? If we visualize ypreds1, if you ever forget what something does, just create a new code cell and run it. There we go, that's what it looks like on its own. And then if we squeeze it, ypreds1, it removes that one dimension. So we have to actually turn this into a constant, a TensorFlow constant or a tensor to see that shape. So there we go. As the predictions come out, they have a 1 here, and it's our first axis dimension. But then if we squeeze it, it removes that one dimension, and it turns it into this tensor. So shape 10. So we can get rid of that now. And if we squeeze them, we can run that. Beautiful. So we see the error is quite substantially larger than what it was before. This is the MAE, so the mean absolute error. So on average, each dot is 18.74 away from where it should be. That's the mean absolute error. And if we square the errors, we see the error is even larger. Now, how about we change our MAE and MSE functions to automatically squeeze our predictions? So let's go up here. This is making our functions better. So TF squeeze, we'll go there, and TF squeeze, and we'll also go there. Shift and enter. Now if we come down here, we shouldn't need to run TF squeeze here anymore. Get rid of the extra bracket. Take note of the output here. Make sure it's the same. There we go. It is the same. Beautiful. Okay. Now that's model 1 done. So what was our second model? Model 2, 2 layers trained for 100 epochs. Now we didn't actually specify how many hidden units. I'm going to let you decide how many hidden units you should put into this second layer. So give that a try. We'll come down here. We'll go create a little note, build model 2, and then we'll just set up, so this is 2 layers trained for 100 epochs. Or better say 2 dense layers. 2 dense layers, also known as fully connected layers. Now, our first model had 1 hidden unit in its 1 layer, but I'll let you decide if we're going to add a layer to model 2. So we'll set up model 2 equals something. I'll let you decide how many hidden units there are, and I'm going to make my decision on how many hidden units there are. So give this a try before the next video, building model 2. You could even calculate the model 2 evaluation metrics and plot the results if you're game enough. But otherwise, we'll go through our second modeling experiment in the next video. Alrighty, how'd you go? Did you set up model 2? Did you run the experiments? Did it go better than model 1? Hopefully these red dots were closer to the green dots. But if not, that's all right. Let's see how we can do it. So what's our first step? We might set the random seed, tf random dot set seed for as much reproducibility as we can get. So model 2, what did we say? 2 dense layers trained for 100 epochs. All right, so number 1, create the model, tf carers sequential, and then we're going to come down here. So this one has 2 layers. We go tf carers layers dense. Now, how many hidden units did you decide? If you built your own model, how many did you decide? I'm going to say 10 for this one. Remember, this is really an arbitrary number. We could set this to 1. We could set this to 10. We could set this to 100. I mean, most often you'll find values like this, like that are evened out. You'll rarely find values that are like 67, but you could try that if you want. So I'm going to try 10. TF carers, layers dense, and 1. There we go. And I'm also going to, what do we do? After we've created the model, what's our next step? I've given you a little hint here. Compile the model. Now we have to do model2.compile. It's going to be the exact same thing. tf carers dot losses dot mae, and then the optimizer is going to be tf carers optimizers dot sgd, just exactly the same before, and the metrics is going to be let's try MSE, you know, just to mix things up, because we're going to calculate our evaluation metrics anyway. So the only thing we've changed from our model up here is we've added an extra layer. Everything else is the same, except we're calculating the MSE as it's training. It's important to note that this metrics here will be calculated during training, and if you call, say, the evaluate method as we've done before on a trained model. So we come down, and what do we have to do once we've compiled our model? Step 3, fit the model. So model 2, we're going to fit on the same data, the training data, of course. X-train, Y-train, how many epochs are we going for? 100 epochs equals 100. You ready? Let's run our second modeling experiment. Boom. Oh. Wow, the MSE starts fairly high. Remember, MSE is often much higher than mean absolute error because of the squared value. So 1084, does it decrease by the end? Surely it does. Okay, finishes on 608. Let's see. Let's plot our, we've got to make some predictions. So make and plot predictions of model 2. So we'll call this one ypreds2 equals model2.predict on the test data, of course. And now we're going to plot our predictions using our beautiful plot predictions function. Woohoo! And again, all we have to change is this one. Remember, this is so helpful. if we're going to be running the same code over and over again, it's helpful to functionize it. We'll go Shift and Enter. What does this look like? Oh, yes. Very nice. So our red dots are a lot closer to the green dots. Beautiful. Come up here. Look at this one we did before. Looks like mud compared to what we've got here. So now we've plotted some predictions. Now let's calculate some evaluation metrics. So calculate model 2 evaluation metrics. You might want to pause the video and just go blaze right ahead and finish this video yourself. But if you don't want to do that, let's rock and roll here. MAE2 equals our function from before, ytest, and now ypreds2. We don't have to squeeze them this time because we've implemented that into our MAE function. And we can press Shift Command Enter. Oh, we should have actually put a doc string of what's going on here. But that's all right. We can do that later on for completeness. And then we want MSE2 equals MSE, ytest, compare it to our predictions with the second model, and MAE2, MSE2. Let's check them out. Boom, doesn't that look great? Oh, much better than before. 3.1 and 13. I think this is actually very similar to a model we've run before. But let's keep pushing on. We're now up to our third modeling experiment. So build model 3. Now, what was the experiment that we set up for model 3? We scroll back up. Lucky we took note of this. Here we go, model 3. 2 layers trained for 500 epochs. Okay, so the only thing we're going to change between model 2 and model 3, we could actually just copy and paste this if we wanted to, and then change 100 epochs to 500, so we're fitting it for longer. However, as always, we're going to favor writing the code out again ourselves. So build model 3. It is 2 layers trained for 500 epochs. Now, you could sit here and watch me write this out, or you could just skip ahead and write out the model 3 code yourself, plot the predictions, and evaluate it using evaluation metrics, and I could just see you in the next video. Otherwise, if you want to stay on board and we'll write this together, let's do it. So let's set the random seed. So tf random set seed. And then we go, what's step 1? Create a model. Oh, we are getting some prime experience here. tf_kerers.sequential. Open up our list. We come back. What did we say? 2 layers. We're going to keep it exactly the same as model 2. So I believe it was a dense layer with 10 hidden units. Wonderful. And then another dense layer with 1 hidden unit, because that's going to be the output layer. And then we're going to, what do we have to do? After we've created a model, what's our step? Compile the model. I mean, by the end of this, you're going to be like, Daniel, you are a broken record. But that's all right. If you're writing TensorFlow code like it's nothing, well, then I've done my job. Kerers losses.mae, and we're going to go optimizer equals tf kerers optimizers sgd. Wonderful. I'm going to set up our metrics. This time we'll revert back to MAE just to spice things up. Oh, too late. Oh, well, optimizers. Oh no, we've made a typo there. Classic. And now we're going to fit the model. So model 3 dot fit xtrain ytrain. How many epochs are we doing it for? What's our third experiment? 500. Oh, nearly did 5,000. Far out. That would have been interesting. I mean, you could do that. That's a challenge for model 4 maybe. 5,000 epochs. We'll see how this one performs first. Shift and enter. There we go. It's going to take a little bit longer, but not too much longer because it's only a small data set. But look at that. We can get ready to make and plot some predictions. Oh, what did it? Before we do that, MAE, I would have expected that to be lower maybe if we were training for longer. But again, don't just trust the training metrics. Let's visualize our model's predictions and run our evaluation functions. So let's go ypreds3 equals model3.predict. And we're going to do it on the test data set. Beautiful. And then our wonderful plot predictions function. We're going to set the predictions variable to be the predictions for our third modeling experiment. This should be preds3. Let's have a look. Oh, golly gosh. That's even worse than the first model. That's terrible. Far out. What's happened here? You know what? I think our model is trained for too long. We've totally missed the Goldilocks zone of where we should train it for. So this is a prime example of how tweaking some hyperparameters of your model, even ones that you intuitively think should result in a better result, actually don't lead to a better result. And we've actually just experienced here probably the first time we've come across our model overfitting, which is a very important concept in machine learning, but we're not going to cover it now. I'll leave that for a future video. However, if you want to look it up, I would search overfitting. Essentially, it means that the model has learned the training data too well, and it doesn't generalize very well at all to data it hasn't seen before. So give that a look in your spare time as a little extension to this video. But let's run our evaluation metrics for completeness. So calculate model 3 evaluation metrics. We'll do our MAE3. For model 3 is MAE. We'll compare the Y test labels to the Y preds for the third model. Wonderful. And then we'll do the MSE3 equals MSE Y test Y preds 3. And then we'll have a look at MAE3, and we'll also have a look at MSE3. Whoa. Now this is substantially higher than our other models that we ran. I think model 2 was actually the best one. Now, what we might do is rather than just scroll back and forth comparing our model's metrics, like we could look at that one, yep, model 2 is the best. Let's put them into a more structured manner. And so in the next video, let's look at how we might comparing the results of our experiments. So we've run a few experiments now. Let's compare the results. So in our workflow, we've said before, come back to the Keynote, the machine learning practitioner's motto is experiment, experiment, experiment. But as you might have guessed, any budding practitioner or any budding scientist doesn't just experiment relentlessly. They do a few, compare them, see which one works, and then they disregard the ones that don't work and move forward with the ones that do. So let's see in the next video how we might compare the results of our experiments. Welcome back. So we've run a few experiments. Now it's time to compare the results of our experiments to see what worked and what didn't. Now again, we said we could just scroll back up and check the numbers, but that's not really a structured way. Like we've only done 3 experiments and already it's getting tedious to just go back through and see what works and what didn't. So the beautiful thing is that we've saved all of our model results to different variables. So to compare them, actually, wait, I just want to put a little tidbit here. Something that I just thought of as I finished the last lecture is note. You want to start with small experiments and make sure they work. So by small experiments, I mean small models. And then increase their scale when necessary. Because what's our motto as a machine learning practitioner? Experiment, experiment, experiment. And it's hard to run a lot of experiments when you're trying really large experiments all the time. So start small, like we've done up here with our first model, model 1. We started with 1 layer, and then we started to increase the complexity as our experiments went on. So just keep that in mind when you're running experiments. Start small, build up, add complexity when needed. So let's go down here. And if that doesn't make sense for now, we're going to see that a lot throughout the course. It's going to be our theme, is start small, build up when needed. Now let's see how we can compare our results. So how might we do so? Well, how about we create a pandas data frame, which is just a table so we can compare our results of a different model. Let's compare our model's results using a pandas data frame. So the beautiful thing about Colab is that it's got pandas inbuilt. Import pandas as PD. And then we'll probably set up our model results as a list of lists. So we can pass it to our... So model 1 can be MAE1, MSE1, and then model 2 can be MAE2, MSE2, and then model 3 can be MAE3, MSE3. Beautiful. And then to create the data frame, how about we call it all results? And then we'll go PD data frame. And then the first thing we'll pass it to is our list of lists, so model results. And then we can set up the column names. What should we call the columns? Well, we have models, MAE, MSE. That's nice and easy. So model, MAE, MSE. Beautiful. And now what does this look like? Is this going to work? It worked, but that's a little hard to read. You know what we can do here? We can just get the NumPy value of all of these. So we go .numpy. Maybe we could have built this into our functions up above, but because we're already here, we'll just do some hacky code to get it looking nice. But when you're writing your code, you're going to make it beautifully functionized, aren't you? Let's see this. There we go. That looks much better. So, from our experiments and comparing our results in this beautiful table, I mean, maybe if you've run a few more models down here, you may have model 4, model 5, model 6, etc., etc. It looks like model 2 performed the best. So what was our model 2? Model 2.summary. So it looks like it had 2 layers. So one with 10 hidden neurons and the output layer with 1 hidden neuron. And it was fit for, we can come back up here, we can see it up here, model 2, 100 epochs. All right. So, what can we do with this? You might be thinking, comparing models is very tedious, and it definitely can be because we've only compared 3 models here. But this is part of what machine learning modeling is all about. Trying many different combinations of models and seeing which performs best, and actually seeing which doesn't perform best. So each model we ran is an experiment to figure out what doesn't work. And I'm going to put a tidbit here, is that we'll just write here, looks like model 2 performed the best. Wonderful. So the tidbit, the takeaway here is this is a follow-on from before. So we said start with a small model, and another one is one of your main goals should be to minimize the time between your experiments. So that's why we start small and build up when needed, because as we said before, if you're having to wait like 10 minutes between each model experiment, and sometimes you will have to with a larger data set, as we'll see in future videos. But the more experiments you do, the more things you'll figure out. Now this is getting too big because it's not a markdown cell. The more things you'll figure out which don't work. And in turn, when you know what doesn't work, you will get closer to figuring out what does work. It takes a lot of trial and error. Remember, the machine learning practitioner's motto: experiment, experiment, experiment. By the end of this course, you're going to have that tattooed on your brain, as well as, if in doubt, run the code, and as well as visualize, visualize, visualize. And so another thing here is that what you think might work, such as with Model 3, we increase the number of epochs, so the number of times Model 3 could look at the data. Sometimes intuitively you'll think it will work. We mentioned this in the previous video, but it in fact turns out to be the exact opposite. So look what happened with Model 3. So that's why experiment, experiment, experiment is so valuable. Now you're probably wondering, it's like, Daniel, hey, we saved all of our results here and we kind of set up a pandas data frame and we had to save all of our evaluation metrics to different variables. I mean, you say here, we're probably going to run potentially dozens of modeling experiments per problem that we're working on. It's going to end up very tedious and a lot of different stuff all over the place. And you're exactly right. Well, the good thing is that the people, like machine learning practitioners around the world, have developed solutions. And so I'm going to put here, tracking your experiments. These are a couple of little extensions for now, but we are going to cover one of them in the future. So let's just put here, one really good habit in machine learning modeling, as you may have seen, is to track the results of your experiments. And when doing so, it can be tedious if you're running lots of experiments. Luckily, there are tools to help us. So the first one, this is a resource. We're going to put the little resource emoji here. Resource. Remember, all of the resources, exercises, extensions, etc. in the course GitHub, as well as going to be links there'll be links where you can find all of these things. So resource, as you build more models, you'll want to look into using. So one of my favorite tools built straight into TensorFlow is TensorBoard. So this is a component of the TensorFlow library. And again, I'm just introducing the names of these things now, but later on we're going to get hands-on. So TensorBoard is a component of the TensorBoard library to help track modeling experiments, a very important part of machine learning, and we'll see this one later. And another one of my favorite ones that links straight into TensorBoard. There's a fair few of these on the market, but this is the one I have the most experience with. It's called Weights and Biases. So a tool for tracking all kinds of machine learning experiments. And the beautiful thing is, plugs straight into TensorBoard. So if you're using TensorBoard, you can definitely use Weights and Biases. So if we have a look, we can search up TensorBoard, tensorflow.org/TensorBoard. Here we go, TensorFlow's visualization toolkit. We're not going to dive too deep into this. If you want to jump ahead and have a look at what TensorBoard is capable of and maybe even plug it into our models, you can check it out. Otherwise, the other one is Weights and Biases. One of my favorite external tools for machine learning. But since this is outside TensorFlow, we're not going to be covering weights and biases. You can look into that as some extra curriculum if you want. We will be seeing TensorBoard later on. But for now, that's all we're going to cover for tracking our experiments. In the next video, if we've trained a model, say model 2, and we wanted to use it, say, in one of our applications, what we might want to do is get it out of our Colab notebook and somewhere else. So let's look in the next video at saving our models. So we've trained a few models, and we found out that from our modeling experiments, model 2 is performing the best so far. So let's say we wanted to save that model. Like right now, it's just sitting in our Jupyter Colab notebook. It exists as a Python object here. How would we save that and export it somewhere else? So let's figure out how we might do that. I'll just put a note here. Saving our models allows us to use them outside of Google Colab or wherever they were trained, such as in a web application or a mobile app. So how might we save a model in TensorFlow? This is where I'd start if I wasn't sure. I'd look it up. There we go. Save and load models. All right. Caution, TensorFlow models are code and it's important to be careful with untrusted code. See, using TensorFlow securely for details. I'll let you have a look at that, but trust me, we're not using TensorFlow maliciously here. Now, we've got a few options here. So defining a model. They've created a function here to define a model, model.summary. Here we go. We could save checkpoints during training if we were training for a long time. We're probably actually going to have a look at that later on in the course. But where is the save model function? What if we go save? There we go. Model.save. Save the entire model as a saved model. Now, in TensorFlow, there are two formats, or two major formats of which you can save a model to. The first one is the saved model format. So the saved model format is another way to serialize models. Models saved in this format can be restored using tf-keras models.load model. Okay. So that's, I'm guessing, once we've saved our model. If it's in saved model format, we can load it in using this method here. And are compatible with TensorFlow serving. We haven't seen that, but if you wanted to look it up, that's something you could look that up. The saved model guide goes into detail about how to serve/inspect the saved model. All right. Well, we've read up a little bit about it. Let's try it. Oh, and what's down here? Another format. Okay. So it looks like there's two formats that we can save our models in, but they're both using the save method. And one has a .h5 extension, HDF5 standard. All right. Well, let's try one at a time. So how might we save a model? Or we'll put a note here. There are two main formats we can save our models to. Number one, the saved model format. And number two, the HDF5 format. Now, I believe the saved model format is the default. Actually, I know it is because I have experience with this, but let's just see. So save a model using the saved model format. Now we can do so, go model2.save. And then if we check out the doc string here, saves the model to TensorFlow saved model or single HDF5 format. Okay. The save file includes the model architecture, allowing to reinstantiate the model weights, in other words, the patterns our models learned, the state of the optimizer, allowing you to resume training exactly where you left off. That's handy. All right, so let's try it out. So what was the parameter we have to pass in first? File path. Or let's call it something simple. You might want to get more creative with your model naming. So I'm just going to call mine best model saved model format and shift and enter. What happens here? We get a whole bunch of warnings. So I've looked at these warnings before, and they come up a lot of the time when you're saving a model. Essentially, what it is some behind-the-scenes libraries that have been updated, and if you're just using the save format, you can safely ignore these. You can also find what the warnings actually are in this documentation here. But just for now, trust me, the save model format, if these warnings come up, it's all right. Unless you're getting some sort of failed, the model hasn't saved correctly. But in our case, let's have a look at what happens. We check the Files tab of Google Colab, and here we go. We get best model.
Hello. I'm not going to interrupt for very long, but just want to give you a congratulatory message on making it 7 hours, 7 minutes, and 7 seconds into this video. Oh, my screens have gone blank. But just wanted to remind you, if you're enjoying what you're watching and coding along with, if you want to sign up to the full version of the course because you've made it this far, I have a little present for you. If you go to the zerotomastery.io website and decide to sign up to the TensorFlow Deep Learning course and use the code TFLW, TFLW, you'll get 15% off your sign-up price. But keep this a secret, will you? Because I want to keep this as a surprise for people who've made it this far through the video. Anyway, that's all I wanted to say. Use the code TFLW for 15% off. And don't tell anyone else. You can tell your friends, but please don't leave this in a comment in the video because people like surprises. Anyway, I'll see you later.
Saved model format. And in this file, we get a few things. We get assets. Okay. So we got what's in here and what's in the variables. And we get saved model.pb. Now this .pb format is called a protobuf file. Again, you can find more on this in the save and load documentation. But to make sure that our model's saved correctly, one of the best ways that we can do it is by loading it back in and checking it out. But before we do that, how about we save a model in the HDF5 format as well to test that out. So let's search that, HDF5. Provides a basic save format using the HDF5 standard. All right, what's the HDF5 standard? Hierarchical data format. All right. Is a set of file formats, HDF4, HDF5, designed to store and organize large amounts of data. Okay, well, I'll let you know that going forward, you're probably going to start training some fairly large models. And sometimes you might need to store them in a universal data format. So something like HDF5. So something that you can pass around to many other different programming applications. And TensorFlow allows us to save our models directly to .h5 by adding the h5 extension onto the end of our file path. So let's have a look at that. We're just going to run the exact same code up here, except one difference. Save model using the HDF5 format. Now, which one of these should you use? Well, it's really going to depend on your use case. If you're staying within the TensorFlow environment, so you want to just use your model with pure TensorFlow code, you're probably better off using the saved model format. However, if you're going to use your model outside of pure TensorFlow code, maybe HDF5 is better off for you. But we're getting a little bit ahead of ourselves here. Just know that there are two main formats that you can save your saved models to. The save model one is also the default, so the majority of use cases, you'll probably be using the saved model format. Now let's see what happens if we run this. See how we've just got the exact same code here, but all we've done is we've changed it to have .h5 on the end. We'll run that. Beautiful. Now what happens? There we go. So you'll notice the main difference here as well is saving a model to the saved model format. We get a folder here. And to the .h5 format, we get a single file. Now, I mentioned before that a way that we can check to see if our models have saved correctly is by loading them in and testing them out again. So much like we've evaluated our model 2, I'll just close this to get these evaluation metrics here. If we load our model back in, if the documentation is correct, saying that it's saved all of its weights and optimized the state, when we load our Model 2 back in from its saved model format or the H5 format, theoretically it should get the same results as before we saved it. So in the next video, let's see how we can both load a model in and reevaluate it to make sure it's saved correctly. Welcome back. In the last video, we saw how we could save our models or a trained model. And we saved them both to, or Model 2, which is the best performing model so far, to both the saved model format and the HDF5 format. So we've still got our models here in the Files tab of Google Colab. Now, what if we wanted to load that model back in? Let's see how we do that. Loading in a saved model. So if we come back to the documentation where we looked at load and save models, there we go. So new model equals tf-keras models.load model. Now I believe if we go load model, there we go. Models saved in this format can be restored using the tf-keras models.load model method. Now the beautiful thing is that with both formats in TensorFlow, the save model format and the HDF5 format, we can use the same method to load them in. So let's see how we do that. Which one do we want to do first? Load in the saved model format model. And let's do, what could we go on? Loaded saved model format equals tf.keras.models.load model. And then we're going to pass it the file path of this folder here. Now in Colab, you can do this by copying the path. So I'll just show you that there. We can copy the path there, turn that into a string. Now, again, in Colab, you're going to get a little content in the front of it. I believe it works regardless of whether you have content in the front or there or not. So we could do it like that. Hopefully that works. Otherwise, we can just revert back to what we want. Load save model format. How should we evaluate it? Oh, we'll get a summary. That's how we do it. Summary. Let's see if this works. Beautiful. Now, is this the same as our model 2 above. We've got 2 layers, dense, with 10 hidden units, and another one here with 1 hidden unit. If we go model 2 dot summary, is that the same thing? Yes, beautiful. Now to see if our loaded saved model format model, far out, we're going to say model a lot here, aren't we, is actually still the same as model 2, because right now the architectures we've confirmed are the same. And these are the same here. However, in the documentation, it told us that it's going to save the weights as well. So in other words, the patterns model 2 has learned. So to really check that, how about we make some predictions with model 2 and the saved model loaded model, and then compare those predictions to make sure they're making the same predictions. Because if they are, that means the patterns they've learned should still be the same. So compare model 2 predictions with saved model format model predictions. So this is kind of like we're writing a test to see if our models are the same thing. Our loaded model and our saved model. And we're going to go loaded saved model format preds equals loaded saved model format dot predict on X test. And then to compare them, we could do, let's just test them for equality. How about we do that? Loaded saved model format. This should return true. False, 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 false. What's happened here? Let's have a look at model 2 preds. And loaded saved model format preds. Five, 2, 8, 1, 3, 9, 9, 1. They seem pretty comparable to me. What we might have to do is, how about we calculate the mean absolute error of each? Otherwise, we might have to bring in a NumPy function here. So MAE, we want MAE of y true equals y test, and y pred equals, this is going to be model 2 preds. And then we want to compare these two to MAE y true equals y test, and y pred equals loaded saved model format preds. So they should have around about the same error. How does this go? True. Beautiful. So I'm not sure why their predictions are different. You know why it might be? It's because of how a computer stores numbers. So if we go model 2 preds, have a look at this. Maybe we'll squeeze that so it's, by the way, you can do dot squeeze on the end if you wanted to. That's a NumPy method coming in there, I believe. Yeah, there we go. And then if we do loaded save model preds dot squeeze, I believe these two should be very similar, yeah. So why aren't that? If we copy this up here, we're going against our rule of always writing code. Should this equal true? True, 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 true. Okay, so I would say the reason why here we're not getting this correct is because dimensionality-wise, they aren't of the same shape. Is that why? But that doesn't make sense. So this is. I want you to experience this. This is me exploring an output that I didn't really expect while I was creating this video. So I really want these videos to be as if like we were sitting side by side and coding and figuring things out together. That doesn't work. Okay. Oh, you know why? Because it's not preds. Haha. What a simple typo. Did you catch that? Why didn't you tell me earlier? Haha. This is a challenge we face when we're bringing in so many similar variable names. Now this should work. Okay, true, 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 true. All right, all that extra code there we wrote, well, the news is we didn't have to write it. So, I mean, you're going to see these things happen a lot of the time. And I'm glad you're watching me make mistakes on the fly because, as you learn, you're probably going to make a lot of mistakes too. Now, we've loaded in a model using the saved model format. How about we try the H5 format? So load in a model using the .h5 format, And we're going to go loaded H5 model can be tf keras models.load model. And then we're going to pass it in just the file path. We can come over here, copy the path if we wanted to, Command V or Control V, depending on if you're on Windows. Going to turn that into a string, get rid of that. Now again, you don't necessarily need content, but just to check if it works. So that's the loaded model, and we'll get the loaded H5 model.summary just to make sure it's the same thing. Does this match our model 2 summary? I believe it does. Model2.summary. So first things first, that's nice and easy to check. The architectures are the same. Now we're going to check it to make sure its predictions are the same as model 2. So if we go here, check to see if loaded.h5 model predictions match model 2. So we can go model 2 preds. We've already got that variable, but we'll just have some practice writing predict on x tests. Writing some more code. It never hurts to write a little bit more code. And then we'll go loaded h5 model preds equals loaded h5 model dot predict on x test. And then if we want to compare them, we can remind ourselves to this time add preds on the end, Daniel, equal loaded h5 model preds. How do we look here? True. Beautiful. We could do the same again for working out the MAE, but I'm just going to, if all the predictions are the same, the MAE should be the same as well. So we can get rid of this extra one and maybe move this one up to the loaded save model format. We'll just put a note in here of what we did so we don't confuse ourselves when we come back to our notebook. Compare the MAE of model 2 preds and loaded saved model preds. So what we just did, we repeated ourselves writing the code here. If you wanted to sort of functionize this going forward, that could be one of the tests that you run. So say, for example, you saved a model and then you loaded it back in. You could write a little function to make sure that the loaded model has the same prediction values or error rate or summary or something like that as your saved model. That way you make sure you're using the same the model with the same learned patterns. But otherwise, in the next video, we have our files here in Colab. How might we download them to our local machine if we wanted to use them outside of Colab? Let's check that out. Welcome back. So we've seen how we can both save a trained model and load it in within a Google Colab notebook. And by the way, a lot of these methods will work in just a Jupyter notebook. But how might we download a model or any other file from Google Colab? Now, this will be this lecture specifically if you're using Google Colab. If you're using a Jupyter notebook, oftentimes your files will be on your local machine or on your server hosted somewhere else. But this is specifically if you wanted to get a file off Google Colab. Now, we've got a couple of ways. So the first one, number one, or if you want to download your files from Google Colab, number one is you can go to the Files tab and right-click on the file you're after and click Download. So let's try that out. So Files tab, this is this one here. We have code snippets, we have search, we have table of contents. Far out, look how much we've covered so far. You should be really proud of yourself. But we'll come into the Files tab because that's what we're trying to do. And say we wanted to download our best model HDF5 format, .h5, we could just go here and click Download. Now, depending on the size of the file, will depend how long this takes. But now if we check My Files, Downloads, I've got the best model HDF5 format saved here in my download. So if I wanted to import that into some sort of application or into another coding environment, I've got it saved and trained here. Now, the second option to download a file from Google Colab is we can use code. See the cell below. Let's write some code to download from Google Colab. If we want to download a file from Google Colab, we can import from google.colab, import files, and then files allows us to files.download, and then if we just pass, we'll copy this one, see if we can download it again, copy path. We pass in the file path of our .h5 model, shift and enter. Oh, has no attribute downloaded. Oh, type that in wrong, so don't type in downloaded like I did, just type in download. And here we go. We're going to get a little loading bar, and there we go. We've got another copy of it. So we'll check the downloads. Oh, there we go. We've got the same file because I've got a little 1 here because we downloaded it twice. But that is a quick and easy way if you wanted to download your files from Google Colab. Remember, depending on the size of the file and your internet connection, it may take a little while to download. So just be patient. The other way is, maybe a third way is if you wanted to, while we're here, you can save it to Google Drive by connecting Google Drive and copying it there. So see second code cell below. So let's see how we might do that. I'm going to mount my Google Drive. So this is going to, if you have a Google account, which you kind of require to sign into Google Colab, it's going to mount your Google Drive, which is online cloud storage hosted by Google. We're going to wait for this to load. And when it loads, we should see our drive file appear in the Files tab. Beautiful. So this is my Google Drive here. If I open that up, I've got my drive, and I've got a few other things that I'm working on there. Wonderful. So if I wanted to save it here, copy path, or actually copy path there. Let's save a file from Google Colab to Google Drive. This requires mounting Google Drive. So we can do bang CP for copy. So we're going to copy this file here, H5. So that stands for copy this file at this path to, which path do we want to go to? I believe I might have a TensorFlow course. I'm going to copy that path. Now you might have to create a file in your Google Drive called TensorFlow course. You might be able to go new folder and create something like that. But mine's called TensorFlow course. It's already existed. So there we go. Copy best model HDF5 format.h5 to content drive my drive TensorFlow course. Let's see if this works out. All right, that looks like it went through pretty quickly because it was a relatively small file. So let's go ls and then just the path here to see if it's copied across. Oh, best model HDF5 format.h5 and a little spoiler alert for what's to come, but I'm not going to talk about that for now. We're going to see that in upcoming videos. So there's 3 ways there. If you wanted to download a model or any other file from Google Colab, you can right-click and click download. You can download it with code. Or if you wanted to save it to your Google Drive and access it later, you can use the copy method to save it across there in your target folder. Alrighty, so we've been through a fair few of the fundamentals. In the next video, or in the next series of videos actually, let's have a look at how we might tackle a larger example. And I'm not going to say any more. I'm going to wait until you're in the next video to show you what's going to happen. I'll see you there. I've said it before, and I'll say it again. We've covered a lot of ground so far. I mean, we've seen the fundamentals of building neural network regression models in TensorFlow, so you should be proud of yourself. Look at all the subheadings we've covered. Give yourself a pat on the back. But now it's time to step it up a notch and build a model for a more feature-rich data set. So have a look at our data. Look at what we've been playing with. X-train and Y-train. Just a couple of tensors with single numbers trying to predict single numbers. But In practice, you're probably going to be dealing with a little bit more of a complex data set. So, what data set are we looking at? Well, we're going to have a look at the publicly available medical cost data set, available from Kaggle and hosted on GitHub. So, let's find it. So, medical cost data set. Here we go, medical cost personal data sets from Kaggle. Now, Kaggle is a website which is basically an incredibly great place to compete in data science competitions, find different data sets, see example notebooks, and also learn more about data science and machine learning in general. So you're going to become very familiar with Kaggle over your data science and machine learning explorations. So we're not going to go through it for now, but just know that if you want example data sets, Kaggle is probably one of the best places to find them. Now, if we have a look at this, so medical cost personal data sets, insurance forecast by using linear regression. Let's have a read of what's going on. So context, so machine learning with R. So R is another programming language that can be used for numerical computing, just like Python, by Brett Lantz, is a book that provides an introduction to machine learning using R. Okay, so the long story short here is that this is a data set that's available online, and we've got a bunch of columns here: age, sex, BMI, children, smoker, region, charges. Now, what we're trying to do here is use these columns, so age through to region, to predict what someone's individual medical costs billed by health insurance will be. So we're using these features here to predict a number. So it's a regression problem. I believe this example has used linear regression, but we're going to build a neural network regression model. So the dataset is publicly available on GitHub here. Wonderful. So there's a fair few datasets here. We're looking specifically at insurance.csv. Now I'll show you a little trick that we can use to import this straight from GitHub to our Google Colab notebook. If we go raw, there we go, raw.github user content. Now, if you can't find this link, I'll put in the resources section for you. We're going to copy this link, come back to our notebook. I'm going to get out of this. And the first thing we're going to do is actually import the required libraries for this larger example. We've already imported these, but it's good practice just to, if we were starting from scratch, import TensorFlow as TF, import pandas as PD. Wonderful. And we're going to also need matplotlib in case we want to do some plotting. Those libraries are pretty standard. So now, because we've got the insurance data set copied to our clipboard, read in the insurance data set. Let's see what it looks like. We'll call it insurance equals pd.readcsv. And then the beautiful thing is we can just paste a link in here, and the readcsv function will read it directly from here. All of these values. So there's the columns: age, sex, BMI, children, smoker, region, charges. We can import directly. Let's have a look. Insurance. All right, so 1,338 rows times 7 columns. Yes, now we're talking. This is a little bit more complex than the problem we've been working on so far. So what do we have here? We have age, sex, BMI, children, smoker, region, and then charges. This is an amount. So this is how much someone's medical costs or medical bills were. Medical insurance was based on their age, sex, BMI, number of children, are they a smoker, yes or no, and whereabouts do they live? Southwest, northwest, etc. I'm not sure. Is it from a city? Anyway, doesn't matter. You can do some research. I'll put the links to where you can find this data set. Essentially what we're focused on here is writing TensorFlow code to take in these features, learn the relationships between them, or more so the relationships between these features and this target variable here, charges. So what is a regression problem? Relating it back to our Wikipedia definition, in statistical modeling, regression analysis is a set of statistical processes for estimating the relationships between a dependent variable, often called the outcome variable, and one or more independent variables, often called predictors, covariates, or features. So in our case, what is our dependent variable? Our dependent variable is the charges, because this is what we're trying to predict. And what are our independent variables? In other words, known as, I like the term features. So that's what you'll hear me use a lot. Our independent variables are these columns here: age, sex, BMI, children, smoker, region. So what do we have to do? What is our first step in getting our data ready to pass into our machine or neural network models? Can we just start building a model? Model equals TF carers sequential. I mean, we could keep that going, but what do our machine learning models like? Can we pass in this column, sex? If it reads female or male, what's it going to do? So if I go insurance, what type is this column? Oh no, insurance. Data type object. Well, what about smoker? Data type object. What's the difference between smoker and insurance age? int64. So we have some columns here that are numerical and some columns that aren't numerical. Do you remember what we have to do to non-numerical columns before we can pass them to a deep neural network or a machine learning model? We have to turn them into numbers, right? If we come back to our regression inputs and outputs, say we're trying to predict the price of homes, the sale price of homes, based on the features here, bedrooms, bathrooms, garages, before we can pass it to our machine learning algorithms, we have to create a numerical encoding, which is often referred to as input features. So that's what we're going to have to do to these variables here. Now, one style, we've covered one style of numerical encoding, and it's the style we're going to use for this problem. It's called one-hot encoding. So if we go, what is one-hot encoding? Probably one of the simplest methods to turn categorical variables into numerical variables. So if we go here, is there a diagram? Maybe we just go to images. There we go. Nice and simple. So one-hot encoding, if we have the food name apple, chicken, broccoli, for one-hot encoding, apple gets a 1 and 0 for everything else. For chicken, chicken gets a 1 and 0 for broccoli and apple. For broccoli, broccoli gets a 1 and a 0 for chicken and apple. So that's what we want to do. Because we're working with categorical variables here, we're going to create a column that is maybe sex underscore female. And if the value of this sample is female, we want to put a 1 there. And if it's male, we want to put a 0 for the sex underscore female column. Now, we could do this manually, but that's going to take a whole bunch of work. So what I prefer to do is use, if we got a pandas data frame, we can use pandas get dummies function. Let's see what this is. Or better yet, if you didn't know what this function was called, how to one-hot encode a pandas data frame. What do we get? How can I one-hot encode in Python? One-hot encoding a feature on a pandas data frame. Examples. What do we get from this web page? Again, I'm not sure what this web page is going to show us, so this is kind of running the gauntlet here. All right, there we go. With one-hot encoding, a categorical feature becomes an array whose size is the number of possible choices for that features. So we create a data frame of country, different countries here. Wonderful. They use get dummies. Pandas provides a very useful get dummies. So once we'd seen that, gives a great example there. Beautiful. We could go to the get dummies page, but we already have that open. Get dummies. Convert categorical variable into dummy/indicator variables, which is I'm not sure why they use dummy indicator variables. I just treat this as another name for one-hot encoding. Come down. We see some examples with pandas. There we go. All right. So let's just run some code and see what happens. Rather than diving into documentation, who needs the docs when you can just run hundreds of different little mini experiments and figure things out for yourself? No, that's not to say that documentation is actually very valuable. So get used to reading documentation, but also get used to writing lots of code. So let's see what happens if we run this. Data frame object has no... Oh, we can't run it like that. I'm eating my own words here. We have to run it like this. pd.getDummies, then pass it our data frame. Come on, Daniel. pd.getDummies. Let's try one hot encode our data frame. So it's all numbers. And what do we call our data frame? Insurance. Oh, yes, look at that. Okay, that's what we want. So we have age, BMI, children, charges, and now for the columns that were categorical columns, such as sex, we have sex, female. So see here, this first sample has a value of female. So it gets a 1 for the sex underscore female column. And then for the sex underscore male column, gets a 0. And then were they a smoker? Yes, they were a smoker. Oh, maybe why? That's why their charges are so high. So they get a 1 for the smoker yes column. And where were they from? They were from the Southwest. So they should have a 1 in the Southwest region. Wonderful. Okay, that looks good. Now, we might actually save this to a variable. Insurance underscore 1 hot. And then insurance 1 hot. Dot head. Excellent. All right. So now we have a few more feature columns. So because charges is still the column we want to predict. So we want to use all of these columns, age, BMI, children, sex female, sex male, sex no, smoker no, smoker yes, region northeast, etc. We want to combine all of those and learn the relationship between what charges equals. So we'll probably end this video here before it gets too long. But if you want to have here's a bit of a challenge too. If you want to go ahead, maybe we'll, in the next video, create X and Y values. So features and labels. Have a go at creating the X and Y values. Then we'll need to create a training and test set. And then we can build a neural network. So here's your challenge. If you want to go ahead, create training and test sets, and then build a neural network. It'll be sort of like Model 2 above, but it might have different input and output shapes, or we'll see. But that's your challenge if you want to go ahead. Otherwise, in the next video, we'll start to tackle these 3 things. How'd you go? Did you take on the challenge? Did you create X and Y values, features and labels? Did you make a training and test set? And did you perhaps even build a neural network, sort of like Model 2 above, to find the relationship between our features and target variable? If not, that's perfectly fine. If you did, wow, that's incredible work. Otherwise, either way, we're going to go through each of these 3 steps in this video. So let's split these off. I think the command is command M minus. Yeah, there we go. If you want to split a cell, so command or control M minus in Google Colab. So we have 3 different things here. This is what we have to do. All right, create X and Y values, features and labels. Let's do this. X equals. Now, what did we say before are our features? Basically, every column except charges. So let's, how can we do that? We can drop a column. So insurance, 1 hot, dot drop. And we're going to drop charges on the first axis. I believe that's how we do it. If not, we can find out in a second. And then Y is going to be just this column. So let's make sure we can get that. Insurance, 1 hot, just charges. Wonderful. Okay, now let's view X. X dot head. First 5 rows. Wonderful. Age, BMI, children, etc., etc. Got a fair few columns there, and let's view Y to make sure. Remember, always visualize, visualize, visualize. Beautiful. There's the charges there, which are all float 64s. Now, these are in a format of, right now, they're in a format of a pandas data frame. However, we're going to see very shortly that we can turn them into formats capable to be used with our neural networks. That's actually probably going to happen automatically because we're about to create training and test sets. Now, previously, we'd indexed our data sets going something like the first 40 examples are training examples. However, there's a much better function to create a training and test set if you've got a feature matrix and a label vector. So we're going to use scikit-learn train test split. This is a very popular function. Model selection, train test split. Remember, creating a training and test set, probably one of the most important things in machine learning. That's why this function is so beautiful. So split arrays or matrices into random train and test subsets. Wonderful, that's exactly what we want. Oh no, we don't need to copy that. We can just import sklearn.model_selection train test split. Let's see how we can use this. From sklearn.model_selection import train test split. So if there's one function from scikit-learn you want to remember, it's this one. Very, very popular. So we go here, xtrain, because it's so useful. xtest, ytrain, ytest equals train test split. And then we want to, can we get the docstring? Or is it not imported yet? Not imported yet, that's all right. I know you need an input, but we're not up to that yet. Here we go. What's the docstring? Split arrays of matrices into random train and test subsets. Okay. So we want, what does it take? Arrays, sequence of indexable with same length or shape 0. Allowed inputs are list, NumPy arrays, SciPy sparse, matrices, or pandas data frames. That's us. That's what we have. Beautiful. Test size. If float should be between 0.1 and 1.0 and represent the proportion of the dataset to include in the test split. So before we made an example, right up the top, right back up here, in the 3 sets, we used an 80-20 split, meaning 80% training data, 20% testing data. That's a very common split, very useful split for our problem. So let's keep it at that. And I just want to see, what's the example here? This is where I got this line of code, by the way. Okay, train test split. It passes x, y, test size equals, they've used a 33% test split, and they've set random state 42 to make sure that the data is split in the same way each time. So otherwise, if you don't set the random state, the split will be random. So let's go in here. I'm going to pass x, y. Oh, I've got caps lock on. Goodness gracious me. Test size equals 0.2. And I'm going to set the random state. They've set 42, so we'll set 42 too. All right. And let's see what happens here. We'll go len x, just to see the length of x overall, and then length of x train and length of x test. What's going to happen here? Beautiful. Look at that. It's created our train and test split. So this is how many were originally in x. And because we've set the test size to 0.2, our test data set has 20% of the sample. So if we were to go 0.2 times 1338, what does it give us? Okay, it's going to be around, it's been rounded up. All right, nice and fair. And it's also random. So if we go x train, what does that look like? All right, all these indexes are randomly shuffled. Beautiful. That's what we're after. So let's get out of that. Now, how might we build a neural network to take in x train and y train and learn the relationships between the two? So the hint is, it's sort of like Model 2 above. So if we go, we get another code cell here, model2.summary. What does Model 2 look like? All right, so we've got 2 layers. Very familiar with this Model 2. How about we just recreate it? What should we do? TF, set the random seed first. Random set seed 42. Nice. Now step 1 is create a model. How do we do that? We go model, or actually we'll call it insurance model. There we go. TF. Pretend we're working for a large insurance company and we've been asked to model this data set so that when Sally Smith comes to buy insurance off us, we know if she tells us how old she is, where she's from, if she's a smoker or not, we know how much we should charge her based on our other customers. That's what we're doing now. There we go. Now, what do we do always after we create a model? Step 2 is we compile it. Compile the model. And here it's called insurance model.compile. What's our loss function going to be? tf_losses. What have we been using? MAE, mean absolute error. We can keep it like that. We could even change it to MSE if we were feeling a little adventurous. But since we're going to stay with a similar experience to what we've been running, we'll keep it as MAE. Optimizer equals tf_optimizer dot the old faithful stochastic gradient descent, SGD. And the metrics we're going to put here is mean absolute error. Beautiful. And now, number 3 is we fit the model. Now, I said before we were going to format our data into a way that it's going to work with TensorFlow. So right now we're writing TensorFlow code here, but up here, this is Pandas code. Pandas, scikit-learn, and now TensorFlow. I wonder if this will work. Do you reckon it'll work? If in doubt, run the code. You ready? We're about to build a neural network model on 1,000, or really because we're fitting on the training data, it's just over 1,000 rows of data, which is a big increase on what we've been working with so far. So, don't hold your breath. 3, 2, 1. Is it going to work? What did we mess up? I knew there'd be an error. Spelt insurance wrong. Oh, what an anticlimax. All right, 3, 2, 1. And again. Here we go. Here we go. Now all the typos come out. All right, third time lucky. 3, 2, 1. I'm done. Oh, you typed in. All right, no countdowns anymore. Just fit the model. Boom, look at that. All right, now this one takes a slightly little bit longer because we're working with more rows. So we come down here. Does our MAE decrease as we're going up? It starts off around 8,600 and it finishes around 7,100. Okay, so a fairly good decrease. And we're just going to get rid of this cell here. Wonderful. So what do we do now? We just train a model. Oh, and yeah, by the way, we didn't even have to reformat this into tensors. The reason being is because Pandas is built on top of NumPy. So really, when we see it like a Pandas data frame, this is actually a big NumPy array. And when we pass that to TensorFlow, it automatically knows how to deal with NumPy arrays because we've seen tensors work with NumPy arrays before. So what's next? After we've trained a model, what should we do? Should we evaluate it on the test data? Great idea. Let's do that. So check the results of the insurance model on the test data. So insurance, how can we do that? We can use the evaluate method, evaluate on X test, Y test. Let's see how it performs. All right, okay. So on the test data set, it's performing even just a slightly little bit better than on the training data set. That's pretty cool. So now what might we want to do? What is this error telling us actually? Mean absolute error. It means that on average, our model is wrong by about 7,000. Now, is that number large? Is that significant compared to the other values in our dataset? Let's have a look at our training variables. Ytrain. Whoa. So if our model is off by 7,000, what's the median, the middle number of our target variables? Wow. So the median variable, or actually what's the mean as well? 13,300. 9,500. So right now our model's pretty substantially wrong because, I mean, look at this. The average value of Y-train, so the average insurance cost, is 13,300. So, and our model is on average off by 7,000. That's pretty significant considering the total amount is only 13,300, well, that's the mean. But the median, it's even worse. It's only 9,500. So if we're off by 7,000 there, we might be charging someone 2,000 when they should be being charged 9,500. So naturally, what might we want to do? If you guessed improve our model, you'd be 100% correct. So let's, in the next video, right now, it looks like our model isn't performing too well. Let's try and improve it. So we're going to start to run some experiments to improve our model. But before I do, again, I'm going to issue you another challenge. If you want to go right ahead, we've already run some experiments to improve our models. How about you try running some very similar experiments on the model we just built here? Maybe you add an extra layer, maybe you change the optimizer, maybe you train for longer. Give it a play around and see how you go. But otherwise, we'll try a few experiments in the next couple of videos. How'd your modeling improvement go? Did you get a better MAE score? Was it lower? I hope yours did better than the one we first built, but if not, that's all right. We're going to see if we can improve it now. So what should we do first? When we did it up here, we did some experiments. So the first thing we did was, okay, we added an extra layer. Okay, let's try that. We'll come down here, a larger example. First experiment. Might write this down actually. So to improve our model, or actually we'll put try. To try improve our model, we'll run, let's do 2 experiments. So one can be add an extra layer with more hidden units. And then 2 can be train for longer. And then I'll leave the rest up to your imagination. Insert your own experiment here. You can put to use what we've learned. So how about we recreate the model? We'll try the first one. So add an extra layer with more hidden units. So set random seed and then TF random set seed. Wonderful. Now, number 1, create the model. So TF Keras, we need to go insurance. What do we call it before? Just insurance model, right? Insurance model 2 equals TF Keras sequential. Wonderful. And then we should go TF Keras layers. Maybe the first one here has 100 now. Then TF Keras layers dense 10. And then TF Keras layers dense 1. Is that an increase? What was our first? Yeah, we only had 1 layer with 10 there. So this model has an extra layer with an extra 100 hidden units. So if we come down here, if we go there, 2 is compile the model. And we want to go insurance model 2 dot compile. We're going to go loss equals TF Keras losses dot MAE. What's the optimizer? TF Keras optimizers. One day I'll get this right. SGD, beautiful. And then the metrics can be MAE as well. And now let's go number 3 is fit the model. Is insurance model 2 dot fit X train Y train epochs equals 100. All right, you ready? This time we're going to set verbose equal to 2, so we don't have a massive output. Verbose, equal to 0. What do we get wrong here again? Oh, metrics equals MAE. All right, we finished there. Again, we get some warnings. I was just saying that our data types are maybe not optimized, but the beautiful thing is that TensorFlow fixes those for us. And now we can go evaluate the larger model. So insurance model 2.evaluate. Hopefully, because we've added more hidden units and an extra layer, we've given our model more potential to learn. So, well, that's at least in theory. Did it work? Oh, what do we get wrong here? Maybe we should output the training. Nan. Tense 100, insurance model 2, insurance model. All right, now we definitely have some troubleshooting to do. What have we got? X train, Y train should be the same. Maybe our model is too complex to learn anything. So we might have built a too big a model. What's another lever that we can tune here? We could remove this layer. Let's see if we just remove that layer. Does this work? Okay, so it works there. This is some good troubleshooting. Now what if we keep that layer on and try again? We get loss is NaN. If you ever see your loss or MAE as NaN, it means that there's probably something wrong with your model. So this is some good troubleshooting. Now, let's think about this. We've got to create the model. Our first experiment, we put down here that we wanted to add an extra layer with more hidden units. Yes, but it looks like our model may be too complex for our data set so that it's so large that our data set is not large enough to teach it anything. So what we might try to change is we haven't looked at anything in number 2. Now, can we alter the learning rate? So the learning rate is 0.01. How about we try Old Faithful Adam? So there's a few different optimizers here. SGD and Adam are probably the most popular. If SGD doesn't work, try Adam. Let's see what happens. Ho ho ho! Look at that! Yes! Oh! That's so far so good. That looks like it's doing better than the previous model. All right, evaluate the larger model. Ho, look at that. Now, if we go insurance model, where's the first one? .evaluate, X test, Y test. What were the metrics from this one? MAE, holy goodness. We've just decreased it by 2,000. So about 30-odd%, around abouts. 30-odd% decrease in error rate by tweaking 2 little things. We added an extra layer and we changed the optimizers. Again, this might not always work, but that's just one of the levers that you can turn on your models to improve them, or at least try to improve them. We put that up here on purpose to try and improve our model. So I'm going to put here, we actually modified this experiment, add an extra layer and use the Adam optimizer. So this one we're going to train for longer, same as above, but train for longer. Maybe 200 epochs. 500 probably too many. Well, who knows? If in doubt, run the code. Experiment. Okay, so that's insurance model 2. Let's run insurance model 3, see if we can improve on this number here. How do we create this? So set random seed. So TF random set seed 42. Beautiful. Now, number 1 is create the model. Same as above. So we'll go insurance model 3 equals TF Kera's sequential. Go right to the end here. TF Kera's layers. The first layer we had there was a dense layer with 100 hidden units. And now we have TF Kera's layers dense 10. And then TF Kera's layers dense 1. Got to make this insurance company happy, you know. What's step number 2? Compile the model. Beautiful. Insurance model 3 dot compile. Loss equals TF Kera's losses dot MAE. That deleted itself out of nowhere. The optimizer is, remember what optimizer are we using now? We're using Adam. Optimizers. Come on, Daniel, you can remember that. And then the metric is MAE. Wonderful. And now let's have a look. Number 3 is fit the model. insurance model 3.fit xtrain ytrain epochs equals 200. We might actually put this history equals that. You'll see what this means in a second. So you ready? Let's run this. 3, 2, 1. All right. We're past 100 epochs. Oh yes, the MAE is going down. Beautiful. Woohoo! All right, so if we go, now let's evaluate. Evaluate our third model. .evaluate. Do these results on the training data set translate to the test data set? Because that's what we're really concerned about. Evaluate. That is what's up. We've decreased our MAE to 3,500. I believe we are now, so if we look at back to our first insurance model evaluate, X test, Y test, we just halved our error rate in about 5 minutes. How cool is that? Now, there's a few more levers that we could try, but there's also a little thing that I want to show you. And we saved history equals insurance model 3.fit. What is this history variable? Well, this is something we're also going to get very familiar as we go. So plot history, also known as a loss curve or a training curve or a training curve. So how we can do this, if we go pd.dataframe equals history. So history has a history parameter saved to it, or attribute, sorry. And then if we go dot plot, inside a pandas data frame that is, and then we're going to set the Y label to loss, and then the X label to epochs. And shift and enter. Look at that. One of the most beautiful sights you will ever see in machine learning and deep learning is a loss curve decreasing. So, why is this so beautiful? It's because if we look at where this history variable originates from, we instantiated it when we started to fit our model to the training data set, specifically insurance model 3. Now, if we scroll right back to the top of the epoch chain here, all the way up to 0 out of 200, look at this. The loss starts at a massive 13,273. So the MAE, when our model first started to learn, its average prediction was off by 13,273, which is basically the average of the whole data set. But then we scroll down, as our model trains, as it learns, its loss goes down, its MAE goes down, and we finish off with a loss of 3,600, and because our loss function is MAE, we finish with an MAE of 3,600 as well. And this is what this curve is reflecting. So when we're training our neural networks, generally we want our loss curve to go down, because that means that the predictions our model is making are becoming less and less wrong. So it actually looks like our model's loss would probably keep decreasing, maybe not as extensively as it has here if we kept it training for longer. So that's probably a little extension that I'll leave for you to try out for yourself. Train the insurance model 3 for a few more epochs, maybe another 100 or 200 or so, and see how low the loss will go. But you're probably asking, after seeing this, how long should you train for? Well, that's a great question. Let's put that there, actually. We'll do the question emoji. Question. How long should you train for? So if you're asking that, I'm going to hit you with an answer that's going to say, it depends. Remember how machine learning and deep learning is very experimental? Well, how long should you train for it actually really depends. Really. It depends on the problem you're working on. However, many people have asked this question before. So, TensorFlow has a solution. It's called the early stopping callback. And we're going to use this in a later video, but I just want to introduce it now so it seems familiar. So TensorFlow early stopping callback. Here we go. And essentially what this is this, I'm going to set the link here, early stopping callback. I'll let you read what the documentation says, but I'll just tell you. It's called the early stopping callback, which is a TensorFlow component you can add to your model to stop training once it stops improving a certain metric. So, in the case of our insurance model 3, if we wanted to say train it for 1,000 epochs, we could set the early stopping callback to say, hey, I'm going to set you off train for an unlimited amount of epochs. But once your loss stops decreasing for say 3, 5, or 10 epochs in a row, which means our model has stopped improving, stop training. All right, does that make sense? Now, a little extension you could do would be to look at the early stopping callback in TensorFlow and see how you could implement it for the code that we've written here. All right, but otherwise, I think this video is getting a little bit too long. So we've covered a few modeling experiments here. What we're going to look at next is another way of pre-processing data, specifically normalization and standardization. So again, if you want 2 pieces of extra curriculum before the next video, read up on the early stopping callback and search for what is normalization and standardization, and think about how it might relate to our training data. But anyway, I'll see you in the next video. Welcome back. So in the previous few videos, we've been putting together all of the different concepts that we've learned so far, and there've been a fair few. We started working on a larger example, specifically trying to predict the cost of someone's medical insurance based on features such as their sex, BMI, where they lived, and smoking status. Now, we've got one more thing we're going to cover before we move on to the next section. And it involves pre-processing data, specifically to do with normalization and standardization. Now, you may have heard of these terms before. If not, that's perfectly fine. We're going to go through them. You might be thinking, hey, Daniel, why are we going back to pre-processing data? I thought we already had our data ready. We'd turned it into tensors, we'd one-hot encoded it, etc. And you'd be 100% correct, but there is one step we can do to improve the pre-processing of our data. So if we come back to our Keynote here, this is our steps in modeling. And you might have noticed, if you hadn't looked at this in a while, we've actually done each of these steps throughout this entire section. We've gotten our data ready, we've turned it into tensors, we've built a TensorFlow model, we fit the model to the data and we've made predictions on the data, we've evaluated our model through both visualization and using evaluation metrics, we've improved our model through experimentation, and we've saved and reloaded our trained model. But now we're going back to step number 1, possibly the most important step in this entire pipeline, getting our data ready, turning it into tensors. So we've turned all our data into numbers. Remember, neural networks and actually most machine learning models can't handle strings. They need everything to be in numerical form. Number 2, we've made sure all of our tensors are the right shape because, as we've seen before, if our tensors are the wrong shape, we run into a whole bunch of different issues. And number 3, we could do, or we haven't done yet, is to scale features. So normalize or standardize. Now, neural networks tend to prefer normalization. Again, these are just words to you at the moment, but we're going to see what both of these are in a minute. So let's go back to our notebook. Again, if you wanted to figure out what normalization and standardization are, what could you do? Here's what I would do. Let's go, what is normalization in machine learning? If we zoom in here, so we got here, normalization is a technique often applied as part of data preparation for machine learning. The goal of normalization is to change the values of numeric columns in the dataset to a common scale. Without distorting differences in the range of values. All right. So let's have a look at our data set, xtrain, or maybe just x as a whole. What does x look like again? So we see here we've got age, BMI, children, but do you see here how age is on a different scale to what BMI is? So if we go x, what do we want? We want age dot plot. So see how these values are all over the place? That's probably not the best plot. Maybe we can go hist. We want a hist. Oh, we need the kind word. There we go. Okay, so here's the distribution of our age column. Now, what about our BMI column? We want plot kind equals hist. It's like this. So what if we wanted to get these both on a similar scale? So see, this goes from 20 to 60, this goes from 15 to 50, and then children, I'm assuming goes from something, if we go x children dot value counts, what's the max number of children? Value counts. So there's a lot of people with 0 children, and there's a few people with 5 children. So what if we wanted to get these, so 15 to 50, 0 to 5, and 20 to 60, what if we wanted to get all of them, say, between 0 and 1? Well, that's what normalization does. If we come back up here, the goal of normalization is to change the values of numeric columns in the dataset to a common scale. Okay, beautiful. Now let's come back to the Keynote. Feature scaling. So we have some options here. Now, the scaling type of scale, a lot of different names are used for this, but I'm going to be referring to it as normalization. But if you hear scale features, typically they're referring to normalization. And what it does, converts all values to between 0 and 1 whilst preserving the original distribution. The distribution of our data is just the spread. So here we can see that the most values occur. What's this? This is BMI at about 30. And as we get towards the tails here, the values start to spread out. Whereas the distribution of age is pretty fair along all the values. Maybe most people in our sample are about 20 years old. So we come back here. Now, if we wanted to do this, we can do it with scikit-learn using the min-max scaler. And when should we use it? This is often used as the default scaler with neural networks, and it's the one we're going to get hands-on with. Another very common scaling type is standardization. What it does is it removes the mean and divides each value by the standard deviation. You can use the standard scaler scikit-learn function. And when to use this one? Maybe you want to transform a feature column to have a close to normal distribution. But remember, if we scale our features or standardize our features, this reduces the effects of outliers. So if we come back, this is a normal distribution. Let's have a look. Normal distribution. What does a normal distribution look like? All right, there, also known as a Gaussian. So we come here. If we were to change this age column to be a normal distribution, what would happen? It would reduce the effects of this outlier value here. So see how this column, if we reduce them all to be the shape of that, the tails we might lose out there. Now, what are we going to focus on? We're going to focus on normalization. So if we go here, in terms of scaling values, neural networks tend to prefer normalization. Now, how might we do this? Well, actually, let me just put a little tidbit here. If you're not sure on which to use, you could try both and see which performs better. Now, one more resource I want to show you before we actually get hands-on in code is Jeff Hale's article on scale, standardize, or normalize with scikit-learn. So this is a phenomenal article. I'll make sure it's in the resources section for you. But if you want to read through this for a bit more information on what scaling is, what the different kinds are, why you should do it. So here we go. Here's a great reason. Many machine learning algorithms perform better or converge faster when features are on a relatively similar scale and or close to normally distributed. Examples of such algorithm families include neural networks, which is what we're building. But we're going to see this. I don't want you, again, to just continually just learn from reading things. I want you to write code to see it for yourself. So let's jump into that. Enough talking, Daniel. All right, what's this first step? What should we do? We might import, we'll start again. We'll start fresh. So import pandas as PD, because I want you to be able to just come to this section in the notebook later on and just run it straight from here. Then we want to import matplotlib.lib.pyplot as PLT, and then import TensorFlow as TF. Wonderful. And then we'll read in the insurance data frame. So we go here, insurance equals pd.readcsv. We'll have to come back up and copy the URL, just the same URL we used as before. There we go. We're going to copy this one just to reinstantiate this data frame. That's all we're doing, so that we can start from scratch and see what pre-processing our data or normalizing our data does. Here we go. We'll make sure it's a string, and then we'll check insurance. Beautiful. All right. So we've discussed the concept of pre-processing data, normalization and standardization. We come back to the Keynote. We've discussed the names of them, but now it's time we're going to get hands-on. We've reinstantiated our insurance data frame. In the next video, we're going to go through normalize the numerical features, and we'll also prepare the non-numerical features as well, and then we'll fit our neural network. So I'll see you there. Welcome back. In the last video, we discussed the concept of pre-processing data in terms of normalization and standardization. Now we're going to get hands-on normalizing the numerical features of our insurance data frame here, and then we're going to build a neural network to learn on the features once they've been normalized. So let's see this in practice. Alrighty, how can we do this? So to do this, we're actually going to borrow a few classes from scikit-learn. So what I'll do is I'll code it up and talk through it as we go. You follow along as best we can, and then we'll discuss it once we've gone through it. So first of all, we're going to need, or actually, to prepare our data, we can borrow a few classes from scikit-learn. Wonderful. Okay, so from sklearn.compose, we're going to need make column transformer. Remember, you know how to look up the docstring of these things now, so you can see what these mean if you're not sure, but you could probably guess. Import, we're also going to need min-max scaler, and I'm not pulling this name out of the air, one hot encoder. If we come back to our Keynote, scale or normalization, we can use the min-max scaler in scikit-learn. So we come back. Now what we're going to do is create a column transformer. This is very helpful. So why do you think it might be called column transformer? Well, if you've guessed, because we have columns here and we need to transform them in some way before passing them to our neural network, you'd be correct. But let's see it in action. Let's call it just CT for column transformer. We'll run make column transformer, and we might just run this cell first so that we can see what the docstring is for make column transformer. Here we go. Construct a column transformer from the given transformers. And we come here, transformer estimator, columns, string. Where's an example? Example, here we go. So make column transformer, standard scaler. Oh, where have we seen that one before? That's this, standard scaler. And what else was there? One hot encoder. All right, so we're actually going to need both of those, but instead of standard scaler, we're going to use min-max scaler, which is transform features by scaling each feature to a given range. So the default is between 0 and 1, which is what we want with normalization. So let's see this in action. We're going to pass it the columns or the column names that we need to normalize. So let's put a note here. Turn all values in these columns between 0 and 1. Now, how did we know this? It's because when we look at our data, when we explore our data, we've got age here, we've got BMI, and we've got children. These are the numerical columns. We don't need to scale this, our target variable, but we might want to scale our feature variables. And we know for the sex, smoker, and region columns, we're going to one-hot encode them just as we've done before. So let's come down here. And now we need to make a one-hot encoder. And we're going to set this parameter to the handle unknown equals ignore. So this just means if there's any columns that the one-hot encoder doesn't know about, just ignore them. And then we're going to pass it the columns we want to one-hot encode. Smoker and region. Wonderful. So have all the brackets correct? Yes, there we go. Beautiful. Now we've got our column transformer ready. So as we pass our data through this, it's going to get min-max scaled on these columns and one-hot encoded on these columns. So now let's create our X and Y values because remember we just re-imported our data frame as a fresh. So X is going to be insurance.drop charges, and then we'll do that on the first axis. Y will be, what are we trying to predict? We're trying to predict charges. Beautiful. No typos there. And now, what do we want to do next? We've got our X and Y, but what do we want our model to learn on? Remember our 3 data sets? We want to train our model on some training data and evaluate it on some data it hasn't seen, in other words, test data. So the beautiful thing here is that we can use scikit-learns. Oh, we should put this up here from sklearn dot model selection import train test split. So now let's build our train and test sets. So we want xtrain, xtest, ytrain, ytest equals train test split x, y. Test size equals 20% of a test data set. And the random state we're going to set to 42 so that the split happens exactly the same as you can scroll up before as we did before. Otherwise, it'll be random and we'll get different results. So now we're going to fit the column transformer to our training data. So the important thing here is that whenever you have some sort of column transformer, you want to fit it to your training data and then use that fit column transformer to transform your test data. Because otherwise, if you do that separately, remember the test data is data the model has never seen before. So it's basically data from the future. So if we're transforming our training data set with information from the test data set, it's like taking knowledge from the future and altering the data that we have now. So let's go here, ct.fit on xtrain. Now we want to transform training and test data with normalization, min-max scaler, and one-hot encoder. So let's go xtrain normal for normalized equals ct.transform. So now we're taking what we've learned from the training data and we're transforming it. We're normalizing the features and one-hot encoding the features that we've defined up here. And now we've got xtest normal equals ct transform xtest. Beautiful. So now we've been through a fair few steps here, but when we break it down, we've just created a column transformer with the minimax scaler and the one-hot encoder. We've turned our data into features and labels. We've split our data into training and test sets. We've fit the column transformer to the training data only, and then we've transformed our training and test data with normalization and one-hot encoding. Let's see what, we got a typo here. Beautiful, that runs without errors. Now, we've normalized our data and one-hot encoded it. Let's check out what it looks like. What does our data look like now? So we want to go xtrain.lock. Let's look at the first one. Oh, sorry, we want to go, oh, well, that's what it originally was. So then if we go xtrain normal dot lock, oh no, maybe we just want the first one. Alrighty. So here's what we started with. Age is 19, sex is female, BMI 27.9, children, smoker, region. Now we've got a value here. I'm guessing that's the age. This must be the BMI. This must be the children. And now all of these other values are 1 or 0. Beautiful. So is that the same for another sample? And how about another sample? Wonderful. Well, what does the whole thing look like? Ah, it's all in numerical format. Now, what does that mean? Well, if you guessed, we can pass this to our neural network as all encoded data. You'd be 100% correct. So let's check the shapes. One more thing. Oh, we'll keep that sample there. And then we'll check the shapes of our data now. How has our shapes changed? So xtrain shape and xtrain normal dot shape. Ah, okay. So you see our xtrain value had 1, 2, 3, 4, 5, 6 different columns here. Well, now, since we've normalized it as well as one and hot encoded it, we've actually added some extra columns here. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Alrighty, so it looks like that our data is ready to build and pass to a neural network model. So what we might do is, actually, I'll write a text cell. We'll write beautiful, because it is beautiful. Beautiful. Our data has been normalized and one hot encoded. Now let's build a neural network model on it and see how it goes. So the challenge for you is to now build a neural network model to fit on our normalized data. So you probably want to build one similar to the insurance model we built before, just in the same way we've been doing it. Build the model, compile the model, fit the model, and then evaluate it. So fit the model on the training data set and then evaluate it on the test data set. So if you want to give that a try, go right ahead. But otherwise, we'll take care of that in the next video. Welcome back. Did you give it a shot? Did you try building a neural network to fit on our normalized data? If not, that's perfectly fine. That's what we're going to do in this video. So let's get started. We'll set the random seed so we can have as much reproducibility as possible. Let's set seed, 42. And now we're going to, step 1 is create the model. Now, if you scroll back up, you'll see that our best performing model is, or maybe you just remember, was insurance model 2. Now, if we get a summary of what that was, insurance model 2 dot summary, we're going to just reproduce the same model. Oh, another typo. But this time we're going to call it, so there we go, 3 layers, 1 dense of 100 units, 1 dense of 10 units, and the output layer of 1 unit. So let's reproduce this, and we'll make it insurance model 4 equals TF Keras sequential. And we'll come right to the start. We'll go TF Keras layers. We'll add the first hidden layer to our model with 100 hidden units. TF Keras layers dense 10 and TF Keras layers dense 1. There we go, we reproduced that. Now, what's the second step when we're creating our models? Step 2 is to compile the model. So we'll take insurance model 4.compile, and the loss function is going to be TF Keras losses.mae. And the optimizer is going to be TF Keras optimizers. We're going to use Atom because that's the same optimizer we use for model 2. And then we can go metrics equals MAE. Beautiful. Now, number 3, here's where the different part is going to be. So insurance model 2, we fit it on, if you scroll up, you can check it out, on unnormalized data. So we just fit it on xtrain only with one hot encoding. but not normalized. So to change the experiment, here's where we put on our experimenter hat. When we're running these experiments, we're just changing one small thing at a time. So the thing that we're changing in this experiment, insurance model 4, is the data we're using. Everything else remains the same. X-train normal, because we want to see, but it can still fit on the same labels. And we want to fit for the same amount of epochs. So we can still see, we only change one little parameter here, so we can see how that influences our model. Now you're ready? And go. Beautiful. Training is going to be nice and quick. All right. Okay. MAE 3636. Now we're going to evaluate our insurance model trained on normalized data. So we got insurance model 4.evaluate. Let's get it on. Now we have to evaluate it on the same type of data it was trained on. So that's an important point too, is because we trained it on normalized data, we have to evaluate it on normalized data. Shift and enter. Insurance, I keep typing N before A. There we go. How did it go? Okay, 3438. Now if we come back up to our insurance model 2, which was the best performing model so far, where was that? So there's insurance model 3. All right. So that didn't do too well on the test data set. Now, what we're after is insurance model 2. Oh, look at that. Evaluating the larger model. So if we copy this, let's copy this so we can compare our other model. If we were doing this properly, we might have saved the results of insurance model 2 to a variable, so we didn't have to go up and copy this. But let's make a code cell. So this is insurance model 2. Insurance model 2 results. Look at that. What a reduction. So that's 5,000 MAE. Just by normalizing our data, we've gone from 5,000 MAE to 3,500 MAE. That's incredible. That's a reduction of like 30% or so. So now I hope you're starting to see the benefits of all of the different hyperparameters we can tune with our model. So not only can we tweak how we construct our models, how we compile them, how we fit them, we can also tweak the data that we pass it to them. So if we come back and look at our Keynote, this is what we've done. We've done the scaling type. All we did was we convert the values or the target features that we wanted to convert to be between 0 and 1. That's all we changed. And we did that with about 10 lines of code here. And those 10 lines of code saw a reduction in error of about 30%. How cool is that? So that's the experimenter mentality that I want you to start developing throughout the rest of this course, is that the first result you get when you build a neural network model it's definitely not your last result, because there are lots of different things that we can tweak. We can tweak the model, we can tweak the data. We're going to have a lot more experience with this going forward, but that's one of the main benefits of normalization, is we see a faster convergence time. What that means is that our model gets to a better result. I mean, if we trained insurance model 2 for longer, say for 200 epochs, it might have reached this error rate here. But when we normalize our features, our models tend to converge faster. In other words, they get better results faster in less epochs. So, again, normalizing data doesn't guarantee improved results, but it's something worth trying because of how easy it is to implement. And in fact, in a lot of our pre-processing code that we do going forward, normalization will be built in, such as when we're dealing with images. Alrighty, so I think we have covered well and truly enough for neural network regression with TensorFlow. Have a look at this. Look how far you've come. You should be incredibly proud. We started by creating data to view and fit. We dealt with input and output shapes. We went through our steps in modeling with TensorFlow. If we come back, this big boy here, look at that. We went through all of these different steps. How cool is that? Now, we improved our models. We evaluated our models through visualization and evaluation metrics. We've run a whole bunch of experiments. We've loaded and saved our models. And we've even gone through a larger example from an open source data set. So give yourself a pat in the back. I've set up some exercises and extracurriculum activities to go along if you want to test your skills even further. I really encourage you to try out the exercises before looking at the solutions that come along with them. But otherwise, go back through all of the concepts if there was something you didn't really understand, practice it, write a bunch more code, get a few things wrong, see what works, see what doesn't, and I will see you in the next section. Neural network classification with TensorFlow. Now, before we get into anything, what we're going to cover or any code at all, I need to stress something. And that's, where can you get help? I'm going to be writing a bunch of code. We're going to be writing code together. So make sure you follow along with the code if you can. Remember our motto, if in doubt, run the code. Don't forget to try it for yourself. If you need the docstring, which is a bunch of information about the functions that we're going to be using. If you're using Google Colab, you can press Shift, Command plus Space, or if you're on Windows, this might be Control. If you're using Jupyter Notebook, it's probably going to be Shift and Tab. If you're still stuck, you can search for whatever problem you're having, and we're going to get a lot of practice searching for our problems as well, because that's what I want to stress. As much as we can teach in this course, you're still going to have to develop the skill of being able to search for answers to your own problems. Now, if you do search for it, you'll probably come across resources such as Stack Overflow, or probably more importantly, the TensorFlow documentation, since we're going to be writing a lot of TensorFlow code. And then after you've searched for it, try again. Rewrite the code if you have to. Look at the examples in the TensorFlow documentation and copy them out by hand and try them in your own notebook. And then finally, this is probably the most important out of all of these steps, is if you're still stuck, ask a question. Don't forget the Discord chat, and that means including those dumb questions that you think you have. All right? The person who asks the most dumb questions gets smartest the fastest. Oh, and actually, I want to add one more to this list, and that's the course GitHub. So if we come to here, GitHub. This is Mr. D. Burke, that's me, TensorFlow Deep Learning. This will have all the materials related to the course you're currently going through. I'll leave a link. At the moment, it's still a work in progress, but by the time you go through this video, it'll have a bunch more stuff and everything you need. Now, every notebooking concept we go through has a ground truth notebook. So, for this one, 02, Neural Network Classification and TensorFlow, this is the information we're going to go through. In the videos, we're going to be writing all of this code out. However, the notebooks here, so this one in the GitHub, have a lot more text around the code that we're writing. So if you want a more text-based explanation to go along with the videos and along with the code, so say in the video we just write this code, if you want all this annotation around it, be sure to check out the TensorFlow Deep Learning GitHub, and that'll have all the information you need. So without any further ado, let's get back to our keynote. And since we're covering neural network classification, you're probably asking yourself, what is a classification problem? Well, let's have a look at some example classification problems. The first one is binary classification. Is something one thing or another? Now, an example of this would be asking the question, is this email spam or not spam? That's actually probably a trend you'll see in binary classification. Is this thing something or not something? So here, we've got clearly a nice email to my email there, daniel@mrdburke.com. Hey Daniel, this deep learning course is incredible. I can't wait to use what I've learned. Oh, thank you so much. That's a beautiful email. I definitely want to see that in my inbox. So we might train a machine learning model or a neural network to classify this text as not spam. And then if I have this email here, which is, again, to my email, daniel@mrdburke.com. Hey, Daniel, congratulations. Oh, that's a 1. A bit of a typo there. You win a very large sum of money. As much as I'd like that large sum of money, that's probably spam, and I don't want to see that in my inbox. So that's binary classification. Now, another very common classification problem is multi-class classification. This is where you'll have a question such as, is this a photo of sushi, steak, or pizza? So we have a photo of sushi, we have a photo of a beautiful, delicious steak, and then a delicious pizza. Now, multi-class, as you might have guessed, is more than one thing or another. Now, we've got 3 classes here, sushi, steak, pizza, but in multi-class classification, we could have 100 different classes or 1,000 different classes, but the principle would still remain. Is this a photo of, so we had 100 different foods. Maybe we added over here a sandwich. So the principle would still remain. There's multiple different things that these photos could be of. So multi-class classification not only relates to different photos of food, it could be different photos of cars, it could be different photos of animals, anything you could imagine. And finally, another very common classification problem would be if you are asking, what tags should this article have? So here we have the deep learning article from Wikipedia. Now, maybe you want to, if you're Wikipedia, you want to sort your articles, because you have millions of them, into different categories. And so just labeling it with one category, such as deep learning, may not be enough. You want to relate it to other things such as machine learning or representation learning or artificial intelligence. So in this case, multi-label classification. Now, these two are going to be pretty confusing to begin with. You just need to figure out a couple of example problems to sort of start to understand them. But I know when I first started deep learning, I often got multi-class classification and multi-label classification mixed up. But the easiest way, or the way I remember multi-label classification, is that there's multiple label options per sample. That means that this one sample, this one article here, could have 3 different tags, or it could have 5 different tags. Whereas in these photo examples in multi-class classification, we only want one label per sample. So we have one photo, and the one label would be sushi. One photo, one label would be steak, and so on for pizza. Whereas in multi-label classification, we have one sample and multiple labels. So now that we've had a look at some of the most common classification problems you're going to come up against, binary classification, multi-class classification, and multi-label classification, let's have a look at the things we're going to cover, or specifically the things we're going to write code for. So here's what we're going to cover, broadly. Now I say broadly because these are just subheadings. What really matters is what we actually write code for. So we're going to look at the architecture of a neural network classification model. We're going to see the input shapes and output shapes of a classification model. In other words, the features and labels. We're going to look at creating custom data to view and fit. We're going to go through the steps in modeling, such as creating a model, compiling a model, fitting a model, and evaluating a model. We're going to see what different classification evaluation methods we have. And then finally, once we've trained some models, we're going to look at how we can save them and load them. And how are we going to do that? Well, we've seen this before, but we'll see it again. We're going to be cooks, not chemists. Cooks are very experimental. They try a whole bunch of different things, and they might measure something a little bit, but they're also going to just, if a recipe isn't going exactly how they want it, well, they're going to improvise. So that's what we're going to be doing. We're going to be cooking up lots of code. So now we've covered some example classification problems and what we're going to cover. In the next video, let's check out what the inputs and outputs of a classification model might look like. So, let's say we're working on a classification problem. And we saw this before, the idea of taking some photos, and then perhaps we're building an app that we want to be able to take a photo of whatever food we're eating and classify it as sushi, steak, or pizza. That's the app that we're building. What might our inputs and outputs look like? Well, we've kind of already got them here. Our inputs are going to be some kind of image of food. And then our ideal output, something over here, will be, if we took a photo of this one, we want it to be sushi. And if we took a photo of this steak, we want it to be steak. And then if we took a photo of pizza, pass it through our app, the ideal output would be pizza. Now, what might this look like in practice? So, all right, Well, here's our little scenario here. This is our machine learning algorithm that we might build, or deep learning algorithm. And we've already discussed what our inputs are and what our ideal outputs are. But what's the rule that we have to, before we can pass our inputs to our machine learning algorithm, or better yet, what does our machine learning algorithm like to look at? Can it understand photos straight away? Like if we just took a photo and just said, hey, machine learning algorithm, tell us what's in this photo. Will it be able to do that? Well, if you remember from a previous section, what do we have to do to our inputs before we pass them to our machine learning algorithms? Oh, maybe this is a little inkling. So if you're not sure, that's perfectly fine. But what this is so if we have a photo, let's say we already know what the width is and what the height is. So it's 224 by 224. So this is a square image. Now, what are we moving towards? We're starting to numerically encode what an image is. So we're starting to break it down from being just an image to being, okay, this is a 224 by 224 image. All right, we know a little bit more information about our image. So we know the width, we know the height. Oh, and what's C? We might know the color channels. So that's 3. So C equals color channels, red, green, and blue. So we might know that some combination of red, green, and blue pixels in 224 by 224, some combination of those different color values are going to give us this image of sushi. And the same thing for steak, and the same thing for pizza. Now, these width and height are arbitrary, but very often you'll change your numerical inputs of a machine learning model to have all of the same width and all of the same height when you're dealing with images. So what might we do before we pass these inputs directly to our machine learning algorithm? Well, we're going to turn them into a tensor. In other words, a numerical encoding. Now here, we've got normalized pixel values. So that means we've changed them to be whatever they were in terms of red, green, and blue, to be some value between 0 and 1. We're going to see this very hands-on in upcoming videos, so don't worry if this isn't making sense. The concept here is that we have images and we have to turn them into numbers in some way, shape, or form before we can pass them to our machine learning algorithm. And then our machine learning algorithm often already exists if we're using something like transfer learning. If not, we can build our own custom one. And then we pass it through. The machine learning algorithm is going to learn patterns in the data and then create some prediction outputs. So let's see here. What have we got? Okay, we've got another tensor, and it seems that the highest value here is highlighted for sushi. All right. But we get 0.00 for steak and 0.03 for pizza. Is that the first image? So that would be correct. Okay, that's great. But then this second image, the one of the steak, the highest value, it predicted sushi. And then these two values are lower for steak and pizza. So that would be wrong. This one, okay. So 1 out of 2, not too bad. And then this final one here, say this is for the pizza image. Same process again, turn it into numbers, pass it to our machine learning algorithm. And then it's got a predicted output here of 0.03, 0.07 for steak, and then 0.09 for pizza. So the highest values for pizza. And so that would be correct. Wonderful. Now, how does it generate these? Well, if we have a look, what are the actual outputs that we were looking for? In our case, we're building an application to classify different images of food. We take a photo of food, we run it through our machine learning algorithm, and then the ideal output is, for this photo is sushi, this photo is steak, and this photo is pizza. So, if we wanted our machine learning algorithm to be able to create predicted outputs like this, perhaps we can show it lots of different examples of images and their ideal output. Okay, so this is the premise of neural network or machine learning classification. This is our inputs over here. We numerically encode them, pass them to our machine learning algorithm, and then have some sort of output. All right. So the example we've seen here is for multi-class classification because there's one or more, each image or each sample can be one or another class. However, this premise of taking some sort of samples, numerically encoding them, passing them to a machine learning algorithm, and then have some sort of output, goes for all different types of classification inputs and outputs. So now we're familiar with the high-level overview of what a classification inputs and outputs will be. Let's have a look at what the shape of these tensors would be, because that's another very important point, as we'll see in practice later on. But before we do so, I want you to have a think about, if we've got these inputs, what might the shape of our input tensor be? And if we've got these outputs, or these ones here, what might the output shape of our output tensor look like? Have a think about that, and we'll cover that in the next video. Welcome back. In the last video, we checked out an example multi-class classification problem, or in other words, the inputs and outputs of what that type of problem may look like. So we had some images here, food images, and we wanted to take a photo of them and classify them as what's in that image. So in our case, we had sushi, steak, and pizza. We learned that no matter what classification inputs we have to numerically encode them in some way. So for an image, we grabbed the pixel values. So we learned that the width was 224, the height was 224, and there was 3 different color channels, red, green, and blue. And we figured out that we can turn those into a tensor and pass that to our machine learning algorithm. It's going to figure out some patterns in these input tensor or in the input images, and then create some predicted output that's based on looking at lots of actual samples of image to label pairs. So knowing that our inputs are in the form of a tensor and the outputs are in the form of a tensor, let's now have a look at what the input and output shapes of those tensors are, which is a very important concept. Because we're working in TensorFlow, all of our data is going to be contained within tensors. Inputs and outputs of our neural networks, of our deep learning models, of our machine learning models are all in tensors. And if they're the wrong shape, well, we run into errors. So this is for an image classification example. We're continuing off with what we just saw. We have our little setup here. Inputs, machine learning algorithm, outputs. We have our image of food, in this case is just the sushi one, and we know that the width is 224 and the height is 224, and there's 3 color channels, red, green, and blue. So what we might do is numerically encode this, pass it as an input to our machine learning algorithm, and it's going to output some kind of prediction probability. We haven't covered this, but we will see this in code later on. This is just more so the concept. Now, the reason why there are 3 options here is because we are building a multi-class classification image classifier, where the output could be sushi, steak, or pizza. And in this case, our machine learning algorithm has got this one correct because the highest value is for sushi. And that's what the input image is. Now, let's check out what or how our image would get represented as a tensor. So here we go. These might be the dimensions of our input tensor. Batch size, something we haven't covered yet, but that's all right. We'll see that coming up. Width, height, color channels. We have covered these. So the width here is 224. The height here is 224. And the color channels would be 3 for red, green, and blue. Now, the shape of this tensor will be, for batch size, might be none, 224, 224, 3. Do you see how the width value goes into here, the height value goes into here, and the color channels go to here? Or we might have a shape of 32 for the batch size, 224 for the width, 224 for the height, and 3 for the color channels. Now I've set 32 here because 32 is a very common batch size. All you need to know for now is that oftentimes when we're training a machine learning algorithm, depending on how much data we're working with and depending on the size of the computing chip that we're working with, it may only have enough memory to look at 32 samples at one time. So say we're working with 10,000 images, which is very common in image classification. Our machine learning algorithm may only look at 32 images at a time so that it doesn't run out of memory. And again, the reason why it's none or 32, 32 is very common. I think it's actually the default batch size in TensorFlow, but none is because this could be an arbitrary number. And it's important here that the width of this image isn't set at 224 and the height isn't set at 224. But again, these are very common values you're going to come across. So that might be what our input tensor shape looks like for a single image. Or if we have a batch of 32 images, it might be of this shape. And then if we have a look at our output, the shape of this might be 3 because we're dealing with multi-class classification and we have 3 potential classes. So that's the shape of this output tensor. Now, of course, this is for our image classification example. However, these shapes will vary depending on the problem you're working on. So say what if we had 10 different types of food here? What do you think the output shape would be? Well, it might be 10. And say this image was 300 by 300. What might change here? Well, the width and the height might change to 300 and 300. So we're going to get very hands-on with this going forward, but this is just to demonstrate conceptually what we have to do for our classification problems to work on them with deep learning and machine learning algorithms. We have to take our data, numerically encode it into some way, which is typically represented as a tensor, and because we're using TensorFlow, it will always be a tensor. And then the same with the output. Depending on what outputs we have to define them as some sort of tensor, and they will typically have a shape dealing with the number of classes. If you're working on multi-class classification, that is, the output shape will have the same number, or will be the same number as the number of classes we have. But again, this is just a conceptual overview. It'll start to make a bit more sense once we start to build classification neural networks. And speaking of which, let's have a look at that in the next video, what the typical architecture of a classification neural network looks like. Welcome back. In the last video, we had a look at what the input and output shapes of an image classification example might look like. And remember, this is specifically for an image classification example. These may change depending on the problem you're working on. So say we were working on text classification. Your input shape may differ to be the number of words in a string. So it may be 32 and then 100 for 100 words, and it won't have these dimensions over here. It'll just be one number for each word in that string. And then the same over here. Say we just wanted to classify an email as spam or not spam. We may have an output shape of 2. Again, lots of practice coming up, but just keep in mind, one of the big things for classification problems is defining the input-output shapes of our machine learning or deep learning algorithms. So now, speaking of those, let's have a look at what the architecture of a classification model might look like. We've got a little spoiler alert here. Here's some TensorFlow code. We've been very familiar with this in the regression section. However, we might notice a few different things. Oh, we've got input layer. All right. We've got activation. We haven't seen much of that. We've got another activation here, softmax. All right. What else is different? We've got loss. Okay. So we're familiar with these steps. 1, 2, 3, 4. The main differences you might see here is the loss function and the input shape and the activation. We haven't been hands-on with those just yet, but throughout the classification section, as you might have guessed, we definitely are going to be. So now, it's important to note that this is a typical architecture of a classification model, and we're going to building lots of these. So although I'm giving you sort of a guideline as to what these architectures may look like, they definitely vary depending on the problem we're working on. However, this is pretty universal. And again, this is adapted from page 295 of the Hands-on Machine Learning with Scikit-Learn, Keras, and TensorFlow book by Aurélien Guérin. Highly recommended that book. It'll be in the extra curriculum section of this course. So let's take a look at what's going on here. We have hyperparameters, and remember, a hyperparameter is something that we can adjust ourselves as developers. And we might have a binary classification problem and a multi-class classification problem. Now, note here, we haven't got multi-label classification. However, multi-label classification architecture is often very similar to a multi-class classification. So let's start with the input layer shape. If we go here, and all of these colors are going to activate for me automatically, aren't they? But that's all right. We'll step through it one by one. Input layer shape we have here. TF-Keras input. So here's where we're defining the input layer shape. Do you remember in just the previous example we looked at before? It might be the same number of features, e.g. 5 for age, sex, height, weight, smoking status in a heart disease classification problem. But we looked at an image classification problem. So here we might have the input shape of a particular image might be width, height, number of color channels. So that's what our image looks like in tensor form. Again, this shape will change depending on the problem you're working on. Now for multi-class classification, it's going to be the same thing as binary class classification. Now hidden layers, again, this is plural on purpose. We've got one here, and this is problem specific, what you set this to. The minimum is going to be 1, the maximum is unlimited. So I think we're actually going to be working with a neural network with over 100 layers. That might be in this section or a later on section, but this one just has one hidden layer there. And for multi-class classification, we can look at the same value here. It can be 1 or up to unlimited. Neurons per hidden layer, that's this green value here. Problem specific, generally 10 to 100. Again, this can wildly vary depending on what you're working on. In our case, we've set 100 here to the hidden layer. And for multi-class classification, we've got same as binary classification. Now the output layer shape. For binary classification, it's going to be 1. So remember, binary classification is something one thing or another? Is this email spam or not spam? So we want the output layer shape to be 1. And multi-class classification is going to be 1 per class, e.g. 3 for food, person, or dog photo, if we were working on an image classification problem to decide whether a photo was of food, of a person, or of a dog. And that's the value we've put here, 3. So in our case, this input shape might actually work for this problem here. This output shape. But the input shape would also work because it could potentially, if these images, so the images of food, of a person or a dog, were 224 pixels wide, 224 pixels high, and had 3 different color channels. Once we'd turn them into tensors, of course. Now we have here the hidden activation. So this is the hidden layers. So the activation function that we have within the hidden layer. So it's often defined with the activation parameter. Now it's usually ReLU, which is rectified linear unit. We haven't seen that before, but if you want to go ahead and do a little bit of research before we get into coding, feel free to look up ReLU. And again, same for multi-class classification. We're going to use now again, there are multiple different hidden activation functions, but I say usually ReLU because that's what you're going to see very often, and that's what we're going to be using throughout the course. Now, output activation. This is the activation function in the output layer. Again, a concept we haven't really covered so far, but I'm just making you aware of what the names of these things are. So for binary classification, we're probably going to be using a sigmoid activation for our final layer. And for a multi-class classification problem, we're probably going to be using a softmax activation, which is what we've got here. All right, so this architecture looks like it's for multi-class classification. Now, loss function. Across the board, we're going to be using cross entropy, which is a loss function for classification problems. Now, for binary classification, we're going to be using binary cross entropy in TensorFlow. And for multi-class classification, we're going to be using categorical cross entropy in TensorFlow. So it looks like here, when we compile our model and define the loss function, we've used TF-Keras losses categorical cross entropy, which makes sense because we discussed before that this is a multi-class classification architecture. And as for the optimizer, we're going to use old faithful stochastic gradient descent, or another old faithful is Atom. So actually, I think we might test out both of these, but I think we're probably going to be sticking with Atom because Atom is safe. And then we go here, multi-class classification, same as binary classification. All right. So that's a typical architecture of a classification model. Again, a lot of things here that we haven't necessarily covered, but we are going to be getting hands-on building a lot of these. And I think that's what we've got here. Yeah, we're going to be building lots of these bad boys. And the reason you might be wondering why I said Atom is safe, I want to reveal that. So let's go here. Andre, here's another external resource, neural network recipe. I'll put this in the extra curriculum. A recipe for training neural networks. So this is by Andre Karpathy. If we go here, Atom. A few tips and tricks for this stage. Atom is safe. In the early stages of setting baselines, I like to use Atom. He's talking about the Atom optimizer with a learning rate of this. Atom's learning rate is actually very good in TensorFlow. It's default one. In my experience, Atom is much more forgiving to hyperparameters, including a bad learning rate. For convnets, a well-tuned stochastic gradient descent will almost always slightly outperform Atom. So again, a lot of things here you might not be aware of, but just know Andre Karpathy is saying Atom is safe, and if you're wondering who Andre Karpathy is, let's go to About, see my website. I am the Senior Director of AI at Tesla. So Andre knows his stuff about deep neural nets. So if Andre says Atom is safe, we're going to trust him. But anyway, actually, let's be skeptics. Let's not trust Andre and let's test it out for ourselves. So in the upcoming videos, we're going to get... Oh, actually, I had a little demo of what was happening here. So here's our inputs. They get encoded into tensors of this shape. And then here's our outputs. So that completes that slide. But with that being said, we've talked enough. Let's code. Now that we've looked at what a classification problem is, what some tensor input and output shapes might look like, let's get hands-on and start to code some classification code. We're going to start a new notebook at Colab. Wait for this to load up. Beautiful. Now I'm going to call this one O2 neural network classification with TensorFlow, and I'm going to add the video tag so that you know once you see this notebook in the GitHub that this notebook was made during the recording of videos. Remember, we've got in the GitHub the ground truth version of this notebook. Doesn't have the video tag on the end here. But we'll get out of that. So let's write here. Introduction to neural network classification with TensorFlow. So in this notebook, we're going to learn how to write neural networks for classification problems. And remember, what's the definition of a classification problem? A classification problem is where you try to classify something as one thing or another. And there's a few types of classification. You've got binary classification, multi-class classification, and multi-label classification. And we've got here a few types of classification problems. Now, we'll turn this into Markdown. I'm going to press Command MM. You might press Control MM if you're on Windows. So, we've got a little intro here. Now, the first thing we might have to do is, before we can write any code, is we need some data. So how about we write a title here, Creating Data to View and Fit. Now, there's a lot of toy classification data sets out there, but I always like creating our own and getting a model to work on our simple data set before moving on to an actual problem. So it's like a rehearsal experiment before our actual experiments. How about to make some data, we can go from sklearn.datasets, import make circles, and then we'll go here. We want to make 1,000 examples. So we want 1,000 different samples of data, and we can create circles. Oops. N samples equals 1,000. And then if we should go down to here, create circles, x, y equals make circles, n samples. Again, you could change this to 10,000 if you wanted to, or 100. I'm going to stick with 1,000. That's a good number. and samples, noise can be 0.03, and random state can be 42 if you want to make this reproducible, so we have the same data. Now you might be wondering, Daniel, we've never used make circles before. And you'd be 100% correct. This is the first time we've used this in the whole course. But how do you get help on something if you weren't sure? We want to press Command, Shift, Space. Def make circles. So make a large circle containing a smaller circle in 2D. A simple toy dataset to visualize clustering and classification algorithms. Beautiful. So if we really wanted to figure out what this is how to make example classification data with sklearn. There we go, an introduction to machine learning with scikit-learn, examples. So we've got a few options there. I've just chosen, that's basically what I did when I found out about this make circles function. And there's probably a way to do that in TensorFlow. I'm not quite sure if it's as quick as this one, but if you want to give it a try, once you see what this data looks like, feel free. So now let's check out the features, which is under the X namespace, usually a capital X. Okay, so we have an array here, and let's check out the labels. Check the labels. All right, ones and zeros. So we've got two options here. I'm guessing one of these samples here, so this is a sample, has this label, number 1. And another sample further along here, say this one, has this label 0. We might just make this a bit smaller. I'll check the labels, that's what we want there. So if we have two label options and we're working on a classification problem, which one of these three are we working on? Is it binary? Is it multi-class? Or is it multi-label? Well, it's not multi-label because each one of these has one label. So each sample has one label. And it's not multi-class because there's only 1 or 0. So this is a binary class classification problem. But if we're looking at our data like this, I mean, I could look at this. I've used this before, so I kind of know what this means. But if you're looking at this for the first time, it might not make sense. So what's our Data Explorer's motto? Come back to the Keynote. The machine learning, or even the Machine Learning Explorer's motto. Visualize, visualize, visualize. And what's the first thing we should visualize? The data. And we could visualize the model, the training, predictions. And it's a good idea to visualize these as often as possible. So let's see how we might visualize our data. Let's write ourselves a little note. Our data is a little hard to understand right now. Let's visualize it. So to get it into a structured format, I'm going to import pandas as PD. Then I'm going to turn it into a data frame called circles. pd.dataframe, and I'm going to label it x0 for this element here, or this sample here. And that can be x, all of the items in the 0th axis. And then x1 can be x, we want all of the items in the first axis. There we go. And then we want the label column to be y. There we go. And let's look at our circles data frame. Typo there, of course. Circles, beautiful. Okay, so now this is a little bit easier to understand as it is. We've got x0, x1, so we have two features per label. And so this coordinate, 0.754246 and 0.231,481 has the label of 1, and so on, times 1,000, because we set n samples to 1,000. Now, this is still a little hard to understand. I wonder if we can visualize this with a plot. Let's try that out. Visualize with a plot. So how might we do that? Import matplotlib. I like to visualize as much as possible before I start writing neural network code. plt.scatter. We want a scatter plot. Scatter plot's a very good plot. We're going to just plot this, and the color can equal Y, and the CMAP can equal, this is just the color layout. I want it just to be red, yellow, blue. I think that should do. Let's have a look. Oh, look at that. Now, so seeing this, if we read the docstring of make circles, has it done what it says it's going to do? Make a large circle containing a smaller circle in 2D. I think it's done that. We have a large circle and a smaller circle. Now, from this plot, can you tell what type of model we're going to build? It's okay if you can't, but I just guess. Like, what are we trying to do here? What would we try to do? I'm giving you a little hint here by running my pointer in between the two circles. How about we build one to classify red or blue dots? So in other words, we want our model to potentially draw a line right through the middle of these two. So if we were trying to predict on another 100 rows and we had values like this, would they be a 0 or a 1? Would they be red or blue? Now, I want you to think about, before we go ahead, this is just a conceptual thing. What is the difference between the data we're looking at here and the data we've looked at in our regression notebook? So if we start a new tab, what is a regression problem? And then if we went to images, what's the difference between this data here and this data here? So have a think about that. Just look at this, like Google regression problem, check out the images, and just have a think. What's the major difference between our two types of data here? And one more thing before pushing forward, so that's your challenge, just to compare these two types of data. I want you to have a look at TensorFlow Playground. Oh, .org, not .com. Here we go. Tinker with a neural network right here in your browser. Don't worry, you can't break it. We promise. So again, we've got a little few options here over what data set we want to use. And what's this one look like? I mean, we've got a few. Watch them change over here. We've got this one. What's the similarities between this data set and this data set? So your two exercises before the next video is to compare this one here. You might have already done that because we've talked about it enough. And then the other one is to spend 10 minutes at playground.tensorflow.org playing around with all the different parameters here. Try changing the learning rate, the activation, the regularization. Doesn't matter if you're not sure what these things are. Press play, change the number of hidden layers here, change the number of neurons, and see what happens with this data set here. So give that a try, and I'll see you back here in the next video. How'd you go? Did you play around with the neural network playground? I've just added a little exercise here with this hammer and spanner emoji. If you ever see that throughout the course, that's an exercise. So before pushing forward, spend 10 minutes playing around with the playground tensorflow.org, building and running different neural networks. See what happens when you change the different hyperparameters. So if you haven't done that yet, give that a try and then continue the video. But otherwise, we've created some data, we've visualized it. Now, what's another important point is the input and output shapes of our neural network. So let's inspect our data. So check the shapes of our features and labels. So what's our features shape and our labels shape? Wonderful. So we have 1,000 samples of X and 1,000 samples of Y, and X has a shape of 2 because there's 2 samples, whereas Y is just because there's one output. These are scalars, so they don't have a second dimension here. They're just one value. All right. So if we wanted to check how many samples we're working with, is just len X, len Y. And if we want to view the first example of features and labels. So again, we're just becoming one with the data here. We're really just familiarizing ourselves with what we're trying to do. We've already seen a few of these things, but just for completeness, we're putting this here. So okay, we've got 2. Here's what we're trying to do. We're trying to take this point, feed it to our neural network, and generate an output, something like this. And let's say, can we get another one with a 0 label? Are we going to get a 0 label? Nope. I believe the 5th one may have been. No. All right. So some of these values here for x have a label of 0. That's all you have to know for that. Now, we've checked the input and output shapes. What might be the steps or the next steps? So steps in modeling. We've practiced this with our regression problem. So now that we know the input and output shapes, how might we build a neural network to classify whether something is a blue dot or a red dot? So how about we go back to our Keynote here and steps in modeling with TensorFlow. We reveal our beautiful, colorful picture. Step 1 is get data ready, turn it into tensors. Well, we kind of have that, except they're in NumPy arrays at the moment. But remember, NumPy arrays work beautifully with TensorFlow. So we'll say that we've finished this one. Now we have to build or pick a pre-trained model to suit our problem. Well, in our case, we're going to build a model. So we have step 1, create a model specified to your problem. We might have to define the input shape here. Or sometimes Keras layers can automatically infer the input shape. Then we might have a hidden layer and an output layer. What would our output layer shape here be? If we come back, we only want to predict whether it's one thing or another. If you remember back to the slide where we talked about the typical architecture of a classification problem, that may give you a hint because we're working with binary classification. Then we want to compile the model. That's step 2. I nearly said fit the model, but we have to compile it after we create it. Remember step 2, Daniel, come on. Now, if we're working on binary classification, what might our loss function be? What optimizer could we use? What metrics could we use? And then once we fit the model, okay, that seems like we've got that set up. We've got X and Y. Well, we haven't got a training data set actually, have we? Or a testing data set. We might just stick with X and Y for now. All right, so now we've got the steps here, 1, 2, 3, 4. I'm going to issue another challenge. We've got X and Y. See if you can create a model with what we've learned so far. Refer back to the slide where we talked about the architecture of a classification model. And write some neural network code with TensorFlow. Give it a go. And I'll come back in the next video and we'll write a neural network classification model together. So in the last video, we checked out what the input and output shapes of our data may be. And we also had a brief overview of what the steps in modeling with TensorFlow are. So how about we start to implement those? So remember, the steps in modeling are number 1, or the steps in modeling with TensorFlow are typically 1, create or import a model, 2, compile the model, and 3, fit the model. And then the 4th one is evaluate the model, etc. 5 is we usually here will tweak, 6, evaluate, etc., etc. Tweak, evaluate, tweak, evaluate, tweak, evaluate. But let's focus on these first 3. We'll get these first 3 done for our classification problem. So how about we start? Set the random seed, tf.random set seed. Now what's the simplest model we could start with? How about we just start with 1 hidden layer. We'll go create the model using the sequential API. So we go model 1 equals tf Keras sequential, and then we'll add a single dense layer. Wonderful. And then what's step 2 after we create a model? We have to compile the model. So model 1, because compile. Here's where it's going to be different from the regression models that we've built. And now before I write the code, I want you to refer back to this slide here. The typical architecture of a classification model. Where are we up to? Well, we're compiling a model. We have to define the loss function and the optimizer. So if we look back at what we're working on, what are we working with? Are we working with binary classification or multi-class classification? Come back to our problem. What does it look like? Red or blue dots? So it is binary classification. So what might our loss function be? Before I write it in here, I'd like you to give it a try. Have a look at this and see what it might be. Did you give it a go? If not, that's all right. Let's write it down. Loss equals tf_chars losses dot binary. Is this going to autocomplete for us? Cross entropy. I believe it might be capital E, but we'll find out in a second. It'll error for us. Now the optimizer. What optimizer do you want to use? tf_chars optimizers. We come back to our typical architecture of a classification model. We can use SGD or Atom, or really there's actually a plethora of optimizers we could use, but these two are the most common you'll see in practice. We'll start with SGD. And the metrics is going to be, we haven't looked at classification metrics yet, but we'll get very familiar with them. Actually, what would you do if you wanted to know different classification metrics? I've put accuracy here, that's a bit of a spoiler, but let's go how to evaluate a classification model. Here we go, evaluating a classification model. What does this tell us? Richie NG. Oh, look at this. Topics. Review of model evaluation procedures, model evaluation metrics. Okay. Model evaluation metrics. Boom, classification. Classification accuracy. There are many more metrics and we will discuss them today. Classification accuracy. All right, beautiful. So then we got a few more options. We could keep going through that if we wanted, but we're just going to stick with accuracy for now. And accuracy is just basically out of 100 examples, how many did our model get right? So what percentage? And now if we go here, we want to, well, step 3, fit the model. So we have model1.fit, we have X and Y, and we're going to fit for maybe just 5 epochs. So we got the first 3 steps here. And all we've done is we've just followed this. The architecture of a classification model. We've just implemented this in TensorFlow code. So we're ready to run this. Hopefully there's no errors. 3, 2, 1. Oh, TF is not defined. That would help if we imported TensorFlow. Did you catch that? Let's write some code here. We'll get rid of this. I want to import TensorFlow. Can't write TensorFlow code without TensorFlow. Import TensorFlow as TF and check our version. By the time you watch this, your version might be higher than mine. Right now, I'm running 2.3.0. As long as you've got 2 point something, all the code should work in here. And let's see if this runs. We got this wrong. So what is it? Tab. Is this going to autocomplete for me? So maybe it's just a little e, and I think this is on the end. There we go. Fits nice and quick because we're only working with 1,000 samples, but what's our accuracy? 48%. This is percentage, by the way, because we've set up accuracy here. So that's saying that on average, out of 100 examples, our model only gets 48 right. Now, what does that tell you? If we're working with a binary classification problem, so we're trying to predict whether something is one thing or the other, basically heads or tails, and our model is only 48% accurate. It's basically guessing. So it's just going up here. It's looking, we have red or blue, and 48% is basically 50%. So it's just going red, blue, red, blue, red, blue, red, blue, red, blue, and you'd get about 50% correct. Well, that's not very good. How might we improve it? What are some steps to improve our model? I got an idea. How about we train it for longer? So let's try and improve our model by training for longer. So we come here, model1.fit. We can just take it straight away. And epochs equals, let's do another 200. And this time we'll turn verbose to 0. So 200 epochs should be enough for our model to figure out the patterns in our data. We've only trained for 5. Let's really step it up. Model1.evaluate x and y. Maybe you're going to catch what I'm doing wrong here. We'll reveal that after. But if you have a look at what we're doing here, fit and evaluate. I'm doing a cardinal sin right now, but that's all right. This is just to exemplify what's going on. Let's see what happens. So it took a little while longer to fit because we're training for 200 epochs instead of 5, but we ran evaluate and now we have loss. So the loss is 6935 and the accuracy is 5 or 50. So 0.5 times that by 100, that's 50. Only 50% accuracy and we trained for 200 epochs. What is happening? Okay, I know how we can really step things up. What if we added another layer and trained for longer? Yeah, that's a great idea. Our model is performing as if it's guessing right now. Let's write that down. Since we're working on a binary classification problem and our model is getting around 50% accuracy, it's performing as if it's guessing. So let's step things up a notch and add an extra layer. Yeah, that worked in our regression problem. It should surely work here. So we'll set the random seed, tf.random.setSeed, and we'll go to step 1, create a model, this time with 2 layers. Model 2 equals tf keras sequential. Open up the brackets there, square brackets and curly brackets, tf keras layers, dense. Woohoo! This data set ain't going to know what hit it. Binary classification, 2 different types of labels, 2 layers. And now, what do? After we create a model, we have to compile the model. I'm going to go model2.compile. What's our loss function? tf keras losses, because we're dealing with binary classification. It's binary cross entropy. Little quiz. What would it be if we're dealing with multi-class classification? Optimizer, we're going to keep the same. We're going to use SGD, stochastic gradient descent, and the metrics we're going to set to be accuracy. Oh, this is going to be so much better. Fit the model. All right, model2.fit x, y. By the way, if you already guessed what we did wrong up here, we fit on the same data that we evaluated on. What should we ideally do? We should fit on training data and evaluate on testing data. But, well, because we're working with a toy problem, we're allowed to fudge what we're doing a little bit here. And now epochs. What should we do? Maybe 100. That should be enough. We've got 2 layers. I mean, this model should be great. Ready? Let's run. Now, number 4 can be evaluate the model. Because we set verbose equal to 0, we don't have very much output, but we should have a trained model 2. Evaluate, again, evaluating on the same data we trained on. Not ideal, but in our case, we're just trying to see if our model's learning anything. What? The loss is about the same, even with an extra layer, but the accuracy is still 50. So right now, our model is still not even as good as guessing. Like, it's getting 50% accuracy. Like, you could do that if you just, for every sample, if you had 1,000 samples, if you just guessed, let's see how many there are. Let's go here, code, and circles, label, which is y, value counts. So 500 and 500. If we just literally went and tried to guess red, blue, red, blue, red, blue, we'd be getting the same results as our current neural network with 2 layers. This is preposterous. What we should do in the next video then is that if our model's still only getting guessing results, we need to pull out a few more bags of tricks to improve our model. So, have a think about, refer to our architecture of a classification model and have a think about some of the things using my cursor in an area that might reveal something to you, by the way. Have a think about some of the things that we haven't yet included in our model and see if you can figure out why our model hasn't learned anything yet. But if not, I'll see you in the next video and we'll see how we can improve our classification model. All right, so we've built a few classification models so far, namely Model 2 and Model 1, which is a little bit further up. There we go. However, we've seen that despite adding an extra layer, Model 2 is still performing very poorly. I mean, it's getting 50% accuracy on our binary classification problem. And since we've got an even amount of samples for each class, so if we look here, we've got 500 samples of number 1 and 500 samples of 0. Now, or 500 samples of a blue circle and 500 samples of a red circle. Now, if you were to toss a coin 1,000 times, you kind of expect about 500 heads and 500 tails. Hence why our model is essentially guessing. So we have to look into our bag of tricks to see how else we can improve our model. So let's look into our bag of tricks to see how we can improve our model. Now, recall back from the previous section where we went through the steps in creating a model, or the steps in building a model, that is. But as you might remember, there are steps from within each of those steps that we can try to improve our model. So if we go create a model, that's number 1. 2 is compiling a model, and 3 is fitting a model. What can we try here? So when we create a model, we might want to add more layers or increase the number of hidden units within a layer. We've seen this. We actually tried this. We didn't increase the number of hidden units for Model 2, but we did increase the number of layers. So we went from 1 layer to 2 layers, and that didn't really improve our model. What else could we do? Compiling a model. So here we might want to choose a different optimization function, such as Atom instead of SGD. Now, what optimization function did we use for Model 2? We used SGD, so we might actually, Atom could be the next thing that we try there. And then fitting a model. So perhaps we might fit our model for more epochs. So leave it training for longer so that it might get a better understanding of what's going on or the patterns in our data. Now, these steps have just come from, if we refer back, this is what we've been through so far, steps in modeling with TensorFlow. Number 1, create a model. We've created a few models here. I want you to think about this one in particular, actually. There's a little part that we haven't quite covered yet, and it may or may not hold the keys to why our model isn't improving, but I'll let you have a think about that before we discuss it. Number 2 is compile the model. So we define the loss function, in other words, how wrong our model's predictions are. We define the optimizer, which is how our model should update its internal patterns to better its predictions. We define the metrics, which is a human interpretable values for how well our model is doing. We fit the model and we evaluate it. But now if we have a look at how we might improve our model from a model's perspective, we've got a few different ways. Adding layers, we've tried that. Increase the number of hidden units, we haven't tried that. Change the activation functions. We definitely haven't tried that, at least for the hidden layers. Change the optimization function. We could use SGD or Atom or one of the other optimizers in the optimizers package. Change the learning rate. We haven't tried that. Okay, so we've got a fair few things here that we could try. Let's start implementing some of these. And remember, because these are hyperparameters, or because these are changeable, they're called hyperparameters. So if we come back, instead of staring at our slide, let's write some code. How about we increase the number of hidden units? Yeah, and we'll add an extra layer. Let's do that. Set the random seed. So tf random.setSeed. I want to emphasize as well is that if you're thinking, well, Daniel, we don't really have a structure to what we're doing here. We're just trying things and seeing if they work. I mean, you're exactly right in thinking that. And that is a lot of what machine learning and deep learning is. Trying things and seeing if they work. Hence why our machine learning practitioner's motto is, I'm just creating a sequential model here, by the way, and I'm calling it Model 3. But our machine learning practitioner's motto is experiment, experiment, experiment. Now, we've created a first hidden layer here, and we're creating 100 hidden units in this one. So we're stepping it up from Model 2. If I create a new cell, oh, I've turned that into Markdown. I don't want that. You can turn it from Markdown back into code, by the way, by going Command MY or Control MY if you're on Windows. Kara's layers dense, wonderful. And we'll have the final layer there. So if we check Model 2, what we've done here with Model 3 is we've added 10 hidden units to the middle layer, and we've added an extra layer this time with 100 hidden units. So I'll put there, add 100 dense neurons, and this one is add another layer with 10 neurons. All right, this one should definitely work because we've stepped it up a notch here. I mean, if our model with 2 layers didn't work and only 1 hidden neuron, well, it definitely should work with it with 3 layers and over 100 hidden neurons now. Compile the model. So Model 3, compile. What do we have to do for compile? We define the loss function, which is how wrong our model's predictions are. For a binary classification problem, we use binary cross entropy. And then the optimizer. Oh, this time I think we might also change Atom or change to Atom from SGD. Let's try that out. Why not? Metrics equals accuracy, which is a very standard baseline classification metric, but may not be the best one depending on your problem. We'll see other classification metrics in a future video. Oh, 2 equals there. We don't want that. And now we're going to fit the model. Oh, I can't wait to see the results of this one. 3 layers, over 100 hidden units equals, let's go for 100 epochs. What do we do Model 2 for? I think we only did 5. Oh no, we did 100 as well. So we'll just do 100 this one. Verbose equals 0, so we're not outputting a lot of information. And shift and enter. Did we get any errors? No. Beautiful. All right. So let's see how number 4 is evaluate the model. So again, not necessarily a great idea to evaluate on the same data set that we've trained on, but for this toy example, we'll keep it like that. Shift and enter. What? Bow, bow, bow. What? We're still getting 50% accuracy. We've pulled out our few tricks. We've changed the optimizer to Atom. We've added an extra layer, this time with 100 hidden units, and even another one with 10 hidden neurons. We're still getting about 50% accuracy, so just as good as guessing. You know what we're going to have to do? We're going to have to visualize. What do you think we should visualize in this case? If we want to see how our model's performing and the evaluation metrics are telling us it's not performing pretty well, what's another thing that we can visualize? How about we visualize the predictions? Yeah, I think that's a good idea. So in the next video, we'll make some predictions with our trained model and see, we'll plot them against, where's our graph? Here. Yeah, let's make some predictions on this graph and we'll plot what our model's predicting, how to separate these blue and red circles, and we'll see what they look like, just so we can understand what our model is trying to, or what the pattern our model is trying to figure out between these 2 circles. I don't think it's very good. So give that a play around. Maybe you want to try a few more things before we plot those, but otherwise, I'll see you in the next video. In the last few videos, we've been building models to try and classify our toy dataset here of blue and red dots. However, they're all performing pretty poorly. Like, I mean, as good as guessing. Even we've pulled out a few tricks to improve our models. So what we're going to do in this video is, if we come back to our Keynote, And we remember our Machine Learning Explorer's motto: visualize, visualize, visualize. It's a good idea to visualize these as often as possible. We visualized our data, we know what it looks like. We visualized our model, we know the layers and the different components of that. We've seen it train. We haven't plotted a loss curve just yet, but we don't need to because we know it's performing poorly. So let's try visualize some of the predictions that our model is making. Now, how might we do that? We could do it like this. We could go model3.predict x and see what's happening. All right, we get some values there. They're all sitting around, that's a little inkling. They're all sitting around 0.5, but we want them to be closer to 0 and 1. All right, so that's a little inkling there, but I prefer to see things visually. So let's get rid of this. And to do so, what we might do is make a function, a plotting function called plot decision boundary, where what we want is, do you remember with our regression model, we had some data that was like a line, and then we plotted our model's prediction as a line compared to the actual data? Why don't we do the same thing but with this circular data? Plot our model's predictions against the actual data. So to do so, let's create a function right here to visualize our model's predictions. Let's create a function. I'm going to call it plot decision boundary, because a decision boundary is just basically where's our model deciding where the bounds are between red and blue dots. And this function will, that's a better option. So we need to take in a trained model, features, x, and labels, y. So those are the parameters. And then it'll create, might turn this into Markdown actually. Create a mesh grid. If you're not sure what a mesh grid is, it's a concept in NumPy. So NumPy mesh grid. That's what you can do for anything that you're not sure. Just search it up and have a little play around and figure out what it is. NumPy mesh grid. You could read the documentation there, or we could just practice coding it. Create a mesh grid of the different x values. And then we're going to make predictions across the mesh grid. And then finally, we're going to plot the predictions as well as a line between the different zones where each unique class falls. Now, right now, these steps are all just in English. They may not make sense. So let's start to write code for it. We'll go here, import NumPy as NP, and then we'll create our function, def plot decision boundary, model x and y, and there we go. And then we're going to put in a little doc string here, so we're being nice and Pythonic. So plots decision boundary created by a model predicting on x. Beautiful. So the first thing we have to do is we've taken in a trained model. So there's our model parameter, there's our features, and there's our labels. Now, let's define the axis boundaries of the plot and create a mesh grid. So we want the x minimum and the x maximum is going to be, we can index on x to get both of these values. So we just want the 0th axis, the minimum, and we're going to minus 0.1 to give ourselves a little bit of a margin. And the same thing with the maximum. So we just want the 0th axis, and then we take the max, and then we're going to plus 0.1 to give ourselves a little bit of a margin there. And then we can do the same thing for the y min and the y max, except we're going to index on x and get the first axis. Dot min, the minimum, and the same thing here. Semicolon, 1 dot max plus 1 for a little bit of a margin. Now, if you're not sure what these values are, what can you do for any type of function? You can just take the code, copy and paste it, or probably better to write it yourself, and then xmin to visualize them. This is what we want to look at all the time. Line by line. I'm not going to deconstruct this function line by line, But if you wanted to understand any function, this is what I do. I take the line by line, and then I visualize it in a single cell. So here's the values. These are our boundaries. And now we can create the mesh grid. YY equals, now again, this is coming straight from the documentation here for mesh grid, is np.meshgrid. And then in here, it takes linspace. Now, how do we figure out what something does? We can do Command Shift Space. Oh, we haven't imported NumPy yet. That's why we can't run this function or can't get the docstring. We'll import NumPy up there and see what linspace does. Here we go. Return evenly spaced numbers over a specified interval. Okay. So if we did 0 to 10, it might return evenly spaced numbers between 0 and 10. Beautiful. But we want evenly spaced numbers between our xmin and xmax, because this is going to be the first parameter of our mesh grid. And then we want the same thing for ymin, ymax. And then we're going to go 100. So here's the minimum, here's the maximum. Return 100 values evenly spaced between xmin and xmax. And create a mesh grid out of this one and this one. If you want to see what that looks like, again, you can copy this and probably put it in a code cell below. Otherwise, let's push forward with the function. There, we've created our mesh grid of the different x values. Now, it's time to create x values. We're going to make predictions on these. So, x in equals np c. Now we want to unravel xx by passing it to ravel, yy, ravel. And if you're not sure what c does, you can go, what can we do? NumPy.c. User manual. Translates slice objects to concatenation along the second axis. So if we pass it in two arrays like this, what does it do? They were stacked and now horizontal. So that's what's happening here. So stack 2D arrays together. Now we're going to make predictions using our trained model. We've passed it in with the model parameter here. So we go ypred, which is our usual variable name for any type of predictions. Model.predict xin. Alrighty. And now we're going to add a little bit of functionality here that we can check for multi-class. We're working with binary classification, but let's check for whether we're working on a multi-class classification problem. This will help make our function usable if we did want to, if we had red, green, and blue circles instead of just red and blue. So we can check the length of ypred for the first sample. If that's greater than 1, print doing multi-class classification. And then if so, we have to reshape our predictions to get them ready. Now here we got to go ypred equals np argmax. We haven't seen this before. We could use tf argmax as well. Ypred axis equals 1. Reshape xx.shape. So we're reshaping it just to the shape of xx up here. Now let's make else. If they're binary, we'll print doing binary classification. So this is just the else statement for this little if condition here. And then ypred equals np round. So we're just rounding our prediction. Ypred reshape to xx.shape. Now we're finally up to plot the decision boundary. Again, this function has a fair few steps, but again, if you want to understand it, take them out, deconstruct it, and look at what's happening line by line. That could be some homework for you after this video. Why? I want to contour plot. So what is this? Plot contours. Nice and succinct definition from that documentation there. Thank you very much. But again, we're going to see what this looks like rather than just reading docs. We're going to write as much code as we can. Alpha, wonderful. And we're going to plot a scatter. We need to plot the 0th axis of x and x's first axis. and color this in Y. S equals 40. Now what does the S parameter do? Where is S? There, scalar. So the marker size in points. So this will define how big the size of the scatter plot points come out. And then we're going to plot CM, RD, yellow, blue. This is our color. And plot XLim. We want to set the limitations. So this is where XX minimum comes in and the XX max comes in, as well as the Y limitation. We can do the same thing for YY, min, and YY dot max. Whew. Okay, that's probably the biggest function we've written so far. I mean, it almost doesn't fit on the screen. A lot going on here, but now that we've got a function to plot our model's decision boundary, I mean the cutoff point between the decisions it's making between red and blue dots, let's try it out. So we go here, we'll run that. Hopefully there's no errors. Check out the predictions our model is making. So if we want to plot decision boundary, we pass it in our trained model, which is, we'll set model 3 because that's our most recent model. X is just X and Y is equal to Y. Remember, X and Y are just our features and labels. So again, 1 point here leads to a 1 or a 0. We'll get rid of that. You ready? 3, 2, 1. Oh, would you look at that? So, this is why our model is performing so poorly. It looks like it's trying to draw a straight line through the data. Now, what's wrong with this? Well, we've got circular data. So the main issue here is that our data isn't separable by a straight line. But if we were working on a regression problem, what is a regression problem? Now, in a regression problem, our model might actually work because it's drawing a straight line. So how about we test that? We might do that in the next video. And as for this function, if you're wondering, Daniel, like, how did you learn how to create all of this? Well, the truth is, I've borrowed this and I've adapted it for our use case. So if we come here, one of the resources I used was CS231N, Neural Networks Case Study. Now, this is a phenomenal course, Convolutional Neural Networks for Visual Recognition. We haven't actually worked with convolutional neural networks yet. So if you go through this, it might be a bit full on, but I'd highly recommend this, as this is going to be a part of the extra curriculum for this section and the convolutional neural network section. So if we come down here, I dug into the code behind this material here, and I found this. So they've got some spiral data here, and I've just changed it for our circular data. And so I'm going to put this link in here. This function was inspired by 2 resources. Number 1 is this one. And then number 2 was another phenomenal resource, Made with ML. So if we go to Made with ML GitHub, and then into the basics. So this is a phenomenal repo. I highly suggest you star this one. I definitely have. If you want to learn more about machine learning and deep learning and how to code them, there are some amazing notebooks here. So I got it from this one here, the multi-layer perceptrons. We come in this one. Oh no, that's for PyTorch. We come into TensorFlow. Now there's a function in here somewhere, very similar to the one we have. Boom, plot multi-class decision boundary. So there we go. So I'm going to copy this resource here. Number 2 is there. So I'll make sure to link those in the extra curriculum. But in the meantime, let's try and adapt our neural network to see if it works, even though we're working on classification right now. Because our neural network is plotting a straight line here, or predicting a straight line, I wonder if we can adapt it to a regression problem. Let's check that in the next video. In the last video, we created a function, plot decision boundary, to visually inspect our model's predictions, and we found that it's performing so poorly because it's predicting that the decision boundary is a straight line, whereas our data is circular. So we have a linear decision boundary, which linear is a fancy word for straight line. And we have non-linear data, which is another fancy way of saying non-straight data. Now, if we come back up here, I've just added a little tidbit in here in retrospect, but we've already discussed this. It's that, remember, wherever you see the key, it's an important point to note. Whenever your model is performing strangely, or there's something going on with your data you're not quite sure of, remember these three words: visualize, visualize, visualize. Inspect your data, inspect your model, inspect your model's predictions. And that's what we've done here. And we also discussed that since our model is predicting a straight line, might we be able to use it for a regression problem? Let's have a look. We'll write some code. Let's see if our model can be used for a regression problem. Now, we'll need some regression data. Now, I'm going to set the random seed here because we're going to create some regression data. And we'll make x regression so we don't override our already existing x variable. And I'm going to do tf range 0 to 1,000, and the step can be 5. And then y regression can be tf range 0 to, actually let's start from 100. So the function here we're trying to predict is just y equals x plus 10. That's the relationship between x and y here. Plus 100, because y starts from 100, finishes at 1,100. X starts from 0 and finishes at 1,000. They both have the same step. So let's check this out. Remember, visualize, visualize, visualize. Inspect your data. Become one with the data. So there we go. Starting from 0, stepping up by 5, all the way up to 995. Starting from 100, stepping by 5, all the way up to 1,095. So we can remove those. Let's split our regression data into training and test sets. XReg train for X regression can be, let's just make it, how many values? Well, we've got 1,000, so there's 200 total. And let's do the first 150 can be for the training data set, and the last 50 can be for the test data set. So XReg test equals X regression. We want just the last 150, so 150 onwards. That's how we can index that. Then we'll do the same thing for the Y data. We could have actually done this for our circles data, but we'll move on from that one. We'll do that later on, I think. And then we go there. And now let's see. So we've got training and test data. Let's see if we can fit our model. Fit our model to the regression data. Wonderful. Model3.fit. Now before we do this, I want you to have a think. Will this work? Go back up, scroll back up in the notebook. I'm not going to give you any hints, but just step through each of the steps that we use to create Model 3. Build a model, compile a model, fit a model. We're doing step 3 right now, fit a model. Will this work or will it error? Inspect how we created it, inspect how we compiled it, think about the problem we're working on, regression, and have a think, will this work? I'll give you about 3 seconds or so to try that out. Well, I mean, you can pause the video, but 3 seconds for me. 3, 2, 1. All right, did you figure out why it will or won't work? You know what I hope you did? I hope you ran the code instead of scrolling back up. I hope you just tried it, because that's what I'm going to do. Oh no! What's happened here? Input 0 of layer sequential 2 is incompatible with the layer. Expected axis of -1 of input shape to have 2, but received input with shape none 1. So what's happened? We've got a shape issue, one of the most common issues in deep learning. So what's going on? We got train. Yeah, we've created our datasets correctly. Why hasn't our model worked? I wonder. So we've compiled our model for a binary classification problem. So we come back up here. Where's model 3? Compile the model. We've set the loss function to be binary cross entropy. But what should it be if we're working on a regression problem? It should be something like MAE or MSE, mean squared error or mean absolute error. So let's go back. How about we write here, we compiled our model for a binary classification problem. But we're now working on a regression problem. Let's change the model to suit our data. All right, so the only thing we're going to change in model 3 is the loss function. What I might do is get rid of this code so it doesn't interfere with what we're going to write. So if you want to try yourself, all we're going to do is just recreate model 3 exactly how it is. We're going to change the loss function. Instead of being binary cross entropy, we're going to change it to mean absolute error so that the loss function is regression specific. So give that a try, and otherwise I'm going to start writing it now. So we've got to set up the random seed so we get reproducible results. Set seed 42. Now, step 1, we're going to create the model. We'll just recreate model 3. It's all right, we can override it. TF Keras, and plus, what's the harm in having some more practice writing model code? TF Keras. By the end of this course, I want you to have created over 100 models. Maybe even more, who knows? I'm not actually sure, I haven't counted. Maybe someone out there could count how many models we actually build together and then let me know, because that'd be pretty cool. You know what I should have done? I should have increased this number so we just knew the whole time what number model we were up to. Too late now. And so compile the model. Now this time with a regression specific loss function. Beautiful. Model 3 dot compile loss equals TF Keras losses MAE. Beautiful. And then the optimizer can be TF Keras. We're going to keep the optimizer the same. We'll keep it as Atom. Optimizers.atom. Remember, Atom is safe. Metrics equals, we need to adjust the metrics as well because it's a regression problem. We'll keep MAE there. And finally, 3 is fit the model. So we have model 3, we've recreated it, dot fit on X reg train and Y reg train, which is our regression data set. And we'll set it up for 100 epochs. Now you ready to run? 3, 2, 1. Ho-ho! There we go. Now what did it start with? Did we have... Oh, so the MAE is close to 250. And by the end, we go right down to 37. That's beautiful. So we see a reduction in loss and a reduction in MAE. But to make sure, seems like our model's learning something from these training metrics. Let's plot them. So just like we've plotted our circular data, we'll plot our regression data. So make predictions with our trained model. Y_reg_preds equals model3.predict x. Make it on the test data set. Oh, sorry, it's going to be, predict x reg test. Yeah, that's what we want. And now let's plot the model's predictions against our regression data. So we can create a plot here. We're not going to write as big and intricate a function as we did for our classification data because this is regression data is just a straight line. And we're going to do a scatter plot. And on this scatter plot is going to be the training data. So X reg train, Y reg train, and the color of the training can be blue. We'll label it training data so we know that it is the training data. Create another scatter plot, this time for the test data set. So test features and test labels. And we will color this with green and give it the label equals test data and plot scatter X reg test. And now let's plot our reg predictions. And we're going to have to No, I think that should be okay. We might have to... I wonder what dimension they are. Well, we'll check. If in doubt, run the code, wait for the error to pop up for us, and then we can see, and then plot legend. So that's what we've done. We've trained a regression model. We adapted model 3 to be suited for our regression data. We've made some predictions on the test data set, and now we're just plotting it, just like we did in the regression section. Training data, test data, predictions. Let's go. Figure. Oh, we want this to be fig size. Oh, would you look at that? Okay, so the predictions aren't perfect. I mean, if they were, the red line would line up perfectly with the green line, but they definitely look better than complete guessing. I mean, imagine if the predictions were all over the shop, like red dots everywhere. That would be basically guessing for this regression problem. Now, this means that our model must be learning something. However, it's still missing something for our classification problem. What's the difference here? What is the main difference between our data sets? I'll give you a hint. This regression problem is a straight line. Whereas if we come back, we discussed this before, our classification data is not a straight line. It's non-linear, but the decision boundary our model's trying to plot is linear, straight line. So, that might be the missing piece, the thing that we haven't introduced to our models yet. We haven't introduced non-linearity. And if you haven't heard of that before, that's okay, because we're going to discuss it in the next video, and probably maybe a couple of videos after that. So let's write that down. The missing piece. It's like we're on a treasure hunt here. Non-linearity. Alrighty, get excited, because we're going to learn one of the most important concepts in neural networks. Woohoo! I'll see you in the next video.